I'm wondering if, I was wondering if it was just right in front of it. Is it better? I don't know.
Testing, is it working? Testing, yes. Does have priority over the PI. And where do you sit? Here. All right, all right. I'm just giving you a hard time. That's right. Section 5 on, can you hear me all right? On tomography and 3D tracking. I'll be chairing with Robin, and the first talk is on solar rotational tomography of the corona with latest instrumentation by Alberto Marcos Vasquez.
Hi, thanks. Good morning. So I'm going to show you some results we obtained recently with the instruments that lately we have been using for tomography that haven't been used before for tomography. This is work in collaboration with Federico Nuevo and a bunch of colleagues from here, from Michigan, and from Italy. So in solar rotational tomography, we use sequences of coronal images in an optically thin regime to determine the three-dimensional distribution of the corona of different physical parameters. So in the case of white light, which is what I'm going to talk about, because I'm going to talk about METIS, that's a diagnostic of electron density, so you can hope to build three-dimensional maps of the electron density. I'm going to show you results today on both METIS and UCOMP. Those two instruments have not been used before for tomography. In the case of METIS, we have two detectors. We have white light and we have Lyman alpha. So with white light tomography, we can, again, do tomographic reconstructions of the electron density. And with Lyman alpha, we can find the three-dimensional distribution of the Doppler dimming term, which is a constraint on wind speed. I'm going to talk a little bit about that at the end, but there's a poster about that here. In a previous work, the new thing about METIS is the very elliptical orbit of, highly elliptical orbit and changing orbit of solar orbiter. Previously, so far, with all solar rotational tomography works, we have always used one AU instrument in nearly circular orbits. So this is kind of new. So we did a previous study with simulated images to show that we can actually do tomography despite the very complicated orbit of solar orbiter. And in the case of UCOMP, this is new also, we have these optical emission lines, and what we can do with tomography is find the three-dimensional distribution of their emissivity, and then apply any diagnostic that you guys can do with the intensities of UCOMP, but in 3D with the emissivities. So I'm going to show you first results with METIS and preliminary results with UCOMP. So before jumping into the tomographic results themselves, being the first time that we're using this instrument, and because we usually do white light tomography with C2, we decided to do simultaneous tomography with both METIS and C2 in an independent fashion, observing from very different points of view. But we wanted first to compare their images. So in September 29 of 22, there was this specific superior conjunction. So this red dot is METIS, solar orbiter. This is the Earth, and C2 is almost there. They were really nearly in a perfect superior conjunction within 1 degree. And we compare images. You have here at the top an image taken by METIS, and 20 minutes before that by C2. So these are nearly simultaneous. They are flipped So we correct for the west and east orientations because they are seeing the sun from different points of view. These rings here are for reference elongations 3, 4, 5, and 6 solar radii as seen by each spacecraft. In this case, Solo was at 0.4 AU from the sun. So of course the disk of the sun, which is occulted and represented by this white disk, looks bigger than in situ. I won't spend much time here. This is just another opportunity of observing from opposite points of view, but not simultaneously, not in superior conjunction. So Solo was here in the blue dot at 0.6 astronomical units. Because of the rotation of the sun, C2 was able to observe the exact opposite point of view 2 days later. So you have some dynamics going on in between the two images. Here's a quantitative analysis or a summary of the analysis. So for the superior conjunction, you have here as an example the PV as measured by METIS and LASCO in red and blue as a function of position angle with the images already flipped to account for the opposite point of view. You can see the semi-structures, of course. These images are nearly simultaneous. But when you analyze the ratio of the PV as seen by the two instruments, you have a median value of roughly 1.6. And this is a scatter plot of the points, which correlate very well, of course, because these are really nearly simultaneous images. When we compare the other pair, of course, we have a very similar situation. You have more spread, just because there's some dynamics going on in between the two images that you are comparing. But still, we have this systematic measurement of METIS being roughly 1.6 more than the C2 observation. And I should mention these images are obtained from the Philippe Lamy team in Marseille, in Latmos. Because you're observing from different points of view, one should analyze what's the effect of the different perspective in terms of the line of sight. They are probing the corona in a slightly different way. So we took a 3D model of the solar corona and replicated, computed synthetic images, exactly replicating the observations I just showed. So here you have the case for the opposition. This is a synthetic image as would have seen if this is the sun by METIS and here by C2. And if we repeat the analysis, of course, you have a nearly perfect correlation, and you have slightly different measurements just because the line of sights are not probing the corona exactly in the same positions, but you don't have this systematic brightness in excess by METIS. So there's something going on there, which is probably related to calibration procedures of the two instruments. So now jumping into the tomography, like I said before now, everything has been done in these orbital, circular orbit instruments. So for this particular work, we chose 3 segments of solar orbiter. I show them here in blue, segments over which we are going to do solar rotational tomography. The time sequence of images has to be long enough so you observe the corona from roughly a change in 180 degrees in longitude. So that takes typically in these 3 segments that we chose 13 days, 14 days each sequence, comparable to what it takes to do that with LASCO C2. So we have these blue and red segments. For example, for the blue segment, here you have the field of view of METIS. You see it's approaching the sun, so of course it's shifting to lower heights. So a given observation, the field of view is going from the blue triangle to the red square, and it's going down. And the 2 dashed lines are indicating the limits of the field of view that it's common to all the images in the sequence. Within that range, we can do full tomography. This is the new thing with an instrument in elliptical orbit. So the field of view or the range of heights that you can hope to reconstruct with tomography is a function of time. So this is just the detail for the 3 segments. These are the latitude of solar orbiter, very low latitude so far, comparable to those of C2. And Here, for example, a result for segment 1. I'm showing here reconstructions of the electron density from METIS data at two heights, 4.9 and 5, almost 6 solar radii. So you can see these streamer structures, coronal holes. The black regions are regions that are not reconstructed. One of the main restrictions in tomography is you take a sequence of images, you assume a static corona, and you need to explain all the images in the sequence. So when there is some dynamics, the tomography needs to place strategically some negative values or zero values to explain. Any change in brightness needs to be explained solely by a change of perspective, not by dynamics. So here you have at the same two heights the reconstruction from C2 data. So you can see basically the same structures, and below you have a histogram of the ratio of the reconstructed density in each location of the corona. We have this median value of 1.73 that is very close to the ratio of observed PV values. So this is a linear relationship, right? I mean, this density is proportional to the intensity seen by the images. So this is a scatter plot. There is a pretty good correlation between the two reconstructions. And this is just to show you the three-dimensionality of this. This is an average radial profile from the two tomographies. You can see the consistent METIS larger density as opposed to the one obtained with C2. Segment 2, which was this red segment here, is consecutive to the next one. The corona didn't change much, so this is a result for segment 1. This is for segment 2. You see some evolution in the corona, but you still see the same structures recovered by the two reconstructions. Again, seeing the sun from the same point of view. Thank you. So this is the numerical, the quantitative comparison between them. Here we have a slightly larger correlation, probably meaning that there was less dynamics. So the reconstructions were more comparable. This is the third period, which was 2 months after the other one. There's a notable evolution of the corona, but still you see the same structures. This is the one that has the largest correlation, probably indicating, again, less dynamics going on during the data acquisition time. So the structures that you can reconstruct with the two instruments are pretty much the same. So just a few comments. Like I said, the METIS field of view changes as a function of time. It goes from roughly 6 to 10 solar radii at maximum aphelion and down to 1.7 to 3 solar radii at minimum perihelion, and nearly always overlapping C2, so we can always do this kind of comparison. In summary, comparing the images, we get a 1.6 ratio between the intensities observed by METIS and C2. When we do tomography, we get a pretty consistent ratio in the reconstructed density. And this discrepancy is not due to finite distance to the sun or lack of perfect composition. We carefully analyze that with simulations. This is all to be found in the calibration procedure, so there's an effort going on by the METIS team led by Burtovoy on the calibration of METIS. I just want to highlight then that tomography might serve as a side thing, a side benefit of tomography, might help to intercalibrate instruments, because when you have these oppositions, these are very rare occasions to directly compare images from two instruments. Those images greatly depend on the point of view, but the reconstructed electron density in this case, of course, does not. So this is research that was recently submitted in 2 different articles, one focusing on the data and one focusing on the tomographies. So I'm going to close my talk just showing, this is very preliminary, we just did that a couple of weeks before I came here. So we took UCOM data, specifically 174 and 179. These are peak intensity with images. These are total intensity images. And we adapted our codes to feed the total intensity images from UCOM. So once we do tomography, for example, with 174, what we have is, what we get after the tomography is the three-dimensional emissivity in the line. So these are latitude and longitude maps of the emissivity at 1.1, 1.5, and 1.2 solar radii, which are in the field of view of UCOMP. These are the same maps for 79. Like I said, these dark features, there might be unreconstructed regions due to some dynamics, or there can be lack of data at some positions, for example, in 179, especially at the poles. And like I said, you can now do the diagnostics that you can do with UCOMP images, you can do them now with the emissivities. So here you have at 1.1, 1.5, 1.15, sorry, and 1.2 solar radii, the reconstructed electron density with UCOMP, with the line ratio diagnostic, but applied to the emissivity. Here you have we did simultaneous tomography with KCOR, so at the same heights, this is the density, and this is done with EUV tomography, which I will not talk about here. There's a poster that I can, if anybody's interested, I can explain a little bit about this. We can derive electron density. This is done with AIA. And now, to close this is a comparison of the electron density reconstructed with UCOMP versus that of AIA in every point of the corona that we analyze. They are very closely clamped around 1, median close to 1, and these are the radial profiles, which match very nicely. This is very interesting to us. And this is what happens when you compare the KCOR electron density reconstructed with tomography compared to UCOMP or AIA, because they are very similar. We have a significantly larger electron density from KCOR. That is something we have previously done, and we obtained that result. So the new thing is that we were able to add a third diagnostic on the same field of view, which is UCOMP. So I should close my talk. Just want to mention that, for example, the UCOMP electron density is independent of the abundance of iron. Those are iron lines, but because it's a line ratio, you don't depend on the abundance. But the density from AIA tomography depends on the abundance of iron. So comparing those might help to provide constraints for iron abundance distribution. And I will just wrap up saying that my first line, as new coronagraph become, or imagers of the corona become in general available, there are new opportunities for tomography, and I hope we can do work with punch as well. There's a poster here on Lyman alpha tomography and what we can do with that concerning the solar wind speed. So that's all. Thanks.
Yeah, call for our next speaker. This talk is Tomo reconstructions of coronal mass ejections in solar corona with physics-informed neural radiance fields. Robert Yarlum. Probably don't have that pronounced correctly.
Perfect, okay, thank you. Yeah, hello everyone. Thank you for inviting me here today. This presentation is about tomographic reconstructions, and in particular with recent deep learning methods. And today I want to talk about neural radiance fields and also about physics-informed neural networks and how they can be used for tomographic reconstructions. So the outcomes here are basically from the Frontier Development Lab from 2022 and 2023. And I'm happy to present the results of the team basically here today. So the main motivation here is that we want to obtain a better understanding of the evolution and the distribution of the plasma in the heliosphere. And what we are dealing here with is this intrinsic limitation of the optically thin emission, which makes it so difficult to properly interpret our data. So, and as we have seen already over all the past presentations, we really need new sophisticated methods that can properly interpret the data and give us this full 3D distribution of plasma in our heliosphere. So here we are basically asking the question, how can we efficiently combine observations with the most recent technology and the physical models in order to determine the plasma distribution in the solar corona? And for this presentation, I will start with a quick introduction on physics-informed neural networks and what they are. And then I will go first, I will show the first results basically just to explain how the methodology works for the EOV corona. And then we move forward to the outer corona for tomographic reconstructions of coronal mass ejections. So if you're familiar with machine learning method and the recent successes that we have seen, you probably have seen mostly this side here on the right, where we have a large amount of data available, but very little understanding of the underlying physics. So for example, image classification or large language models, those are all in this regime. On the other hand, in physics, we usually have the problem of very limited data, but a good understanding of the underlying physics. So this is where we can actually make use of physics-informed machine learning, which deals with the regime on the left-hand side, where we can essentially use the physics in conjunction with neural networks to learn more about our data, and also for the intersection where we have some data available and some physics to learn new physics. So in both of these regimes, I will try to cover with this presentation here. So the underlying concept here are physics-informed neural networks, and they are especially designed for this small data regime where we have the known physics and given boundary conditions. So here, a neural network is basically used as a function representation of a simulation volume, where we perform a mesh-free simulation where we can solve certain boundary conditions and partial differential equations. So this is basically shown here on the right-hand side. What we're doing is we use coordinate points as an input for a neural network, which maps the coordinate points to the respective quantities in our simulation volume, and we can then optimize the neural network for a given set of boundary conditions and the physical model. So one example of this is shown down here, where this is applied for the Navier-Stokes equations, where basically the boundary condition is given by this box in the center, and then by solving the Navier-Stokes equations, we obtain the flow field in the remaining volume. So essentially it's a solver method that we're using, and it's only used for solving a single problem, but we obtain basically new data through this. So this is the decisive difference to like general learning methods. So let's have a look at the first application of this concept for tomographic reconstructions of the solar EOV corona. So the main motivation here is the limited number of viewpoints that we have. So in total, we had like a maximum of 3 parallel viewpoints of the solar EOV corona. And all of this plasma is like extended in height, but optically thin, which makes it so difficult to combine this data into a consistent 3D image of the sun. In addition, we also only have ecliptic viewpoints. So for this challenge, we were basically trying to combine and leverage the recent observing capabilities that we have to obtain a 3D reconstruction of the sun. And from this 3D reconstruction, we want then to basically get viewing points from different positions. So this can be from the ecliptic plane, but also out of the ecliptic plane. So how do we do this? So this is based on a method which is called neural radiance fields. And here we adapted this for the solar case, which we call sun neural radiance fields, or short, SUNNERVs. So you can see so what we have is basically we have observations of the sun from different viewpoints. So what we can do is we can trace rays through the individual pixels of the image into a simulation volume. So here we use our neural network as a representation of this volume, which maps the coordinate points to the respective emission and absorption values. So we cast the ray into the volume, sample points along the ray, and then use those points as input in terms of x, y, z, and also the time component t. From this we get then emission and absorption coefficients, which we combine into the corresponding profiles. And by using radiative transfer, we obtain then our final predicted pixel value, basically. So by comparing this to the original images, we can immediately match those two values. And since all of these operations are differentiable, we can start optimizing our neural network to give us emission and absorption values that match the resulting pixel values. But we're not doing this for a single image, but we're doing this for a video sequence of images from multiple viewpoints. So essentially, we are probing this volume from multiple different angles, which gives us then, where we need then to find a solution of emission absorption values that satisfies all observations, which then gives us our reconstruction. So for the first application of this, we applied this to EOV observations from 3 different viewpoints with the ideal angle between them. And we did this for a video sequence of 14 days. And from this, we obtain then this 3D reconstruction, where we can, at the given point in time, we can orbit around the ecliptic, but we can also move to non-ecliptic viewpoints, and we can also model this over time. We can see here also that we can capture this eruption and model the dynamics, even from like a polar-like viewpoint. So how can we apply this concept now and move this forward for tomographic reconstructions of coronal mass ejections? So here we want to build again on this concept of multi-viewpoints and recent and hopefully also future observing capabilities in order to deduce the direction, velocity, and mass of coronal mass ejections. So for this, we built on synthetic data. So for this presentation, I'm not going into the application to observations, but here we're dealing with an idealized data set of synthetic punch observations, which were prepared by Anna Malonushenko, and you will hear more about this later today. But just in short, this is based on a Gamera simulation, and specifically, we cut out a smaller region starting from about 22 solar radii up to 100 solar radii, which is what we use as a ground truth reference in order to validate the method for this case. Of course, this is idealized, so we don't have noise, we don't have artifacts, we don't have background stars in there, so this is a much simpler problem in that sense. So what you can see down here is basically an overview of our ground truth data, where we have this slice through the ecliptic. So this is the electron density distribution. And then you have the two observers, so observer 1 and observer 2 here, with the corresponding images of polarized brightness to the left and right. So you can basically see the CME erupting through the middle. So this is also the data set that we are using for fitting our model and then trying to recover basically this electron distribution from the whitehead observations. So what are we seeing here actually is Thomson scattering. So I'm not going in all detail here, of course. But the important thing that I want to mention here is that when we look at the total brightness and polarized brightness that we are observing, that this is all dependent on the geometry. So this means that when we have a plasma parcel basically moving through our system, that the brightness will change independent of the geometry. So this is really important for us here because we can actually use this in order to link basically the brightness variations to the spatial location. So by combining basically the brightness that we are observing and the temporal evolution, we can deduce spatial information from this. But this is not trivial, especially since we can find multiple different solutions for this. For example, we can also find unphysical solutions in terms of ghost trajectories. So how do we solve this here? So we use the similar approach as before, where we have multi-viewpoint observations in white light, and cast rays through our simulation volume and render the corresponding points. So here then we use the points as input, and the model gives us the corresponding electron density distribution. So here we then replace basically the forward modeling of the pixel values with the Thomson scattering to obtain our total brightness and polarized brightness images, which we then can compare to the observations. So this is similar as before. We can use this for optimization, but this is usually not enough. So we need additional constraints in order to obtain better solutions, especially in the case for limited number of viewpoints. So what we add in addition is a coupling together with physics-informed neural networks, where we add the continuity equation to our optimization, which requires that, that this is satisfied in our simulation volume. And in addition, we apply regularizations for radial directed solar wind speeds, and also for a minimum velocity that we introduce. So what this means is that all the mass that we have, that we basically map, is only can only enter through the inner boundary and leaves through the outer boundary. So let's have a look at the results that we obtain with this. So on the left-hand side, you can see again the ground truth that we have of electron density distribution, and then you can see here the full coverage, basically having viewpoints all around the heliosphere, which is very unrealistic, and also a bit less realistic here is with 6 viewpoints. But you can see when we place 6 viewpoints around the ecliptic, equally spaced, we obtain reconstructions that are still very similar to the actual ground truth. So a more realistic case is actually to go to 2 viewpoints where we have the observers located to the sides, and you can see that we still obtain the proper direction, speed, but there's a slight deformation. let's have a look at this in a bit more detail and in comparison with the 6 viewpoints that we have. So here you can see basically that when we look at the horizontal slice, we can see this deformation where this is like slightly truncated just based on the viewing angle of the observers. And when we look at the vertical slice, however, we can see that this matches very well and reconstructs this shape very well. And in either case, we obtain the distribution quite well in terms of seeing the bright front and also the dark cavity. But how does this actually, so this was like for an ideal case where we have the observers located like right around the CME, but how does this vary when we apply this for different viewing points? So here we did this always with 2 observers and a 60-degree separation between the 2 observers, but at various different locations, which are indicated here by those green arrows. So you can see this basically with a shift of the observers by 90 degrees, 270 degrees, and 180 degrees shift. And we can see that we have, when we shift like to the sides, we have a slight shift to left and right in like the range of 5 to 10% in degree, sorry. But still, we obtain the correct direction from this, even though the observers are observing the CME from the side. However, when we move to the other side, this is basically just a sanity check. We can see that we don't obtain a reconstruction, of course, because we don't observe the CME directly, but we are just looking at it from the back, basically. We can see that there are some artifacts basically occurring for this case. So the last thing that I want to talk about here is basically the importance of the physical constraints that we were adding to this. So by just doing a ray tracing approach and just optimizing for like the observations that we have, we obtain for 2 viewpoints and 6 viewpoints very like structured field, which is like kind of unrealistic. And you can see also like this wobbling basically in the field, which is just like basically background noise. So we don't obtain the solutions that we're looking for. However, if we introduce the additional physical constraints, we see that we obtain much smoother solutions that even give us better results than for the 6 viewpoints, just based on those 2 viewpoints with the included physics. And we can also see this here from this distribution of when we compare the electron densities that we obtain. So on the x-axis, there's the ground truth density. On the y-axis is the model density. You can see here this distribution where the 1-to-1 correspondence is the central line. So we can see that this matches much better for the 2 viewpoints with the included physics. So in summary, newer radiance fields enable us to, are basically a novel tool, which enable new approaches for tomographic reconstructions, both for EUV and white light observations. And by including additional physical models with the ray tracing methods, we can overcome limitations of the viewpoints. So, of course, the results that I showed here today were based on synthetic data. So moving forward, we want to apply this also for observations. But as you can see, it's like we have different field of views, we have different physics in the individual domains. So connecting these domains and including the physics in order to tie them together is basically the next thing that we have planned in order to combine this into a consistent 3D image of our heliosphere. Thank you.
Thank you. Our next speaker talk is Deep Projective White Light Traces of the Slow Solar Wind, Cynthia Lopez Portela.
So, good morning, everybody. My name is Cynthia Lopez Portela. I'm a postdoc at Goddard Space Flight Center with Nikki Bayal in the group of heliophysics. Okay, so the content of my talk are divided into 6 sets. The first one has to be with the quasi-static solar coronary structures and the slow solar wind. Then the mesoscale structures as traces of the solar wind. Then I will continue talking about the high time analysis technique. That this technique, what does is to produce the projected data from coronagraphs. Then I'll mention some applications of this technique. I'll talk about some future exploration, and finally I will conclude. So during solar minimum and solar maximum, we observe Wait, where is it? Okay. We observe these bright areas. And in solar maximum, we observe these helmet streamers along all latitudes around the solar disk. And in solar minimum particularly, we observe these helmet streamers localized at equatorial latitudes, and we have this intensity in brightness due to the fact that we have the solar magnetic field, we have the close magnetic field lines, solar magnetic field lines close, and the important thing and the interesting thing comes when magnetic field reconnection happens, and the magnetic field lines opens and permits the detachment of coronal material into the heliosphere. So in 1997, Chile made how can I say, he studied the characteristics of blobs, which are a subset of mesoscale structures, and he mentioned that they are compact structures that are detectable in brightness intensity. We have to apply techniques to enhance their, to visualize the structure. They have a radial size that ranges from 0.1 to 3 solar radii. And they basically, as they propagate in the corona, they propagate with a constant angular extension of around 1 solar radii. They mentioned that they are detectable from 3 to 30 solar radii because they work with the LASCO coronagraph C2 and C3. And after Chile publication, there came other studies, like the one mentioned by Song in 2009, and basically they have like the same characteristics of, with blobs. So we know that all the astronomical observations with a telescope, we have bidimensional images. And if we want to trace the motion of any features that appear in a sequence of images, we have strong problems with projection. So the exploration of appropriate techniques to reduce the projection effects in white light trajectories allow us to take advantage of different spacecraft locations, which comes something like natural to think if we have different spacecrafts located. To perform an accurate tracking of the solar wind to analyze its kinematic behavior, and this is one of the main goals of PUNCH mission. So for the high time analysis technique, what I did is to select the data that is basically propagating in quasi-radial trajectories for this technique. And this technique, I have to mention that is not appropriate for large structures that are like CMEs. It is important to mention also that at least the structure has to be detected by 2 coronagraphs in order to perform the deprojection technique. I use the LASCO coronagraphs and Core 2 A and B onboard stereo. I basically perform the detection of these structures along the equatorial latitudes. And, well, this is a slide that I can stop too much about the mathematical things, but I would like to mention that this is a coordinate system of epipolar geometry, and it takes into account 3 assumptions. The first one is that both the spacecrafts are localized at the same ecliptic plane. The geometrical vector analysis is appropriate for the reconstruction instead of using projective geometry, and the epipolar lines can be treated as parallel to the ecliptic plane. So what we have in this slide, very briefly, is that on the left side, this is like a cartoon of a coronagraph image where we can obtain RB, which is the radial distance from the center of the coronagraph to the object I would like to trace. Let's think or imagine that I want to follow the trajectory of this point. So I can obtain also, I measure from the images the position angle, and imagine that you have this same cartoon duplicated. So we obtain 2 radial distances, 2 position angles, and it's very important to mention that this technique has a very important parameter that has to be obviously with the separation between the spacecrafts. So the real position in the space in spherical coordinates are given by R3D, that is obtained by this expression over here, and we have the ecliptic latitude and lambda being the ecliptic longitude. So this is a real coronagraph image that now is the real one, not the cartoon. And I have to mention that the detection of these structures is not an automatical one. And I have to think about the observer. So what I did is to write the codes so that have a more familiar interface to localize the structures in both of the coronagraphs. And basically, these J-maps are synchronized. So I obtained from this, that because we are interested in obtaining the real positions of these objects, I have to mention that the R3D position uncertainty that we found for 13 mesoscale structures, that is the equivalent of detecting 44 single structures between 3 solar radius to 15 solar radii, and this has to be because of the combination of the field of views of the coronagraphs I mentioned I used, and it was just along 2007 and 2008, which was along the long extended minimum. So there is an assumption that we did, is just that the spacecraft we assume that are at the same ecliptic latitude. And the fact that we found is that when we perform this subtraction, so the subtraction of the longitude of the spacecraft and the projected longitude of the object, we found that when this happens, when this number is small, it happens that the structures are brighter and are more visible in the plane of the sky of the coronagraph that appears here in the subtraction. And we found for this period and for these events that the best spacecraft separation angle is around 30 degrees. So what are the applications of these projected trajectories? Well, we can calculate the 3D parameters as position, radial velocity profiles, and of course the acceleration through the application of kinematic models that are based on real trajectories to characterize the solar wind flows. We can also, with these 3D parameters, we can apply them to explore the motion of mesoscale structures, testing different dynamic models based on physical and morphological 3D data. We can also test models that use, for example, the information of the observations between that combine magnetographs and coronagraphs images, like the one mentioned, just to mention as an example, the one mentioned by Mueller in 2013, and there are other models apart from this that was developed by Wonshili and Argy. And this can be done to compare the inferred and the calculated 3D radial velocities of the solar wind. We can also compare with solar wind flow tracking techniques. The observations of the three-dimensional space like PUNCH mission, we can compare this information also with PUNCH mission, with the information that PUNCH mission will produce. So what is next? Well, the idea is to explore this technique, expanding, going closer to the sun surface, could be with core 1, A and B, and maybe to expand also this kind of technique to the heliospheric imagers like High 1 of Seki on board SOHO. And with this kind of exploration, we will be able to have more information about the origin locations of the mesoscale structures and their evolution as they propagate through the heliosphere. This is, of course, additional to the unified punch of view. Thank you. So my conclusions are the next ones, and has to be with that the high time analysis technique is appropriate for coronagraph data. I use LASCO and Seki. Permitting to produce the projected positions in 3D coordinates along the field of view from 3 to 15 solar radii. And this technique enables then to perform the flow tracking of mesoscale structures in the solar wind at equatorial latitudes. But the good news is that PUNCH, white light observations, will enhance the detection of these mesoscale structures in a field of view from 6 to 30 solar radii, extending, of course, our knowledge and exploration of the solar wind behavior. The second conclusion, I would say that one of the most interesting applications from my point of view of producing this projected data is that it can be used to test models in space weather. And what's even more, PUNCH mission will open the opportunity to perform model validation to constrain the simulations in space weather. So thanks for listening and happy summer.
Thank you. One more talk.
There's one more talk.
This talk is demonstrating wind speed measurements with WSPR via the stationary point. Sam Van Kooten.
Cool. Forward back. You got it. All right. Hi, everyone. I'm Sam. This is some work I've been doing with Craig and Kenny at SWRI. I think it's a true statement that this work is my main contribution to PUNCH and that I've taken the project off of Craig's hands so he can focus on working on PUNCH. So WSPR is the camera on Parker Solar Probe. PSP is very close to what it's seeing. It's moving very quick, so you get a lot of relative motion relative to what WSPR is seeing. And PSP is always rotating relatively rapidly to track the sun and maintain heat shield alignment. So when you see all these structures in WSPR images and you want to kind of track them and understand velocities, none of your traditional flow tracking methods are going to work because there's a lot of other contributions to the apparent motion of features in these images. So this is what we believe is a very novel technique that we've developed to kind of exploit that unique observing geometry to infer how things are moving in WSPR images. I'm going to start by demonstrating the method with a toy model that I put together, and then I'm going to move on to actual data. So here in this toy model, we have PSP is up here, this blue dot. It's moving on a realistic PSP trajectory. You encounter maybe 13, something like that. The WSPR field of view, the realistic field of view, is indicated by these white lines. And you can see that that field of view is kind of always rotating to track the sun. So it's always kind of the same angular distance from the sun. It turns out Google Slides, I couldn't find a way to automatically make the videos loop, so we're having to kind of just re-click on these. The orange dots are a cloud of plasma parcels all moving radially out from the sun. And on the right, what you see is a synthesized image of this setup. So you see all these parcels, they're all moving throughout the image. There's a very predominant rightward motion due to that rotation of the camera in the spacecraft. So there's nothing too remarkable here. But if we go to the next slide, so that video you just saw is on the top. And on the bottom, what I've done, instead of having that realistic WSPR rotating field of view, this is a fixed field of view. It's always looking in the same direction relative to PSP. And in this setup, what you can notice, this particular plasma parcel that I've kind of made artificially brighter, it corresponds to the green one over here. It is not moving horizontally in this image, in this kind of fixed direction field of view. It's drifting vertically, but it's fixed horizontally. So it's always in the same direction relative to PSP. So its velocity components, it obviously has an upward velocity component. It does not have a horizontal velocity component. And then it has a component toward or away from the spacecraft in the PSP orbital frame. That could be towards PSP, away from PSP. It could very unlikely be a zero velocity component in that direction. But for this talk, I'm going to focus on that. It's getting closer to us, that case. I consider all of it in the analysis. So this parcel, it's in the fixed direction relative to PSP. It's moving toward PSP. It's going to fly above PSP. And that encounter geometry, which is coincidental, it's not something every parcel will have. But when a parcel, by coincidence, has that kind of unique approach geometry, that puts constraints on what its velocity can be and what its position can be. So I'm going to Find that it's not clicking forward. Here we go. And I was going to skip past this video just to go to this geometry diagram. So to kind of illustrate what I was describing earlier. So here's the setup with the sun over here. This is starting with a 2D case. The next slide will be 3D. So I have a plasma parcel that's moving radially out from the sun. And I have PSP over here, and it's moving with some velocity vector. And a key part to this analysis, I'm working in a small window of time where PSP's velocity vector can be approximated as constant. So that and the parcel moving radially out from the sun are kind of my two big constraints. If we shift to the PSP rest frame, we subtract the negative of its velocity from everything. So in the PSP rest frame, the parcel's velocity is its own velocity minus the spacecraft velocity. That gives this kind of apparent velocity in the PSP frame, which again, by coincidence for this parcel, is directly toward PSP. So in this 2D case, this is a parcel which fortuitously is on a collision course with PSP, which puts constraints on where it is and how fast it's moving. In the 3D case, so here the 2D geometry is all the same in this XY plane, which is the PSP orbital plane. Now the particle is moving out of that plane, still radially out from the sun. So its projection into the orbital plane kind of does everything that I was just saying. It has its own velocity component. You subtract the PSP velocity vector to go into the spacecraft rest frame, and the in-plane velocity component is directly towards PSP. You'll notice I've kind of labeled every angle that could be labeled in this diagram. Don't pay attention to all that. I do use those angles, and I actually labeled one additional angle since I made this slide. But what's important is just kind of the vector geometry here. So the in-plane stuff, the fact that it's moving directly towards PSP, and so it's always seen along the same line of sight, or in the 3D case, it's kind of its projection into the plane is always along that line of sight. That puts this constraint, that the plasma parcel's velocity component in the plane is related to the PSP velocity. The direction in which we see it as an elongation measured relative to the sun and measured relative to the PSP velocity vector. And then this longitudinal separation between the plasma parcel and PSP, which is also unknown. So one constraint relating these two unknowns. And then the out-of-plane angle at which the parcel is seen, this kind of alpha angle, that value and the derivative of that angle put a second constraint relating those two values. And that's an equation that's not worth putting on a slide, but when you plot those two constraints, so here this is the in-plane velocity component on the y-axis, x is that longitudinal separation between spacecraft and parcel. The constraints look like this. That first constraint is the blue curve. The second constraint is kind of two variants for whether you assume the parcel's approaching or retreating from PSP along that line of sight. There is a big discontinuity there. It's not physical, it's understandable. It can never affect the actual solution you get. For time, that's all I'm going to say, but I'll say more in the paper. That should be submitted soon. So these constraints, they intersect. That gives you a single value for that longitudinal separation and the velocity component. And then from that, you can work through the geometry and recover everything. The 3D position of the parcel, the 3D velocity vector of the parcel. So this is for that toy model I was showing earlier. So I know the actual values and the inferred values from this method are all very, very close to the actual values. So in this ideal case, the method works very well to recover what that plasma parcel is doing. Now I'm going to move to actual data. So this would be a good break point if there's another fire alarm. I think we're good, so let's move on. So this is real WSPR data. And remember I was showing earlier, WSPR is always rotating, but I need to work in that sort of fixed direction field of view. With real WSPR, I can't just repoint WSPR like I did with the toy model. So I kind of reproject the data into this fixed reference frame, where this longitude, the x-axis, is fixed directions relative to PSP. And you'll see in the background the stars are always at the same location because they're always at a fixed direction relative to PSP. And there's a number of plasma parcels kind of moving through this image. There's a lot of other stuff. There are a few parcels that if you look closely, you can see that they don't move horizontally. They just move vertically. And I'm going to zoom in on one of those and slow it down. I hope this shows up well on the projectors. I think it looks better on the projector than on the screen, actually. But between those arrows are just moving down, and in between them, there's always kind of a little clump there. In some frames, it's hard to see. There's stuff moving above it and behind it, but there's something there. There's something consistently there. So I, clicked on that little feature in all these images to compute the angles, the horizontal angle at which we see it, and the vertical angle and the derivative of that vertical angle. And that produces these constraint curves. Again, there's an intersection. That weird discontinuity is a lot smaller here. And these are the inferred values you get from those two constraints. That this plasma parcel is moving at 260 kilometers a second at 6R sun from the sun. It's 100 degrees away from us in longitude, and it's 50 degrees below the PSP orbital plane in latitude. Those parameters, if I feed those back into my forward model and put a parcel on that inferred trajectory, it reproduces the observations very well. So this is the exact same coordinate frame on both sides. The arrows are in exactly the same locations. And you can see that in both frames, there's that thing always right there in between the arrows. So it kind of closes the loop. A implies B, B implies A. That's really good to see. That inferred location geometry, it all looks like this. This video is mostly just to kind of emphasize this is that full 3D position and velocity vector solution. So again, PSP is the blue dot with the WSPR field of view is this little pyramid. Orange is the plasma parcel. The thicker part of that line is the region in which we see it, and I've just extended that line illustratively for the visualization. We can do some error analysis on this method as well. If we allow for up to a 1 degree error in the horizontal angle at which I'm seeing the parcel, at which I'm measuring it, up to a 1 degree angle in the vertical, 1 degree error in the vertical angle, and 5% in the derivative of that angle, and just kind of work through a grid of all the combinations of those possibilities. You get kind of these distributed constraint curves and a whole range of intersections that looks kind of steady, but there's, I think, more dots in the middle than on the edges, because if you make a histogram of what are the inferred values for all these combinations of possible error, you get these distributions, and all these inferred parameters, they stay within about 10%. So I think, for reasonable amounts of error, considering you're clicking on the parcel in a bunch of frames and kind of averaging together those measurements, this method, I think, is good to about 10% in all these inferred values. And that is everything I have to say. So this method, we're calling it the stationary point method because the plasma parcel is horizontally stationary. It's at a fixed angle. This method is limited to only those parcels which by coincidence have this kind of approach geometry to PSP. And it's kind of a temporary geometry because over time all the velocity vectors evolve, but for some window in time you have this sort of approach geometry towards PSP. So again, these are kind of the inferred values I got for that one plasma parcel. In the future, I plan to finish up a pipeline to kind of remove debris streaks and stars from these WSPR images so that I can then try some Fourier filtering to clean up the images and isolate horizontally stationary stuff. And that'll make it easier to measure these things and to find these things. And then I'll build up a catalog of all of the horizontally stationary parcels that I see, the inferred velocities, and that'll be over a range of distances from the sun and latitudes above and below the orbital plane. And that's going to be, I think, a really interesting comparison to what Punch is going to measure. Because Punch will be measuring the same sort of thing, distributions of position and angle, and so we can put those side by side and kind of just see how those compare and contrast. I'm really interested in the idea of maybe seeing a parcel in WSPR and also seeing the same parcel in Punch. I'm skeptical if that'll work because I'm focusing on these small, easily localizable things that we're seeing from close up. So from far away, I'm not sure the same things will be visible, but it'll be really neat to try and see if there's any possibility there. And that is what I have. Thank you.
Thank you. Okay, now we have the panel discussion, so if the speakers would come up. Hey, hi. So let's see. We will start with Sarah's question to Alberto.
All right, Alberto. You showed that was really interesting, and it's fascinating that you get the similarities with the AIA and the UCOMP, because even though they are both emission, they're very different measurements, as you said. One's in line ratio, one is not. But can you talk a little more about the differences with the white light? And there's an expected differences because the scattering goes as density and the emission goes as density squared. And have you thought about constraints on filling factor, or is there evolution with time or location?
Yeah. So, like I said, when we compare, for example, UCOM results with AIA results, there we have for sure the difference in iron abundance. But filling factor can be affecting the emission even in the faint corona, because we deal here with the faint corona, with the diffuse corona, not with active region loops. To be honest, you saw a very little difference, very good match between the AIA and UCOMP results, which was really interesting to us. I think those differences are mainly probably due just to an effect of iron abundance. In the case of white light, that huge difference with K-core, and I believe we have a lot going on there on calibration issues. So I look forward actually to talk to you guys about the K-core images and make sure we are on the same ground the way we are using them, and make sure about the absolute units that we're using. I believe there's that big change, difference of density between AIA, UCOMP, and K-core. It's not really due to the filling factor. It would surprise me that such a big difference is due to that in the diffuse corona. So, yeah.
Can you remind me if it was bigger or smaller, the white light?
Bigger, yeah.
I mean, if there are there are electrons that are not at the temperature of the other ones, maybe they're adding to the white light, which doesn't care about temperature, or?
Yeah, probably so. But again, the difference is just too much to me, yeah.
Okay, let's see, Marcus, do you want to ask your question for the tomographic work?
Hi, everyone. So this is a question for all of you. So the SOC is making more realistic synthetic data, and we'll have products obviously after launch. So I was curious what kind of synthetic data would be helpful for you now, and then what products might you be interested in using after launch?
I think tricky to do would be having a proper background star. It's kind of straightforward because you could take a star map and include it, but it's still a lot of work to do it actually. So that would be extremely helpful. But also having realistic noise or maybe even artifacts in there would be a proper test set. Maybe at various levels would be even perfect to experiment what are different the different effects, what they cause, and how they impact this.
I don't know if anybody else wanted to.
Yeah, in the case of solar rotational tomography, again, we talked about this yesterday. It would be great to have access to those FITS files of synthetic images and the model you guys are using to kind of test the reconstructions. Yeah. Again, they could be perfectly, ideal images or have artifacts. That would be great as well. And so, yeah.
Okay, thanks. Several questions here for Robert. Craig?
Okay, so the colloquial version, I feel like I'm standing on a used car lot looking at a deal that's too good to be true. So a perennial concern about any complex reduction method, right, is that it might be plausible but not correct. So have you looked into or thought about the null space of the inversions you're doing? What kinds of confusion it could have?
Right. So, especially for the first study that we did on the EOV reconstructions, we did this really extensively in terms of the validation. So we started basically also from synthetic observation, like from synthetic data, tried to do the reconstructions there, provided uncertainty estimates, and also linked those uncertainty estimates in the end with what we reconstructed. So uncertainty estimates is a good way of basically understanding where we have regions that are like not well constrained and where we have bigger uncertainties. On the other hand, like what we already see, like also for the tomographic reconstructions of CMEs, is that when we have two viewpoints, there are regions that are like not covered, only covered by one instrument, and there we definitely see the artifacts. It's partially constrained with the continuity equation, so we kind of fill in a bit. It makes it look more consistent and a bit more smooth, but of course, like those regions should be avoided, and like probably like we want to exclude them basically from any further analysis and only focus on those regions that have actually like a proper coverage with like at least two viewpoints. Yeah.
Okay, and Sarah, do you want to ask your question to Robert?
Sure. So the question is, have you done reconstruction from non-ecliptic views and in your synthetic analysis, and is there an optical configuration if you only had 3 or 4 viewpoints?
Right. You mean reconstruction from non-ecliptic, like that would be like for solar orbiter, right? That we would also use those, right? Oh, right, yeah, okay. Right, yeah. I mean, like in principle, we can incorporate all the data. Usually we were dealing like with ecliptic data all the time because this is like something that's like most feasible, I would assume, to have like satellites in the ecliptic, and that's also where we have like stereo observations coming together. So that's why we were focusing on this. I think also for the final evaluation in terms of like dealing with different number of viewpoints, I really want to look into having like observations at individual Lagrange points, because this would be like the most likely spot to have actually satellites in and to get basically some information of where the best places are for putting new satellite missions. Yeah.
Yeah, and I think that was my point, was if you were going to design a configuration from the point of view of new missions, like what would be the optimal to actually get the configuration?
Right, yeah. I mean, like this is like still a bit of ongoing work to do more evaluation, like really have probably like a full table of different configurations, also with like stepping angles between the separation angle and so on, to see where we get like a performance drop or where we get the best performance out of this. Yeah, I mean, like I would say like that's still like ongoing to have like the full evaluation to see like where's the best point, but also like to compare it with like realistic configurations.
And Robert, if you're still able to handle more questions, Michael Kirk.
I think Sarah and I were thinking exactly along the same lines.
Okay.
And I think you answered what I was going to ask, so that's great. Thanks.
Hey, Lika, did you have a comment from the floor?
Sorry, I didn't mean to ask the question, but the questions in the panel precipitated, so it's not in Slido. So talking about what Robert presented, the UV part, and I'm responding right now to the point that Craig is making, right? It seems too good to be true. So one of the things we are doing actually is ground truth verification. So the UV model that has been constructed, that can predict UV in the solar system, anywhere, right? And we have actual observations of UV at MAVEN. So that would be actually a ground truth validation, which we are working on right now. What Robert presented with CME, I had not seen that. That's actually very cool, bringing also the physics component. But the other way of looking at it that I'd like to at least try out with the community is that we have lots of data of CME from stereo and LASCO. So sort of taking the analog of what we did with the UV and see if we can do that 4-pi kind of approach, even though the density of observations are not as high as UV. That's faster cadence. This is much less than that. But it would be kind of interesting to see. And then we can do ground truth validation because we have Solar Orbiter, lots of other kinds of missions that are giving us this information. So it's absolutely worth trying because we really haven't had the opportunity to look at all the data we have collected over years and see how it pans out. There's another component here. So there are lots of very interesting mathematical tools, right? There is NORV, there is image-to-image translation from instrument to instrument. Lots of things to look at here. So don't be a complete skeptic.
Okay, so Sam, we have a couple of questions here for you. And my question is related to Sarah's question at the bottom about radial motions. Let's see. Sarah asked, are your blobs all moving radially? That's her question. And mine is, can your technique deal with non-radial motions?
Yeah, so in my toy model, they're all moving radially. In the real sun, I think that's not strictly true, but I think it's often a reasonable approximation. It is, for my method, a necessary approximation. I'm inferring basically 4 unknowns. I'm positioning a radial line, it needs a longitude and a latitude, and then I put the parcel at a position along that, a distance along that line, and give it a speed along that line. So 4 unknowns, I'm measuring the horizontal angle, the vertical angle's derivative, and observing that the horizontal angle is fixed. So that's kind of 4 measurements for my 4 unknowns. To lift radial motion, I'd need some other relevant measurable, and I don't know what that is.
And Craig, you have a question for Sam?
Thank you. Yes. So great. This is actually related to what we just touched on, which is great analysis in the case of stationary items. Does the method generalize to other cases, things that aren't quite stationary, or is there some other intermediate case before you go to full tomography?
Yeah, so I think you've asked me that same question before, Craig, and my answer now is that one thing I'm interested in trying is seeing if, looking for things that have a non-fixed horizontal angle, if using its derivative, like I do for the vertical angle, if that can, lift some restriction from this geometry that I'm using. I think what it would do is lift the restriction that things have to be moving directly toward PSP, because that's what would cause a changing horizontal angle. So I think that would be an interesting intermediate case to explore, which I think would not actually speak to radial motion from the sun. Another maybe sort of intermediate or related case would be what Kenny's been working on, and I'll just call that out. They're working on a similar related technique using the motion of features through the imaging plane and the motion of PSP to infer positions of ray-like structures as they pass above or below PSP. So that's kind of more tomography related, but also exploiting the, the relationship between its position and PSP's motion. Kenny, do you have a poster here? Okay, well, somewhere else Kenny will have a poster or a talk, and you should see it.
Okay, a couple of questions for Cynthia. Start with Sarah.
Yeah, Cynthia, have you considered applying your analysis to synthetic data like we've been seeing to compare your 3D trajectories to ground truth simulation knowledge?
No, but I think that would be a very interesting idea to continue with this kind of analysis technique. Yeah, absolutely. Yeah.
Yeah, and the SOC data that they've now put forward is really nice because I think we're really trying to get people to start analyzing using the SOC products that they told us that are available through the GitHub and through the various tools, and because then you'll have codes all set up and ready to use Punch right out of the gate to do your analysis.
Okay, Craig?
All right, let's see. So great analysis using, I guess, basically stereoscopy, right? Where you're looking at 2 different angles. Have you thought about generalizing that to use the Punch PB over B data?
Yeah, I think this is going to be absolutely the next step. When I started looking about the technique or about Punch mission, and absolutely I think put in my mind that I should explore with the same data, but with different calibration, like working with PBs and make the difference with the total brightness. So yeah, absolutely.
Okay, 3 questions for Alberto. Joan?
Yeah, hi, thank you. Very nice talk, Alberto. So LASCO uses a set of calibration stars, and I'm just wondering if METIS views any of those so you can do a cross-calibration on the photometry.
I suspect so. I really don't know the details. I just mentioned that Alexander Burteboy is taking care of that effort. So I've heard recently from Marco Romoli that they are doing a lot of progress. So I suspect, yeah, of course, there should be some comparison with stars, yeah.
And Sarah? Or Alberto or Robert?
Oh, yeah. Okay, these have been really wonderful. And now the question is with Punch. There's a couple differences. In some cases, you're using multi-point, and with Punch, we have a single point, although we do have the polarization information. We're also looking very far out, and I don't know to what extent people have done. I don't know if they've been able to do the kind of tomography you've been doing on heliospheric imaging because they don't have as broad a field of view, but with Punch you'll have it. So how do you think things are going to change in this bigger field of view using polarization in addition to the sun's rotation? Are there challenges you foresee? Are there things you think are the first things we should be doing with the tomography with Punch?
So for SRT, I don't think there's a particular problem. The main thing would be to have the full field of view, I mean all position angles. So that in principle should be not the problem. The big problem, of course, is separating the F from the K corona. So looking forward to those clean images, and yeah, we should totally try it, especially with the PV images, yeah. We tried something with Whisper, but based on simulations. With Whisper is a very different, I mean, we know we could do in principle those large elongations, but the field of view Whisper is for us too restrictive. That won't be the case with Punch, so yeah.
Okay. Sorry, yeah.
Will I also add to it? Yeah. Yeah, I think in terms of challenges, I would say definitely like what we can expect in terms of signal to noise out there gets more challenging to extract the actual information. So that could be something that's challenging. But I would say like, especially since you're also saying like we have one viewpoint then in the end, right? So this makes tomography methods way more challenging to have like only one viewpoint. Like my hope, or like what I see as a challenge and as an opportunity at the same time, is basically to also couple it with like the intersection of the other instruments and use more like a physics-based approach potentially to like propagate what we see like to better constrain basically what we later observe further out to get like a limited solution space. So I think that would be a great perspective there.
I have a quick related question. Sorry. I haven't seen any use in your work, either of you, on using solar high data. Have you thought about that, and is there a problem with using that in your for tomography? I know, of course, it's in different orbits and so forth. So.
Sorry, I missed what you said.
Solar high data.
Oh.
Compared to Whisper, you're using Whisper, but what about solar high?
Yeah. Another limitation.
Solo high. Sorry.
Another limitation will be, of course, one is the separation of the F corona. The other is signal to noise. So we haven't tried that, yeah.
Okay. Let's see. Craig, did you have one last one on Alberto?
So Alberto, what really jumped to my mind, you were talking about the differences between METIS and the C2 inversions. And you're absolutely right that the tomography helps remove some of the instrumental effects or point of view effects. But couldn't the sun have evolved between the rotations that you used for the two different instruments? Maybe that's part of the problem that you're seeing.
Sure, but that cannot explain the systematic difference. So what we did is simultaneous reconstructions, right? So the sequences of METIS data and the sequences of C2 data are simultaneous from very different points of view. That explains the spread you see in the histograms, but not the systematic shift. Yeah. That should be purely about, it could be partly because of differences in the point of view, but we tested that, and that's not the case. So it's really mostly about calibration here, yeah.
Okay, and last question, Sam to Sam.
Hi, Sam. So in addition to the position of your blob, you can also get a physical size and apparent brightness. So I was wondering if you've tried to predict like how it would look from other images, and I could think of Solar High as being an example which could be feasibly close enough to actually see it at the same time. So if you tried to like, or have you thought about that as a way to like get a second cut at it?
Yeah, that's a good question. I was kind of thinking about that with Marcus's question earlier, like if we could embed these parcels in a realistic punch foreground and background and see how visible they are. The most difficult part would be getting like a brightness or a density. The videos I was showing were Guillermo's LW processed images, which give relative values, so I'd have to see if that can be converted back to something photometric, or else re-identify the features in the photometric L3s. But if that's possible, you're right, I can get the actual size of it as well, and then, yeah, we could find out.
Okay, well, let's thank the speakers again. And now we have coffee and posters, and Sarah has a comment.
Yeah, I have one comment. Could people who are organizing AGU sessions that are relevant to people here at this meeting in Punch, could they come and let me know? And we're going to put up a slide with those probably right after lunch, and just to advertise.
daughters to that, and I graduated, and then we're back.
You lose that one. I like the Totoro sticker thing.
Oh, yeah. Put my daughter's Totoro. Howl's Moving Castle. Yeah, it's just an amazing film.
Yeah, I think Spirited Away scarred my daughter.
Every fall we go to it's pretty fun. Yeah, Princess Mononoke.
I know.
That's the movie that'll scar.
Yeah.
It's super fun.
Okay, we're going to get started with our next session. It's on, and our first speaker is an invited speaker, Erika Palamario from Predictive Science, and she's her talk title is Investigating the 3D Morphology and Kinematics of CMEs via Multipoint White Light Imagery. And I'm going to let her take it over.
Sorry for my coffee there, well prepared. Hello everybody, and thanks for having me here. So yeah, thanks for the introduction. We're going to talk about the 3D morphology of CMEs. This work? Yes. Why is this vibrating? Oh, whatever. So we will start with a small introduction about the hard life of a CME chaser, which is that we have a major issue in coronal mass ejection forecasts because most input parameters for prediction models are derived from remote sensing observations, but those are not well constrained and they are associated with large uncertainties. We observe CMEs in white light with coronagraphs and wide-angle heliospheric imagers, and usually we apply forward modeling techniques. Here we have examples from the most popular one, which is the graduated cylindrical shell, or GCS model. So we apply these forward modeling techniques to this data to derive the NCME morphology and kinematics. And we use these inputs as input parameters for CME propagation models. But we have two main problems, which are that forward modeling techniques have to assume a parameterized CME shape, and obviously does not always work well when a CME has itself an appearance that is not well constrained by these parameterized shapes. And the but number two is that we don't have enough viewpoints. At the moment, we usually get to see a CME from 2 or 3 viewpoints. So even our results are not well constrained. So for once in my life, instead of just complaining, we decided to take the matter in our hand, and we put together an EC team to play with fake CMEs. So this EC team was selected last year. Our first meeting was in December 2023. So these are going to be very preliminary results obtained over the last 6 months or so. Shout out to Mike and Kenny, who are here in this room. And also I think that there are some team members listening online. And you will hear the word fake a lot in this throughout this talk, because it kind of became our motto that also appeared in the EC. Oh, the quality here is not great. In the EC guest book, where we wrote real people, fake data, no Photoshop. So let's take a look at the overview of our research questions and project. So we simulated Sun-to-1 AU CMEs with 3D MHD modeling using mask or HEL. And we put synthetic spacecraft throughout the simulation domain. And of course, since we are using model CMEs, we have no limitations, and the heliosphere is our oyster. And our main questions are, do more observers make a difference when evaluating CMEs in 3D with forward modeling? And can we retrieve the irregular shape of CMEs with inverse modeling? And with how many spacecraft do we need to get a proper reconstruction? But also, importantly, does all of this make a difference in actual space weather applications? Because CME models themselves, the propagation models, assume simplified shapes themselves. So if we have reconstructed something that is extremely irregular, we still have to re-regularize for genetic inputs for propagation models. So anyways, in our first effort, we have decided to begin using 2 spacecraft configurations that we can see here. All the spacecraft are at 1 AU for now, and these 2 configurations, we have called them the 3 Ls plus polar, where we have a synthetic spacecraft at L1, L4, L5, and then a polar viewer. And the solar ring, where we have 6 spacecraft at 1 AU, separated in pairs by 20 degrees. And those are configurations that they're not attained as of yet, but they are still technologically realistic and economically feasible. So we are not into the sci-fi regime yet. So in terms of simulating the CMEs, we're using, as I said, the mass code and the CORHEL, Coronal Heliospheric Model. This model has 2 domains, the core domain that is usually between 1 and 30 solar radii, and the HAL domain usually between 28 and 230 solar radii. We're modeling CMEs from their eruption at the sun with a Fluxrop description. Here we're using the regularized Biot-Savart law Fluxrop model. And we have modeled 3 CMEs inspired by real events, meaning that we've used an actual eruption that actually existed, but we have made absolutely 0 attempts in matching the real observations because it's not the point of our work. And we generated a slow CME, about 800 kilometers per second, a medium one, 1500, and a fast CME, which was about 2,500 kilometers per second. Here it's an example of the fast CME in the core and HAL domains. So after we have modeled the CME, we obviously have to produce synthetic white light images from them. So by solving a couple of equations from Howard and Tapp in 2009, we have obtained both the total and polarized brightness for all of these observers. Obviously, yeah, there is line of sight integration involved. And our initial work has focused on coronagraph-like synthetic images, such as this one, these ones that we are seeing here for the medium CME example. And so, yeah, these synthetic views have a field of view of about 30 solar radii, so we have nicknamed it fake C3, but fake NIFI also works. And fake heliospheric imagers will be the main focus of our second DC meeting that is in October 2024, but watch out at the end of this talk for a sneak peek. So the inverse modeling technique that we have used is discrete tomography. Tomography in general is an inversion problem, and the particular technique that we are using is the discrete one, where we are defining a grid over the heliosphere, or anyway the field of view of an instrument, where the line of sight integral can be approximated as a sum. And the discrete, it is expected that this method needs at least 4 vantage points to permit CME reconstructions. And the pipeline, I don't know why in the equation my dot product became a period, but okay. We have to solve this inverse equation, which is y given by h dot product with x, where y is the array that contains our data, x is our unknown, and h is a physical operator. So the pipeline is to first process images to reveal CME structure. We're resampling data over a grid, then calculate this h operator, and then solve for x. So first of all, how do these CMEs and observers do with forward modeling? So we have reconstructed these CMEs also with forward modeling, because in our next attempts, as I said, we also want to see what the differences are between tomography inverse and forward modeling in then applying inputs to space weather forecasting models. So for example, here we have 3 observers, L1, L4, and L5, but adding the polar view, then which is this one, it's already constraining our observations a lot. So I'm not going through the forward modeling a lot, but the first impressions was that we found that 3 versus 6 spacecraft on the ring, so all on the same plane, does not make much of a difference in fitting, but adding the polar view to the 3 L points does. And also we can notice already from here that the CME shape that we're modeling is not much GCS friendly. So we can now go for I hope that it's more visible there than here. We can go with our preliminary results with the discrete tomography. Here on the left, we have the images from all of our synthetic observers that have been rebinned in this grid that is 128 by 128 for applying the tomography. And then from all of these spacecraft, we have, we are all using polarized brightness. So in all of these lines, we have simulation, so the real data, the solution, so what has been reconstructed, and then the residual. And we have it for the radiance on the red rows and on the degree of polarization that is the blue rows. But when we go and reconstruct things in 3D, so these are our preliminary, our results that are looking at the effect on the number of spacecraft. So we're also interested in seeing more. We became interested in seeing the effect with using more of these two configurations. So with the 3 spacecraft, we're actually using only the 3 L1, L4, and L5 points. And with the 7 spacecraft, we added to the ring configuration of the 6 spacecraft also the polar view. So clearly the number of spacecraft, and we see here results with the total brightness on the left and polarized brightness on the right. No need to look between TB and PB at the moment because that will be in the next slide. So you can just look at them separately. And the number of, it's clear that the number of spacecraft employed for the inversion has a big effect on the reconstructed 3D structure, but also on the noise level. We can see with 3 and 4 spacecraft, we have a lot of more noisy points all around. And now if we combine these views by just comparing total versus polarized brightness, we found a result that is extremely interesting. It was extremely interesting and unexpected to us, which is that employing total versus polarized brightness has a much larger effect with decreasing number of spacecraft. So if we look at the bottom right plot, which is using 7 spacecraft, we don't see an immense difference between PB and TB. But if we, for example, look at the top left, which is, or also top right, with 3 and 4 spacecraft, we see an immense difference between total brightness and polarized brightness, which clearly means that the less spacecraft we have, the more we should have polarizers to get more accurate results. And yet, it's an important implication in real life because we are quite unlikely to get something like 10 imagers out there in the near future at the same time. So yeah, future instrumentation should definitely carry polarizers to enhance our inverse reconstruction capability. So good job, Punch. And yeah, so at this point, like complicated things that we're working on are, for example, how to get a shape that we can then adapt to CME propagation models from these much irregular shapes that we're getting from the tomography. So we will look at the effects in space weather forecasting from these results. But now it's time for the sneak peek of a fake HI extravaganza. So we can look at the 3Ls plus polar configuration. We're going to reverse it because for beauty of visual purposes, it's gonna look better, trust me. So if we, for example, and I'm gonna point out that proposed or actual missions that are gonna happen. So from here we've imaged these CMEs with a pretty wide fake HI field of view. It starts from 4 degrees, so the inner field of view of stereo, HI1, and then we have made this field of view that is 60 degrees large, so it's pretty wide. So this is what a spacecraft from L5 would see of a CME, but then we can add L4, and here there are some papers of proposed missions to L4. Then from L1, we have put 2 fake HIs from both sides, looking at both sides of the sun, so we call them L1 West and L1 East. Okay, I know that it's not the Punch field of view, but it's still looking at both sides of the sun like Punch will. And then From the polar view, we have, for example, something like Solaris, super interesting. We are going to see the CME from above, and then afterwards we can actually see the Parker spiral. So I now really want a polar heliospheric imager to look directly at the Parker spiral, which would be super cool. But then, yes, I got invited for this talk, and I was like, well, I can't not make a fake punch movie, so here it is. So this is what that CME that we just saw would look in a fake punch field of view. And do we have a pointer here? Where do I point? Oh, do you see it there? Yes. And actually, after the CME, we can really see, even here, the Parker spiral. So this field line will be curving. And it's very interesting that if we look at the NIFI field of view only, which is the C3 one, we still see the structures being all radial, like we do actually in C3. So I'm really interested in seeing if with real punch data, once it's launched, we can actually image the Parker spiral. So our future plans include tomography analysis using the fake HI field of view, which is going to be pretty complicated, actually interesting to look at, because a big difference between, this is the last slide, so we're doing great. There is going to be a big difference compared to coronagraphs, because in a coronagraph field of view, we have the entire CME in the field of view. Instead, in HI fields of view, we're going to see only parts of the CME. So I'm really interested in seeing how the tomography reconstructions will work. And then we are, well, this is half a lie because the scenario is being created already. Of a possible realistic future scenario, which is using actual ephemeris data for future orbits of the current spacecraft that we have, and generate analyze synthetic imagery for stereo A, Parker, Solar Orbiter, and Punch. I've already created all the images for this, for a encounter of this CME in the future. So if you want to look, please feel free to ask to see the movies, and they're going to be presented next week at the WISPER Consortium meeting. And yes, and that's it. Thank you so much.
Okay, our next speaker, Yulia Shifu at George August University of Göttingen, is going to talk about low polarized emission from the core of a coronal mass ejection.
Hello, everyone. Thank you for having me here. I am Yulia Kifu, yes, from the Institute of Astrophysics and Geophysics at the University of Göttingen. And today I'll present you some analysis we did using polarization on CME. Right. Yes, so the analysis was already published some time ago already. The first author is Marilena Mierle. So to start with the observations of the CME event, it happened in 2007, right shortly after the stereo was launched. We used coronagraph 1 images on board stereo A and B, when B was still there. The coronagraph 1 has this field of view, and at that time the separation angle was 28 degrees, and the CME was triggered by a prominence, and this will be important later. The coronagraph images are recording white light images in this waveband of 22 nanometers, and it is centered in this H alpha. This is also important. And recordings of the stereo so they are taking 3 polarized images at this degree, 0, 120, 240. And based on these polarized images, they build polarized brightness images, total brightness, like we see here. And based on this, we can also derive the unpolarized brightness. So to this images from coronagraph for polarized and unpolarized and total brightness. We applied the usual calibration with SekiPrep. Then we subtract the background for polarized and total brightness, and then we apply the median filter to increase the signal-to-noise ratio. And after we did that, here you see two images from stereo A and B, and it is plotted on a logarithmic scale, and we plot the polarized to unpolarized brightness, like we derived it before. And here we can see, so this is part of the CME, and with red, it's actually the core of the CME. So we think it's the prominence material which goes out into the corona. And it has remarkable low polarized values. So we also apply the polarization ratio method, which is based on the polarization properties of the Thomson scattering. It was developed by Moran and Davila in 2004. It is suitable for 3D reconstruction of CMEs. And yeah, we said this core takes polarized images. And the degree of polarization is a function of the scattering angle, psi, and also of this angle. And actually, it is based on the Billings formulas, which you have seen earlier in Robert's talk. Yeah. And, but this polarization ratio method has, here, has a dependence of the distance from the plane of sky, and it's also having ambiguity of 180 degrees. So when the 3D reconstruction is happening, you don't know if it's in front or behind of the plane of the sky. So after we applied the polarization ratio method, we could obtain the 3D position of each pixel, and we derived this cloud by having, so green dots are the scatterer location from core 1, A, from stereo A, and the blue dots from stereo B. And by using the two spacecraft, we combined them so we could, let's say, solve, in some sense, the forward-backward symmetry of the Thomson scattering. Nevertheless, this reconstruction showed us that there is a strange location of the scatterers, so we can think that Thomson scattering would not apply in these parts. So we were thinking, and it's also like co-spatial in some sense with the core of the CME. So we were wondering what is the real location of the CME core in this case, because it shouldn't be so far away from the plane of sky. For this, we applied a stereoscopic reconstruction method, which is called multi-view B-spline stereoscopic reconstruction. It was initially developed by Bernd Intester and MPS, he was my supervisor, and I was expanding it. So it retrieves the 3D information of curve-like object. It can use 2 or 3 view direction. It is based on the stereoscopic reconstruction technique, and B-splines function are used during the reconstruction in order to obtain the smooth curves. Now, you've seen a little bit the epipolar geometry in Cynthia's talk. So in this case, the epipolar geometry is the based geometry for a stereoscopic reconstruction. And here with blue, we have the stereo baseline between the two stereo views, and the plane also with blue, and the angle between the two observers. And you also have the epipolar plane and line. What you also need to have and to do, it is to identify and match the object which you want to reconstruct in the 2 or 3 views, which is very difficult from my point of view. And the third part, it is the reconstruction itself, which is, in this case, an iterative process. So the reconstruction minimizes dysfunctional. So it minimizes the projection of this 3D curve in each image. So the projection of the curve and the tie points which you initially choose. And this term is only true for the smoothing of the curve. Now, when we combine the polarization ratio method and the stereoscopic method, here we have in stereo, for stereo A and B, again, the images which we've seen before with the red patch for the low polarization, but with the green line, we have the projection of the 3D curve which we obtain based on the stereoscopy for each image. And now if we add this 3D curve into the cloud, we can see that the location of the core of the CME, it is here at the base of these horns, practically. Right, so now what is the cause of these horns, as we called it? Some ideas would be that it can be due to scattering on the dust particle, or the scattering from enhanced plasma far away from the plane of the sky, or it can also be, as it was mentioned in literature, the resonance scattering from the H-alpha atoms. For the first two, we can eliminate because the scattering for the dust particle, we can eliminate because we were subtracting the background. And this would take all this dust particle. Then the second point we can also eliminate because we were applying the stereoscopic reconstruction, so we could see the real location of the core of the CME. So we remain with only the last explanation. And now from the observations from the coronagraph, we could estimate the ratio of polarized to total brightness. And this ratio, we call it here our Thomson, like in the Thomson area, let's say, it's like 0.5. And the ratio for the patch is 0.1. We can also observe that in the total brightness images, the total brightness patch is 10 times the total brightness in the Thomson outside of the patch, let's say. Now, if we consider, like in this sketch, that the contribution on the image of the patch, it is due to this, let's say, cloud where we have brightness from the Thomson scattering, brightness from the H-alpha, and outside only brightness from the Thomson scattering. We can consider these relations. And now if we assume that the duration of Thomson scattering outside of the patch is the same with the inside of the patch, we will reach with this relation. So the polarization ratio of the H-alpha radiation cannot exceed 1/18. This is a very low intrinsic value, but it agrees with observations from low polarization of H-alpha taken from the chromosphere by Gandorfer. And also the contribution of H-alpha to the radiation from the patch is at least 8 times the Thomson scatter from the patch. Now, I just arrived to summary and conclusion. So we applied the polarization ratio method to a CME in 2007. From the 3D reconstruction of the CME cloud, we identified unusual location of the CME core. Then we applied the stereoscopy to identify what is actually the real location. And then based on the analysis, the conclusion is that the major part of the CME core emission in H-alpha radiation is like 85%, and only a small fraction, it is a Thomson scatter light. Thank you very much. Punch.
Well, our next speaker is Anna. I don't see Anna. Have an E. Okay. Go to Christopher. Okay. All right. Oh, no, here she is. All right, yay, Anna. Okay, we're going to go with Anna. So our next speaker is Anna Malinushenko from the High Altitude Observatory, UCAR. And she has an invited talk on the analysis of synthetic flux rope in ICME simulation using unpolarized and polarized white light signal and in situ data.
Okay. Thank you very much.
Anna, you'll need to join the Zoom session to present from your laptop.
One moment, I have everything. I do hope that what I have to show would be worth a little bit of a delay. Okay, I'm in. Sorry? I am here.
Yep, and you can just share your screen.
Awesome. So, the title of the talk is The Analysis of Synthetic Flux Ropes in Punch-like Simulations. And first off, here is the agenda. And the agenda is pretty brief. First, I will go over the open dataset CME Challenge version 2.0. Then I will very, very briefly touch on touch the basics of Thomson scattering because it's kind of important for the next topic, which is the density along the line of sight. So the CME challenge is a set of synthetic punch-like observations. It's open, it's ready to use. It is based on Gamera simulations that Elena Pravornikova had run, and it has WSA background and Gibson and low flux rope. And it contains both total and polarized brightness. It has punch-like field of view, and it has punch-like projection. And here's the link, and you can also email me for the link, and it will also be available from the Punch website. So in this data set, there are 4 CMEs with different properties, including different sizes, different launch locations, fast wind, slow wind, and so on, different velocities. One CME is a reference, so the parameters are published over there in the open on the website. And 3 others are for validation. And again, this is not a contest, this is not a competition, this is to help you validate your reconstruction techniques. So if you reconstruct your validation techniques, you ask me for the correct answer, and the correct answer is matching your reconstruction, then it is a very, very strong confirmation of the method. So that is why it's there. So there are 2 types of data products there. And one is the challenge itself. So an observer is on the solar equator, and there are several different viewing angles on the CME. And the second data set is the 4Pi data set. So it's only available for one data set, but the observer can be at a whole variety of different angles. And this is what the website looks like. As you see, there is a bunch of data published on the reference CME, and there are links to fits for all synthetic CMEs. And then there is the 4Pi data set, and again there is the link to it. So you can change longitude, latitude, select the viewing angle, and then download the corresponding data. So that's kind of the idea. Then there are, well, we know a whole lot of different properties about those synthetic data. So we know the simulation parameters because we launched the CME using them. So size, launch location, and so on and so forth. Then there are ground truth data, and here is one example of what I mean by that. Given that there is a deceleration of the CME in the solar wind,
the launch velocity is not necessarily the same as the velocity of the actual transient. So we do isolate the actual transient, and we do measure the front and the center of mass of the actual transient. And this is kind of what it looks like. And from that, we can derive mass, acceleration, deceleration, trajectory, and so on and so forth. So there are other parameters, such as in situ data, that can be calculated to match your reconstruction technique. So we do have all MHD variables in the full volume in time. So let me know, and we can work and make a different kind of CME properties known. So now I need to talk very, very quickly about projections, and I will not spend too much on that. I will just show a few images, and they will be in my talk that is uploaded online. So Punch has a very wide field of view. So if we take a slice on the central plane on the solar equator, this is the view from above on that plane, on the density. Please note that in all of those images, there is a vignette applied for display purposes. So the Punch field of view is about 90 degrees. So it is quite a lot, and the projection is slightly unusual for heliospheric observation, so it's pretty much a fish eye. And by that I mean in near-sun data, we are more used to mnemonic projection like SDO data, and in that projection, the pixels are equally spaced in the plane of the sky image. And the plane of the sky is a teeny tiny portion of the celestial sphere, which kind of works in the near-sun regime. Far away from the sun, what we do is azimuthal equidistant projection, or at least that is the chosen projection for Punch, and the lines of sight are spaced by the constant elongation angle. And this is just something to keep in mind. This is so the field of view of Punch is shown is confined between those two lines of sight, and the observer is at the bottom center in this density slice. Now, what do we do with the lines of sight? And again, that will be very, very quick, but I need to show it because of what I'm going to show next. So there is some mass, and we observe the mass in scattered light, and there is the scattering angle. So if the mass is at a point P and the observer is right over here, there is line of sight, and then there is a scattering angle chi. What we observe would depend on that angle. So here are some useful papers. I'm not going to go into those equations, except I'm going to say that for both total and polarized brightness, those are line of sight integrals, and they contain density, and they contain some functions of the location of the point that scatters, and they contain some functions of the scattering angle. And those functions are different for total and polarized brightness. And the scattering angle is 90 degrees at the Thomson sphere, which is also, for each line of sight, is the point of closest approach to the sun. When we integrate that along the line of sight, this is what that looks like. For the observer, so again, this is the equatorial slice. We're looking from above, and the observer is at the bottom center of the frame. So this is what those two multipliers look like, and again, a vignette, because otherwise everything drops very, very quickly with distance from the sun. So we have to multiply the density by that, and then take a line of sight integral. So when we do that, say for polarized brightness, this is what we get. So the image on the left is actual density. This is what we want. The image on the right is what we have because of Thomson scattering. That is kind of important because, for example, if you take a look at this CIR over here, this portion of the CIR appears brighter because it's closer to the Thomson sphere. And this kind of effects we need to keep in mind when we do reconstructions. The good thing about that is that since total and polarized brightness depend on scattering angle in a different way, from the ratio we can derive the position, the scattering angle. And well, it only works for a compact mass. It works kind of in a way that Kurt showed yesterday. Now, we do not have a compact mass, not in general, so we have a distributed mass. And what do we do? So here's an example. Now, this image on the left is again a density slice. I highlighted one line of sight. So the observer is at the bottom center. The highlighted line of sight is in yellow. And this is how mass is distributed along this line of sight. The density is distributed along this line of sight. Now, is it true that from the ratio of total and polarized brightness we get the center of mass? Well, we can calculate center of mass over here. And the center of mass is somewhere in this circle. So actually, these white diamonds show centers of mass for various lines of sight. Actually, when I look at this picture, I think of a saying. So probably every single language has a saying for remembering the colors of the rainbow. The Russian one translates as, every hunter wants to know where sits the pheasant. So in this image, the hunter is right here, and the pheasant is right here, and we want to know where it sits. So I showed what it looks like for just one instance in time, for the observer in just one position. What I can do here, I froze the time, and I'm rotating the observer. I'm looking at the whole situation from different angles. And the image on the left shows the entire simulation volume. In the image on the right, since we've done the ground truth calculations, we know where the CME is. I zeroed out everything that is not CME in the volume. So this is not a background subtraction like a Thomson scattering sort of subtraction. This is like physically, I rendered the volume in which there is nothing but the CME. This is how the locations of the pheasants look like on different lines of sight. And the question is, does it make sense? And I actually think that it kind of does make sense. And here is why. So first off, what should it be? If we were just taking one step at a time. So imagine that there is no structure, there's no Parker spiral, no CIRs. There is just uniform density drop-off. And imagine that we integrate from -infinity to +infinity. In this situation, the center of mass will be in the point of closest approach to the sun, so on the Thomson sphere. Since we have an observer that's looking forward, we do not integrate from -infinity. We integrate from us to +infinity, and that kind of pushes the center of mass a bit away from the Thomson sphere. On the other hand, Gamera does not go to +infinity either. So we have to stop the integration when the domain stops. And that kind of pushes the Thomson sphere towards the observer. So between those two effects, we kind of expect the Thomson sphere plus or minus. And then there is structure. And this is kind of what we see here. So it does make sense. Now, I'm going to show preliminary results, but the determination of this pheasant over here, we can in principle synthesize punch data, right? And this is what we did, and this is one data set from the challenge data. So I took total and polarized brightness, and I calculated the ratio. And the ratio gives us two solutions plus. So for each line of sight, we get the distance from the Thomson sphere, but we don't know in which direction. So for each line of sight, we have two solutions. And this is what I'm showing over here. So the true centers of mass are again in the true centers of mass are again in white dots, just like before. Sorry. And well, the movie is not playing, but that is kind of what we see. And the two other solutions are in dots, in colored dots of different color. Again, for the situation where we have everything and for the situation where we have CME alone. Since this movie is not playing, I'm going to cheat and do this. I'm going to cheat and play it manually. So if we rotate, if we look at the structure from different angles, This is how, and these are preliminary results, this is how the ratio of total and polarized brightness compares to the position on the line of sight. And that is actually my last slide, and thank you very much.
Okay, we have our last speaker for this session, Christopher Rura, and from Catholic University of America and Goddard, and validating image-based methods for improving coronal magnetic field models.
Hi, everyone. My name is Chris Herrera. I'm a PhD candidate at the Catholic University of America. And today I'm going to be presenting on my research for validating image-based methods for improving coronal magnetic field models. So I want to start out with just looking over the punch science goal that I think is the most relevant to my group's project. And there are two main points that I want to highlight with what we do. So as many people in the room probably know, it's very hard to get a direct measurement of the orientation of the coronal magnetic field. And we have to rely on extrapolations to do this. And there's a lack of ground truth to validate these extrapolations against. So what my group looks to do is we look to model global structures using image-based segmentation. And we look for structures that correlate to the formation of the solar wind. And what I specifically do is I look to validate these structures against the ground truth in order to try to validate this segmentation. And I'm going to just briefly go over this validation framework, but essentially what I do, I look for chronograph observations around the date of the 2017 solar eclipse. Do I have a pointer? Oh, I do have a pointer. Okay. So yeah, up in the left-hand corner. And I use forward along with MHD model provided by Predictive Science to generate synthetic polarized brightness observations using plasma density parameters of this MHD model. And I retain the magnetic field parameters generated from this model. And then I use a code generated from my advisor called Craft, which basically traces quasi-radial features in white light observations that correlate to open field regions of the corona. And since I have the orientation of the model field and the orientation of the features given from Craft, I can directly compare it to each other and be able to validate this that way. And the ground truth that we're comparing against in this case is Predictive Science's mass model. And there's a couple reasons why we really like this model, but two of the main ones are, first of all, it's a three-dimensional model, which allows us to rotate it from any perspective. So that means that we can look on different observations, different observatories. And the second reason is that it is able to model the interaction between the plasma and the magnetic field and the corona because it has a complete energy equation. So we want our ground truth to be able to accurately model this, which MASS does a really good job in doing. In the interest of time, I'm going to briefly go over Craft, which is my advisor's code. Essentially how it works is it takes a polarized brightness white light observation. It goes through two orders of azimuthal detrending, and we're essentially left with a second order difference image that uses a percentile-based thresholding system, and we are able to then extrapolate these segmentations as polynomials in radial coordinates. And these polynomials then give us the orientation of these features at every single pixel. Let me move on to the actual data that we're using. So in this talk, I'm going to be going over Core 1 data. And we look at the polarized brightness because it reveals the K corona illuminated by Thomson scattering. And with this framework, we're actually able to analyze multiple methods of image processing. One of the methods that we use is an image stacking algorithm, and then we average this over about 30 minutes. We also use a bandpass filtering method that was generated by Nadia Elzadi, and it's really good at being able to enhance transients and reduce noise. And then after this, we segment the quasi-radial features using Craft. So looking back, just in a broad term, we have the features from Craft, and then we have our ground truth solution given to us by the mass model. And the ground truth solution that we're using in this case is the plane of sky magnetic field. And because we have the orientation of every feature, and we're able to retain the orientation of the plane of sky magnetic field from mass, we're able to create these profiles of the angular error between the two for different populations that I'll get into a little later. And this allows us to be able to actually see how well the features that are segmented are fitting the ground truth solution, or what we assume the ground truth solution to be in this case. And let me go through a couple of contributions of error that are a little obvious just from the data itself. So first of all, Craft sometimes has segmentation errors. It is really good at being able to segment models, but sometimes the actual data has noise in it. So Craft is good at filtering out most of these segments, but there are a few that still kind of escape inwards. So that is one contribution. Another one is that this is in 2017, so Core 1 sometimes has these instrument artifacts that are prevalent in the images. But actually one of the biggest sources of errors is Craft tracing what it thinks to be open field regions that the mass model tells us are closed field regions. And this gives us these really big spikes of error because it's essentially perpendicular to what the model tells us the orientations should be at that spot. So let me get into the actual comparison populations that I use in this analysis. So I start with the mass central plane of sky electron density. And again, we're comparing all of this to the central magnetic field, central plane of sky magnetic field orientation. So this is essentially a one-to-one comparison of the mass central electron density to its own magnetic field. My second population is I take the mass line of sight integrated electron density and I compare it to that same magnetic field. So this is just integrating the line of sight along the observer. I then use forward to generate polarized brightness observations, which is essentially that line of sight integrated electron density with adding artificial scattering. And then finally, I use the actual Core 1 polarized brightness to compare to that expected magnetic field as well. And there's a reason why we chose these different populations. I'll get into that a little bit later, but this essentially allows us to plot this by, I forgot to mention this as well. So we take 6 observations around around the 60-degree rotation of the Carrington rotation correlating to the 2017 solar eclipse. So we want to get a 360-degree view of the sun. And this plot's a little bit busy, so I'm going to kind of give you a little bit of help. So the 3 warm colors you see here are all going to be your model-to-model comparisons. That's going to be your electron density to the central magnetic field, the line of sight integrated electron density to the central magnetic field, and then the forward polarized brightness to that. And then the blue is going to be the actual data compared to that magnetic field. And we can go step by step on one of these slices. So we see that the central electron density in this case is performing the best, and then we bump up to the line of sight integrated electron density, the forward polarized brightness, and the Core 1 polarized brightness. And for the most part, we expect that the order that you see in this example is the order that it should be. That your ideal one-to-one comparison should be giving you the best results. When you bump up to the next most complex population, it should be giving you a little bit more error. When you get up to adding artificial scattering, it should be giving you a little bit more error. And then the actual data is going to give you the most error. and we can actually aggregate this data and then take a look at some of the trends. And in this case, we see that that ideal 1-to-1 comparison is performing the best. And then if we bump up to the line of sight integrated electron density, to me what this is telling us is this could be a measurement of the projection of that three-dimensional volume onto the plane of sky, the error that you get from that. You bump up again, this could tell you the error that you're getting from that scattering and different methods happening in forward. And then everything else that happens is going to happen from the third population to the fourth population. And an example of this could be that even though we're using mass as ground truth, the photospheric extrapolations that was used to feed that model may not have been entirely accurate, or image artifacts like I showed before. But this essentially allows us to pick populations based on the assumptions that we choose and actually measure those assumptions and get a quantitative value for them. Something else I'm able to do is I can aggregate this data again and I can plot them on a histogram. And I can then take these histograms and I can use a Gaussian kernel density estimation to get probability densities for each of them. And what I can then do is I can feed it into a similarity index called the Jensen-Shannon divergence, which basically all you need to know about it is that it compares the shape of two histograms, and if they're exactly similar, it's going to be very close to 0. So that's why on the diagonals here you see a perfect 0. And if they're anti-similar, they're going to be close to 1. And if you have a random population, it'll probably be close to 1/2. And for this, we see that most of this is very close to 0, but you can pick out trends on certain populations that are more similar to each other in terms of their shape of probability distributions than other populations. Another nice thing about this statistic, you may notice from this heat map here, is that it's symmetric. So even though we're assuming the MHD model is our ground truth solution, this statistic does not care what you think is the right solution. If you switch up your P and Q distribution, you're still going to get the same answer. And finally, I'm going to go through some of the preliminary statistics of this aggregated data. So again, we see that the mass plane of sky we see the mass plane of sky electron density is performing the best to its own plane of sky magnetic field. That's what we expected. We bump up to the line of sight integrated electron density. It's performing a little worse, but it's still within the same ballpark. The forward polarized brightness is also within the same ballpark of all this. And the really interesting thing is that Core 1 is actually doing very similar to a lot of this. And we can see this because we can throw in the RAM data set in there. And, RAM data set around 45-degree mean. The first population is really the best answer you're ever going to get, because there are reasons why you're never going to get a perfect extrapolation of the orientation of the coronal magnetic field. But for the actual Core 1 segmentations, we're a lot closer to that ideal answer than we are to complete nonsense. So I'm running out of time, so I'm just going to go over a couple of my conclusions. We were able to provide a quantifiable ground truth validation against a mass model for these coronal segmentations. We were able to create metrics to correlate these white light features to an actual model magnetic field. And we were able to diagnose and quantify error between several model populations. Like I said before, the central electron density, line of sight, integrated electron density, forward polarized brightness, and then the Core 1 polarized brightness. But what is really interesting about this framework is we can actually adapt this to use it for punch or other data sources. We're actually in the process of optimizing this for K-core right now. We can shove in other MHD simulations if we want to, and we can also even use other coronal feature tracers as well. So any of these can be swapped out, and the validation framework is still valid. And we were able to verify that these coronal segmentations is representative of simulated magnetic structure. And I think I'm out of time, so that is my talk. Thanks, everyone.
We could have our speakers come up, and then definitely help me figure out who's in the room and not. I think I'm going to start out with maybe some questions from people that haven't asked questions too much. I'm gonna wait till everybody gets up here. Okay, we have all 4 now of our speakers. So James Tappan had a question. Okay, thank you. It's a question for Erica. It says the shapes look closer to the bent shell of the TH model. Would it be feasible to use such shapes? That's what the question is. Yeah.
And I have to keep.
Yeah, you have to keep holding it down.
Yeah, so the TH model is the Tappan-Howard model, if someone didn't know. Yeah, I mean, we can use, definitely at least for these CMEs that have been modeled for this effort, like anything that has some kind of front flattening would be more successful than the GCS model that is very spherical. And I mean, yeah, we are open to fitting things with other models, definitely.
Okay. Okay, thank you. Gabriel had a question for Anna. Is Gabriel here? Okay.
He's online.
Okay. So I'll read it. It's a question for Anna. Could you expand on the implications of the final video comparing the discrepancy between the white dots, the actual center of mass, and the blue and orange dots, reconstructions based on PB/TB? The backside of the CME seemed poorly constrained. Was there better agreement for the Earth-facing CMEs?
Hmm?
The long one.
Yes, there was a better agreement for Earth-facing CMEs. And what are the implications? Well, we really need to understand what is it we're looking at, and perhaps some serious work on subtracting the background needs to be done.
Okay. Okay. Thank you. Now let me see some highly. People can also vote these up or down to help me out. So we'll go for a question from Craig for Lulia.
Super. Actually, this is something of a comment, actually, that I'm sure we'll see these kinds of events. That was a really cool analysis. I'm sure we'll see these kinds of events in Punch. Right, Alexis Riard and Tim Howard both tracked different prominences out into the heliospheric imaging field of view, right? So we ought to see this kind of stuff.
Yeah, this core of the CME, which were constructed from stereoscopy, it was at 1.6 solar radii, and Punch will be starting at, I forgot.
Yeah, we started about 5 or 6, but this type of feature has been seen way out in the high 2 field of view even.
Yeah, so probably we will see all of those.
Okay, we have a highly rated question from Joan.
A very nice talk. I was wondering if you tracked the polarization changes in the core with height. Did you see any changes with that, with height?
We did not track the CME in time. No, it was only one-time analysis.
I would expect the polarization to increase with height, frankly, as the material gets
Yeah,
ionized.
sure. I would also expect that the material will be fully ionized as it is diffuse, sure.
Okay, and all the remaining questions are from Craig and Sarah.
Good,
so
it
you
makes-
can hang out right there.
It makes- gotta be easy, I don't have to run around the room.
Okay, all right. So yeah, Sarah, go for a few of yours.
All right, actually, let me follow up first on the Annie one. Yeah, I think Craig has, and I'll hand it off to Craig so you don't get tired of listening to me. But nice visualization. I think you really illustrate an important point, which is that while polarization can be directly related to center of mass, and by the way, I think I can do this. Can I? So it pops to the top? Apparently not.
It's okay.
Yeah. So while you can show that, Kurt showed us how polarization ratio can be directly related to center of mass when you have like a Dirac delta function. But in fact, in the case of a spherically symmetric drop-off, as you mentioned, while the center of mass is the position of closest approach, the polarization ratio is utterly decoupled from the Thomson sphere and depends only on the radial drop-off of the density. And so my question for you is, how are we going to deal with this in Punch if we have a combination of three-dimensional, two-dimensional, one-dimensional things along our line of sight?
I wish I had an answer right now out of the box, but the truth is that we need to analyze the data quite a lot more to answer that.
Okay.
I do have a similar question, which is, wow, this is phenomenal. What do we do? One comment is we can do the same kinds of background subtraction people do with the EUV, right? Find the general brightness around the feature you're looking at, subtract it all around. But this is a stark reminder that even if Dan does his job or Marcus does his job right, and all we have is K in the data, there's still a lot of K that's not the thing you're looking at. And so the PB over B is fraught with peril. We all need to learn and work around that peril. Oh yeah, the Van der Hulst. That is not as perilous as it looked. Those ABCD coefficients look very complicated, and for Punch, it reduces to a much simpler solution. So I put a reference up there, but don't scare the people.
Oh, okay. Thank you for the reference. I don't know, that was not intended as scary, that was intended as just like some functions, but thank you for the better reference.
Okay.
And regarding more on the background subtraction, I wonder if the tomography can help us. Tomography of the time prior, if we knew the 3D structure of CIRs, for example, that would have helped.
Okay. All right, we have a late breaking question that's not from Craig or Sarah. So Nita had a question. Is it one I need?
Yes,
okay.
Maybe this was already discussed, but to Annie, is there a possibility of telling front side or far side origin of a CME with their synthesized images, and especially using polarization? And HAO CMEs are not always symmetric. Most of the time, they are asymmetric. So using this asymmetricity, being asymmetric, is there any possibility of telling the difference?
I think Craig can give a much better answer than I can.
So the morphology will be about the same, right? Because we're all familiar with that. The PB over B gives you the distance from the Thomson sphere. And so actually far side CMEs are farther from the Thomson surface. And so in some ways PB over B should work better. What we saw here is that that's not necessarily the case because these other background effects are more dominant. So this is just something that we're all going to have to be aware of and work with.
Hang on, let me bring you the mic.
There was a confusing paper published in 2002 by a guy called Mike Andrews, claiming that you can just look at the data and tell the front side or far side because the way scatterings are done in the solar corona or something like that. Please look at the solar physics paper. Maybe that's completely wrong, I don't know.
Okay, we have another question from Marcus. Is Marcus in the room? Okay, yeah, Marcus is getting the mic.
Yeah, so Erica and Anna, you both had awesome data sets, and so the SOC is a little jealous and wants to use it too. So would you be interested in working with us to add our metadata to your data so that way we could share it with the community and also just use it to make sure that our own code works right?
Absolutely, that's the reason why I came all the way to Boulder. Yes, and actually we should talk because I want to have discussions about like masking the data for making like properly making like the trefoil in my synthetic data. Yes.
Okay. Do we have any questions that were not on Slido? Okay. Okay. So back to Sarah and Craig.
Questions is all me. Oh boy, where to start? This is where my typos start getting a little weird, so you probably can't even understand them. I'm going to go to Yulia, which is third one. What I was supposed to say was those horns is the fact, I don't know where face came from, that the two stereos, something, I don't even know what I was trying to say, but I was trying to say that you those two horns, it looked like they were on two different sides of the plane of sky for one stereo versus the other stereo. Was that significant?
Yeah, they were in two different planes. So I put one cloud of the CME in front of the plane of sky for stereo A and B, whatever. And for the other stereo, I put it behind just to overplot them.
It was because I thought you were using a combination of the stereoscopy and the polarization to identify which of the polarization solutions were the correct ones, front versus back, or?
No, so the clouds are reconstructed based on the polarization ratio method, and only the red curve, it is reconstructed using stereoscopy. And the red curve was the core of the CME, just to see exactly the position, because from the cloud, you see those horns, which are not, they shouldn't be there.
Okay, cool. And this is published, right?
Yes, long time ago.
I thought so. Okay, so I'll go look. All right, so my next one, let's see. Chris, apologies, and if you said this or I missed it. So all of your comparisons are, you're looking at different kind of integrated density things, right? Density, integrated density, polarized brightness, and then the actual observations. But in each case, you're comparing to the plane of sky magnetic angle, is that correct?
Yeah, that's correct. In the past, I tried to compare to the line of sight integrated. In this analysis, I wanted to compare everything to the plane of sky magnetic field because one of the assumptions that we want to try to verify was that when we're actually segmenting these coronal features in polarized brightness images, we assume that they're going to lie within the plane of sky because of the it will be more polarized due to the electron scattering. So that's one of the assumptions we wanted to test with that.
But in the past, you tried some sort of line of sight weighted integral of the angle.
Yeah.
Because it's interesting because with the UComp observations, Zihao Yang has a paper, I think it's out, where he compared to the plane of sky magnitude. You're looking at a direction. And was able to show just that if you do the weighting, you can get a very nice comparison. Now, it doesn't address what you're trying to test, but it kind of shows that, how sensitive your line of sight integral is to the weighting.
Yeah, and that's another thing too, where that's even another thing you could change out with this framework, where you could actually change your right answer to, instead of the plane of sky magnetic field, let's do some sort of line of sight weight integration and see if it compares better or worse. And you'd be able to get a quantitative answer on that as well.
I think Gabriel's back.
Yeah. Gabriel had a question. So, so I need to read Gabriel's. Would be useful to test how much better we could do with a basic imager at L5, such as Vigil, and a polarizing imager along the Sun-Earth line, such as Punch. So does anybody want to make some comments?
It definitely would be useful to test that. There have been a bunch of folks doing modeling and analysis, and opinions vary. So it'll be neat to see who wins.
Okay.
And Erica, I had a question, and this again relates back to Kurt's talk. So yeah, that discrete tomography was really interesting. You're kind of getting these shapes, these nice sort of shell-like structures in the CME. Kurt showed us something like that for the co-rotating interaction regions, and one of the things we're hoping Punch is really going to do is help us understand a three-dimensional shape, different, from the ecliptic. Have you looked at that at all?
Okay, so if that wasn't clear, in the EC team, I am the person who modeled and in charge of the modeling of the CMEs and doing the synthetic imaging, white light imaging on the CMEs that tomography effort is led by the co-leader, David Barnes. But in any case, what I can say is that tomography, yes, has been applied for correlated interaction regions with the rotational tomography technique. Yes, we heard about that yesterday. Not sure if the discrete tomography has been done on CIRs, but I know that with David's code, we can do it. What he needs is like high quality polarizer data. So if the punch team will allow us, we could totally apply the technique to punch data. And we can also do it with synthetic punch data.
Yeah, it might be good to start with the synthetic, it sounds like. And any more Sarah questions?
I got one more. And this one's for Erica, but anybody in the room who's a tomographer, and we have a lot. Or on, well, I guess online if they want to reply in the Slido. Punch has a much bigger field of view, and it just kind of hit me when we were looking at your thing, Erica, that you know, for most CMEs, for most fields of view, the CME goes through, and I mean, at solar maximum, there's always something happen, but a lot of times if it's not solar maximum, you can have a steady period. How are tomographers going to deal with that? The field of view, the full field of view, will almost always have a CME in it for a lot of the solar cycle.
So I don't think it's going to be an incredibly big problem because punch is going to have the largest field of view of all. And for tomography, like, we need multiple fields of view, so there is going to be some other imager that has isolated the CME more than punch has, right? If punch has like 3 CMEs in the same field of view. So with the other fields of view, then the reconstruction will focus on the one CME that is common to all the different fields of view. So yeah, the important thing will be to have very good background characterization and subtraction. And for that, I'm confident that the SOC will do a great job.
Actually, can I add to that a little bit?
Of course.
Yeah, so I wonder, so the CMEs would look different from CIRs in the sense that they will be compact and they will move faster. And I wonder if that they will move faster will allow us to use some sort of an optical flow identification of the points that do move faster. And then we can either subtract them from the background or subtract the background from them.
Oh, okay. He's bringing you the mic.
I have a general question for tomographers too, which is, you know, we've seen a lot of folks looking at CMEs, and you know that's a useful thing. The CIR tomography is going to be harder, right? Because you're looking at a manifold that moves in a non-intuitive way. I know Bernie's done some. Bernie, are you here? Oh, okay. Bernie's done some inversions of CIRs, but I think he's the only person who's really done a proper tomographic inversion of them. Have you guys looked at points of confusion in the rotational tomography, or?
I mean, at least from our effort, we haven't done rotational tomography yet. So stay tuned for updates.
Yeah, the comment I had made to Kurt's presentation about the gradients and the speed, if you can estimate the flows better, we may be able to use that as an extra constraint. I'm not exactly sure how to do that, but that might be useful. Okay, so I don't, we got one more. Oh, yay. Sam's got a question.
Hi, Anna. When you show the synthetic, like, punch field of view kind of perspective, you have these spiral shapes which come down to like very high or low in the field of view. Is that coming from an integral that goes through an entirely equatorial structure, or are those like high latitude structures in the actual simulation at other latitudes?
Yeah, no, the slices that I did show, they are fully confined in the equatorial plane, and the lines of sight were also fully confined in the equatorial plane. That is partly by design to just make the illustration simpler.
Okay, I guess everybody's very hungry, so we're finishing up early. So you'll have more time before Joe speaks, so you can make it back. Oh, okay. Yeah, Sarah has an announcement.
All right, so yep, we have time. We have Joe Westlake is going to be talking at 12:20, so we're breaking a little early, so that should give us a little time to eat. You can maybe even eat outside if the thunderstorms and tornadoes haven't come yet. That's what I heard was happening today. just to keep things exciting, we do fire drills, And then the other thing is if anybody else has an AGU session they want to announce, please send it to Craig and or me. And then after lunch, please do it by 1 o'clock and we'll put it on a slide so that we can put it up after lunch. Anything else? Okay, have a good lunch.
Hello? All right, Joe, can you hear us?
Yeah, sure can.
Excellent. Okay, everybody, it is 12:20. So we are very fortunate to have Joe Westlake, who is the head of heliophysics at NASA, presenting. Can you all hear me in the room? Yeah. Presenting an overview of what's going on in the heliophysics division. Joe couldn't travel to us today, so he's going to present remotely. I can see on the screen there, Joe. So take it away.
Yeah, excellent. Thank you guys for taking the time to hear about what's going on in heliophysics. But also, I apologize that I was not able to come out and visit you guys. Perhaps next time. And let's see, let me go ahead and share with you guys a brief presentation. Then I want to allow a little bit of time so that folks can ask questions if you have them. Hopefully you guys can see my slides okay?
Yeah, it's great.
Okay, great, perfect. All right, so my name is Joe Westlake. I'm the Division Director for Heliophysics. Let me give you guys a little update on our Heliophysics Division leadership. So I have stepped into this role as of January 15th, and we are all very lucky to have Peg Luce, who continues to serve as our Deputy Division Director. Peg, of course, has stepped in for the second time as acting division director in the absence of a division director. So when you see Peg out in the world, please thank her for her service and her continued service to heliophysics. Nikki Rail is our associate director for flight, and in many ways Punch interacts primarily through the flight side of the house and probably is very familiar with Nikki. And then we've welcomed Teresa Moretto-Jorgensen back into our leadership team in heliophysics. Teresa was serving as our our acting deputy division director. She is stepping back in as the role of director of research and will be handling most of our RNA and research-related tasks within the leadership team. So welcome back to Teresa. I'll give you guys a quick update on our recent events. Of course, right now we're in the middle of and towards the end of the heliophysics big year. Let's see if we can get this to run. The heliophysics big year started off with the annular eclipse last year and went into the total solar eclipse. I had the joy of joining along with Craig and others from the Punch team at the Dallas Cotton Bowl, really a lovely event in which we had many other Dallas folks come and join us for really a spectacular activity. The heliophysics big year ends this year with Parker Solar Probe's closest approach to the sun coming up on January 24th. And talking about the eclipse, here's a lovely photo from Keegan Barber of the eclipse. And of course, one of the true lovely things that I was able to get was at the Cotton Bowl. Craig and folks on the Punch team shared with me a live view of the eclipse and of some really spectacular prominences and other things coming off of the solar corona. So really excited about that, and was really a wonderful experience for me, and a thank you to the team for sharing that with me. I think that was my first time seeing an eclipse in person, but also one of my first times having that kind of view of the sun, which I thought was very impactful. A little bit on the statistics from our solar eclipse activities. So over 400 NASA employees across 14 locations engaged with the public. Of course, many more scientists, researchers, engineers also engaged with the public as well. We distributed over 2 million eclipse glasses, making sure that there was a very safe eclipse. We had over 12 million viewers for the NASA English broadcast and over 4.6 million viewers for the Spanish broadcast. Really fantastic metrics against which we've seen and captured a large portion of the American public. We also had tens of thousands of engagements across social media, whether it be with Barbie, Cookie Monster, Elmo, Snoopy, Lego, and various other places. And 17,535 news stories with a very large publicity value. So these are really wonderful metrics that really just sort of touch the surface of where our impact was from this recent solar eclipse. Now we've carried this impact from the solar eclipse forward into what has been really a major event, which was the solar storm that happened over the weekend of Mother's Day. Folks are sort of naming this the Gannon storm in memory of Jen Gannon. This is was really a wonderful event in which we were able to see a whole slew of CMEs, and those CMEs, they overlapped each other and really ended up making for a heck of an auroral display, and for basically everywhere across the U.S. except for the D.C. area, because we were totally clouded out. And let's see, maybe I can make this play, and you can see some of those CMEs as observed from SOHO. Now, we're really, really excited to be able to see CMEs and other events like this from the viewpoint of Punch, and I'm excited to see what that's going to look like. And I'm sure that you guys have some ideas as to what you'd be able to discover for upcoming events, and really, really excited to see this mission get up and running. I'll tell you guys, the decadal survey is coming soon. I know about as much as you do about what's in it, though some of you in the room probably know more than I do. There were over 250 white papers submitted, and I love this little word cloud that James Mason put together that really talks about the content of that set of white papers, and hopefully what will end up being the content of our heliophysics decadal survey. As you guys know, the decadal survey rolls out in a process. So it's going to come out and we're going to have time to consume it and work with it before we enact it. Generally what happens is that the decadal survey gets delivered out to the public. The decadal survey team goes out and reminds and presents that out to the public. We'll see a lot more about that hopefully at the AGU this year and meetings in the fall. And the Heliophysics Division also provides a written response to the decadal survey. So we take some time, we provide a response, and we really develop a strategy based upon that decadal survey. I think the key point for me to make here and for you guys to understand is that for any of these changes and any of the exciting new directions, it will take us time from the Heliophysics Division standpoint in order to enact and create this vivid future that the National Academies and our decadal survey has hopefully written up for us. I'll talk to you about our present fleet of heliophysics missions. If you look at this chart, the sort of decoder ring is that the missions that are in green are those that are in prime operations. So that's Parker Solar Probe, Solar Orbiter, and AW. Really looking forward to turn Punch, which is in yellow in development, from yellow to green. But you can see the multitude of missions that we have in development, as well as the missions that we have in operations, which are in blue. And we cover this wide realm between the closest to the sun to the farthest in our solar system with the Voyagers. I'll note while I'm talking about the Voyagers, the Voyager 1 spacecraft is back up and humming, and we're getting some fantastic data back now. So huge kudos to that team for bringing things back online. And let's see, let's talk about our launch timeline as we come up into the next year and a half. So the Heliophysics Division has really been doing some really fantastic work to push forward a large number of new missions in the basically the next year and a half. So ESCAPADE launches this fall, two spacecraft going to Mars, EASY, and a set of CubeSats looking at our at the Zeeman effect on field lines in the auroral region, a SUNRISE, which is looking at a radio interferometry array or radio array, TRACERS, which is looking to trace the field lines between the polar caps out into the magnetosphere. Of course, Punch, our favorite polarimetry coronagraph. And then IMAP and Carruthers, which are launching together. IMAP is looking out into the boundary between our heliosphere and the interstellar medium, and Carruthers, which is looking back into the geocorona back at Earth. I would also like to ask you as science members to help us to share share your science. So share the scientific discoveries that you are doing, the science work that you guys are doing, so that we can broaden and bring more impact, both to the work that you're doing, but also elevate the status of heliophysics as the preeminent science at NASA. Really proud of the work that our folks in heliophysics are doing, and I'd like to be able to share some of that with folks higher up at NASA, but also be able to share it with the community as well. There's an email here, hqheliohighlights@mail.nasa.gov. You can send us fairly straightforward nuggets, and I'll give you an example of a nugget here. So this is just a straightforward nugget on a recent result that was in the Nature journal on solar moss, taking measurements from IRIS and High C. And this is really just an image from the Nature paper, a link out to that paper itself, as well as some description from that caption. So as easy as that, and our folks will ask you questions and try and develop this into a story that we can actually tell higher up at NASA and tell in other places. So help me try to tell stories about our science in ways that is captivating for folks. I'll give you an update on the Heliophysics System Observatory. Now, when we talk about the Heliophysics System Observatory, what we're talking about is the multitude of spacecraft and missions that are in their extended mission phase. Those create the Heliophysics System Observatory, of which we have a multitude of missions. All those missions generally go through the senior review as they're reviewed by members of our science community. We found from our 2023 senior review that there was a desire to bring individual extended mission proposals into the system level coherence in order to sort of break apart or figure out ways to further and better join our communities together. And so we're looking for ways to, from these senior review findings, from various other places, looking for ways to broader engage the heliophysics public, but also broader engage our system observatory. And so we're in the middle of developing a framework that will help us to understand and work with the extended missions and the multitude of missions, including Punch, that are going up in the next couple of years, in a way that we can actually draft a policy that allows us to have this sort of system level influence. Right now, we're in that policy development phase at the bottom there, and we'll be seeking community feedback. We sought our first bit of community feedback from that we received from the HPAC, which happened earlier this week. And then we'll actually get, in September, we'll have a heliophysics town hall in which we will discuss further this policy, as well as get feedback from folks. So we'll have an IO tool that allows people to ask questions and give comments prior to finalizing and releasing that policy into the 2026 senior review and ROSES. So I look forward to engaging with Punch as well as with the rest of the heliophysics community as we talk about this extended mission policy. The hot topic these days has been GDC and dynamic. I'll give you guys just a really brief update as to where we're at on these exciting missions. So the Geospace Dynamics constellation and dynamic, which is dynamical neutral atmosphere ionosphere coupling, are the next missions in the Living with a Star and Solar Terrestrial Probes program. The two of them together provide this whole system study of the upper atmospheric dynamics. And the two of these missions together are sort of in an interesting spot as far as how they've been able to move forward. The way that the fiscal 24 budgetary language gave it is that the GDC mission was placed on pause. That fiscal 24 pause meant that we could continue to operate and bring forward the instrumentation. So the instruments are continuing to progress, and we're doing limited work on the mission and spacecraft during the fiscal 24. The fiscal year 25 President's budget request proposed cancellation of GDC due to budgetary constraints, mainly in response to the January 2024 Fiscal Responsibility Act that was signed into law, which has caused a significant decrease in SMD's total funding. Now, as you guys know, the budgetary process is not a one-step process. This, to me, is in many ways the first step along the way. that first step along the way allows us to open the conversation in a way that we can talk about where we're going to go to next with GDC. And then on top of that, the other thing to note is that in the fiscal year 24 appropriations language, we were asked to report back with a study that would, or a report on what it takes to launch GDC by the end of the decade. We are working on that report and we'll be delivering it towards the end of July. Dynamic, we selected recently 3 missions or three potential missions into Phase A, into a Phase A study. Those selections were just made in June, so literally last week. We're really excited to welcome on those teams and see what they can come up with as they move forward for Dynamic. Couple more updates. I'll give you guys an update on our RNA. You can see our RNA selections from ROSES 2023. ROSES 2023, we received a significant increase in proposal pressure across many of our programs. I've been looking out and asking folks within the community what is driving some of this proposal pressure and trying to understand cases where the enhanced proposal pressure makes sense or where there are potential issues out there. So if you all know of reasons why there are increased proposals in some of these programs that have seen fairly significant declines over the past 5-6 years, I would be curious to see what you guys see there. I'll note that these selection rates, some of these are okay, some of these are an issue. And so we're actively working to figure out ways to improve the selection rates. We talked about this a little bit at the town hall and at the HPAC, where we've been asking for advice from our HPAC members as well. I'll note that we stood up our Heliophysics Strategic Technology Office as well. HESTO is the place that helps to manage the technology program. I would look out to this hesto.smce.nasa.gov website to look for announcements and opportunities that are in the technology world. I will also note that in later on this year in September, we'll have the first 2024 Heliophysics Technology Symposium out at Wallops. So I look forward to and hope that you all can come and join us, and especially the folks who are working instrumentation and have unique ideas that could go into our technology program. We'd really love to see it. I'll note that it's a great time to be a heliophysicist, and I'll leave you guys with a quick stay connected and stay informed, whether it be to bring forward some of these heliophysics highlights, but also connected via our Sun Earth blog, the Sunspot blog, Facebook, and Twitter. And I think with that, I left a couple of minutes for questions, so I'm going to end this slideshow and so that I can see you guys.
All right, thank you so much. We do have a lot of people in the room. We have a couple of questions on our Slido chat. If you have questions, you can put them on there, or just come up to the mics here to take your turn and ask Dr. Westlake. I'm going to hand off to Sarah with the first question.
Alrighty. Hi, Joe. This is Sarah Gibson. I'm the project scientist of Punch. So,
hey, Sarah.
My question is, okay, so Punch is, we're very lucky. We have multiple science co-Is and collaborators across the globe, and also representing ground-based observatories. And so I was wondering what your thoughts were about how to best exploit the synergies between Punch and also other NASA missions, and both international and ground-based observatories.
Yeah, I'm judging from the white papers that went into the decadal survey. One, I expect the decadal survey will probably weigh in on this. I don't actually know the answer to that, but I'm assuming, again, just by the white papers that went in, that there will be some weigh in there. From our aspect, from the headquarters aspect, we're very interested in the collaboration that can happen between the ground-based observatories and between our space-based missions. Now, you all, of course, know that there is some challenge there. Right? There are limitations in what NASA can and can't do as far as ground-based observatories and what we can and can't work with as far as that goes. There's a lot of things that go between NSF and NASA, and a lot of really great partnerships that have been built in that regard. I have been talking with our NSF colleagues and trying to find ways that we can further build and support this ground-based community, and I look forward to working with them more as we go forward. My folks were looking at ways to create some better policy around the way that NASA handles, specifically heliophysics handles, ground-based assets. And I think in the next year or so, you will probably see some results of that. So hopefully that's positive news. I again, the scientific synergy that we get between these ground-based assets and our space assets is science positive and should be supported. The challenge is just always interagency support and making sure that we're all on the same page.
Good. Let's see. Next is Nikki Vile, who's at the microphone.
Hi, Joe. How are you?
Hey, Nikki. Good.
I was curious if you could say more, please, about how heliophysics is going to respond to the decadal. Are you going to do a heliophysics roadmap committee, or can you just say a little bit more about that process?
Yeah, so at the very least, we provide a written response to the decadal survey. That written response is us at headquarters taking a minute to consume the data and to understand what's in there and to say, we heliophysics agree with, don't agree with, however it is going forward. That's the least amount of response that you'll get from us. In the past, and looking at what other divisions have done, there are differing approaches to how folks deal with a new decadal. Some divisions have been using roadmaps, some divisions have not. And actually, the most recent set of decadal surveys have not used a roadmap. And to some degree, there's lots of different opinions as to whether or not one should do a roadmap. And to be honest, I haven't quite figured out exactly the right way forward. Some say that it actually delays the start of decadal process by creating a roadmap. Some say that it actually makes it go faster. So with those two differing opinions, it could be either way. But to some degree, I think it's that initial look at what's in the decadal that will put forward the right path forward. I'll note one other thing, which is that my folks at headquarters and the folks that you see out in the community from headquarters have been working at and thinking about how we're going to respond to the decadal. And we've begun developing a strategy from headquarters on how to do that. So we've at least started to think about it. But until we actually see the content, it's going to be a challenge. Thanks. Great question.
Joe, I actually have a question for you too, which is
Yeah.
There's been a fair amount of budget pressure over the last year or so. We've seen a lot of symptoms of that. One of the more obvious ones has been AO's pushback and that sort of thing. And then, of course, we just saw your selection ratio, and at tests we heard that the selection ratio for the HSR 2024 is not looking good. So what's the outlook for heliophysics RNA for the next couple of years?
Yeah, I'll be perfectly honest with you guys. With the number of proposals that we've gotten into HSR and the guest investigator program, the selection rates coming out of this year's RNA are going to be a real challenge. As I mentioned in the talk, I am concerned because I don't quite understand the proposal pressure changes. So the increase in number of proposals that we've gotten into HSR and the guest investigator program are sort of out of bed. If you look at 24 and now what's going to be 25, or I should say 23 and 24 values, they are significantly higher than the 22, 21, and 20. Now, of course, we're in the middle of a global pandemic and all the other things that go along with that. But some of these are even higher than pre-pandemic levels. And so I have some concerns in how we're going to handle these. I mean, in the short term, in reality, we're going to have some low selection rates for a little while, and it's going to be unfortunate. And I say that because the thing that we have done is we've ensured that the funding for the RNA program remains at least constant. We've had immense budgetary pressure, and we've pushed a lot of that budgetary pressure onto our missions and kept it away from the RNA portfolio. And so in many ways, that's caused us to, whether it's change our ability to have new competitive missions, or it's changing our ability to put forward things like GDC and dynamic. We have made sure to keep the funding levels, so the dollars that we put into the RNA portfolio, the same. And that to me is when I think about what we do for the budget, the RNA is the last ditch effort of being able to do any sort of cuts. And so we have maintained a very steady RNA level as far as dollars go, but we've had a fairly flat budget for years, and so your buying power with one RNA dollar has gone down, and I know the community is feeling that, and we'd like to figure out ways to improve that. And so it's sort of a two-sided thing. So understanding one, why we're getting so many new proposals in, that's something that I'm out and about and talking to folks about, and it's something I would have loved to have been around the group there to chat with folks about. But when you see folks from headquarters, please let them know if you have ideas or thoughts on this. And again, just to voice once again, with all sincerity, RNA is the last place that we cut. And so if, under budgetary pressure, I take it very seriously that we make sure that our research and analysis funds are there to support the science that we're doing.
All right, thank you. We have Anna Molyneux-Shenko at the microphone for you.
It's not as much a question as a comment, but
Sure.
regarding the influx of proposals, it is true that the SPD had received an influx in early career scientists in the last several years. So I do not know if that is related and how it is related, but it can be a factor.
Yeah. So one of the things that's a great input. To be honest, if we can figure out that it's demographically related, that's actually not a terrible thing. It's just we want to make sure those folks are supported. The vibrancy of our community requires us to have a good balance between folks that are coming in and our folks that are retiring. And so making sure that we do support our early career folks, super important. Yeah. And thanks for that.
Excellent. Heather?
Yes, Heather Elliott. You mentioned that you'd put pressure on the mission budgets. Do you think that caused people to move over to RNA to get funding?
Yes, we've been looking at that. That's been a curiosity. And the pressure, it's not quite a one-to-one game, right? So the pressure that we put on some of the missions have caused a few extra proposals, but not nearly the numbers that we've seen.
Okay. You think
So it's a good idea.
Maybe people automated more or something?
I'm worried that people are fear proposing.
Okay.
Is sort of my concern.
Okay.
And if that's the case, I would love to hear that.
Okay.
Not in that I enjoy causing fear for people, but in that I would love to understand the concern. And thanks, Heather.
We have a question from Noriaki Nita.
I should say that the heliophysics is always weak division at NASA, but we believe that we are doing something very, very important. It is, not just living with the star, but also in connection with astrophysics and planetary sciences. But our budget is also always low. So my question is, if you have any strategy to change this trend, like hiring those people who are more outspoken and more effective in communicating with other branches or just even with general taxpayers, that we're doing something very important.
Yeah, so your comment's a good one. I think the best thing that we as a community can do is to build upon singular talking points and singular, all of us sing from one sheet of music when we go and talk to folks about the importance of heliophysics. I think for years heliophysics has struggled by taking a widely divided community and looking after certain pieces of that community. I think one of the great things that Nikki and other folks have done with the TESS meeting and with various other pieces of the community is attempting to unify. And I think within our heliophysics community, that bringing together one message that is exactly what you started with. What the work that we do is important, and it is a discipline in its own. It has amazing interfaces with all of the different mission directorates and all of the different divisions within NASA. And our work is so important that we really need the additional support in order to do our job and to do the important work for the American public. So being able to deliver that message uniformly as a heliophysics community is the best way for us to garner more support that we need, in my opinion.
Okay, this is Heather again. We've had a lot of outreach this year with the eclipse, and we've been making heliophysics has been making the news with the big storm that went all the way to Texas. But I'm wondering if it's not that the public doesn't like our work or think it's really cool. They don't necessarily know to tell Congress, we want you to fund heliophysics, because they don't know what heliophysics is, and they don't know that the cool stuff they saw on TV was part of heliophysics. I wonder if maybe we should start on all the press releases and web releases, put NASA heliophysics repeated.
So we have that at the bottom of all of our press releases. I totally agree. We've been working on a sort of branding isn't the right word for it. It's a way to make sure that NASA heliophysics has that sort of attribution when we put things out. But I would encourage you all to inform your neighbors. I mean, that's the big thing. There's only so much that I can do from a headquarters perspective as a civil servant, as far as that goes. In many ways, I think I forget who put it this way, but they put it the best, which is I lack an opinion nor an ability to chat with and advocate for the work that we do. And so in many ways, the only thing we can do is educate. But in many ways, the things that you guys can do out in the community are much more impactful in that regard. So being able to deliver the message that our heliophysics science is that important and deliver it to folks who matter in that regard, I think is of importance.
Okay, thanks.
Thanks. Let's see, I have a follow-up question to something that we did yesterday here at the meeting, which is we've been talking a lot about open science. Punch has really striven to be as open as possible, and we're continuing to do that. We had a great presentation from Barbara Thompson about the TOPS effort that's going on.
Excellent.
She made some allusions to that becoming sort of official policy moving forward. Do you want to make some comments about open science and where we're going?
Yeah. So as many of you guys know, the NASA is a part of the executive branch. The executive branch makes various decisions, and one of those was to enable open science across the multitude of NASA endeavors, and within that, what open science generally means is what we consider good practices within heliophysics, right? Ensuring that our data is open, that it's of the highest quality, and that it's out there within the public, not behind paywalls, not on one person's computer, but is out there and accessible for all to see and use. And I want to laud and give you guys real kudos for embracing that from the beginning. I'll note that some of the tools that we're creating that are being created within HDRL and within some of the TOPS and other places, hopefully will be of help to you guys on Punch, allowing you to better share your data and allowing you to better integrate with this, the system observatory and other things as you go forward. So I would encourage you to engage, Barbara Thompson, I believe, really understands this as well. But I would encourage you to engage with the HDRL folks and various other folks in order to make sure that you've got you can best use the wide multitude of investments that we're making in open data and open science. I will note also that while it sounds like we're sort of investing on extra things here, we're in many ways responding to requirements that are being placed upon us. They're not bad requirements, and we've had some influence in trying to write them as well, but they are being pushed across the Science Mission Directorate portfolio. And really, we're looking for ways. I think one other thing to note that I think is of importance here is that when you look at where data science is going, one of the things that's amazing in the world of data science the ability for machine learning and AI algorithms to get in and make discoveries based upon some of these data sets. And so some of this open science side of things is enabling that kind of work, which hopefully works as a multiplication factor of the science, and you know, the multitude of data that's going to come down from Punch will allow us to do some really unique things.
Thanks. Let's see, are there other questions? I think we're close to the time. In fact, we're just a little bit over it. I think we've had our questions answered. Thank you very much for taking the time to come and present to us.
I sincerely appreciate you guys taking the time to listen, but also your attention, and sincere apologies for not coming out to visit and spend time with you guys. Next time for sure.
Thanks so much. Take care.
Yeah, thanks. Take care.
You will. All right, back to you, Sarah. What's our agenda?
We have an hour of poster time. Woo! So 2 o'clock, talks begin. Enjoy the posters. We're going home. We're done.
Mm-hmm.
Can you hear us from here, Bernie?
Yes, indeed.
Okay. It's about 2 o'clock. I don't know if anybody's ringing the cowbell out in the room there, but please come on back in. We have our afternoon session on punch and space weather starting up now. And we have 2 out of the 4 talks are virtual. The first one is by Bernie Jackson from UCSD, and he'll be talking about time-dependent 3D high-resolution reconstructions providing brightness and polarization brightness. So yeah, take it away, Bernie. I'll try to hold up the 5 minutes to go so you can see it from where you are, and yeah, take it away.
Okay, here you go. Presentation mode here. These are the folks that helped me on the analysis so far, and have been most responsible for the instruments analysis that I do over the last few years. I'm going to give you a short tutorial about the time-dependent 3D reconstruction analysis that I do and how it works. The analysis modification to provide high-resolution Thompson scattering pseudo brightness and polarization brightness will also be discussed, and I'm going to talk about the beneficial enhancements for future 3D reconstruction analyses that are needed. Thompson scattering brightness, the solar mass ejection imager that was launched in 2003 made strip images around the sky from 20 degrees out to 180 degrees. These strips from 184 kilometers above the Earth in sun synchronous orbit, the instrument was, could provide about a gigabyte of data a day from these images that were presented over the 140-minute orbit. You can see here what we did with CME that was one of the brightest seen during this period. You can, in the 3D reconstruction analysis on the left, show you this over here, you can see this complex of CMEs come out from the sun, and you also see background here, but the structure that you see is a bright, very large spike up to 35 particles per cubic centimeter can be reconstructed here with ACE, or looking at the ACE data, or in retrospect at a 1.5 hour cadence, and it agrees the tomography is pretty well with what's seen in the wind or ACE data. There are differences from the 2 and C2 monitors. Now, how this works, you have a weight along the line of sight here. This is brightness, and this is polarization brightness, and I'm going to talk about polarization brightness. The you have a line of sight from Earth, the observer, that expands from close to the observer to a long distance. But you segment this into line of sight segments and try to figure out where every segment comes from on a source surface below all lines of sight. What you do is start with an initial speed down here at the reference surface and project outward to the lines of sight, not the lines of sight that are present. And you do that to figure out on that surface, and it's shown here on the right, and all the projections of approximately 1/25 of the numbers of lines of sight from one time to another, how to change these values on the surface. So you start with an initial density here that's just simple, a certain amount of material that moves outward from the sun, and speed, and then you conserve mass flux from this location to provide a model along the line of sight that from the first guess, looks like one thing, but when you look at it relative to the brightnesses that you actually see, you then change the brightnesses, the densities and velocities on the surface here to better match the lines of sight. You formally invert the changes you have to make on the surface, and you do that all the way along the line of sight to change the analysis. Okay, well, the brightness and polarization brightness of every electron here is folded into each segment's electron density, its distance from the sun and its distance from the observer, and to sum to provide the model image brightness that you observe, whether it's from observed data or the line or your model data. And when those match, you've converged. Well, what does it mean for tracking line of sight segments? You have to track these outward, and that gives you the location along the line of sight. And if many line of sight structures are present, you really have to track them all, and that's generally the case, be they background or CMEs, and sometimes there are a lot of CMEs along the line of sight. To know where any one line of sight segment is located, you must what's present in all of them. And this implies the background can be as important as the line of sight place of interest you're trying to track. Now here's some examples of the analysis that I did at high resolution. Here's that same structure that was present in 1 degree, 1.5 by 1 degree resolution at in latitude and longitude, with about a 2-hour cadence, little s, in time. And so you can see this one instance in time of a ecliptic cut, a meridional cut, and a synoptic cut. And the point to make here is that the high resolution analysis that we do shows that CMEs are corrugated and spotty. They're not really a nice, smooth feature that you can see. And this meridional cut shows that if you were one spot here or the other, at the speed of the CME, which is about 600 kilometers, it would take about 12 hours to go that distance from this part to that part in these things. Now, SME only looked outward from about 20 degrees, and so I show that here. And so the reconstruction actually is present from that and viewed out to the 180 degrees that we were able to view. Once you have the data here from the solar mass ejection imager, you know, for instance, as a perspective view of what's seen. Over on the right is this divided into cubes, And that it can give you, shows where the excess mass is, and so that gives you an excess mass, but you also have you know what the ambient is within this volume, because the CME is there, and so you add that to the excess mass and get a total mass, and you can get the energy if you know the speed of the various particles here. You then get a total kinetic energy of the CME that moves outward. Okay, so in getting pseudo brightness or polarization brightness, you have a density here that I showed you before. This is a low resolution version of the analysis, and you can see there's a lot of structure. It matches in situ pretty well, and you get a remote view, a sky map out to, in this case, out to about 110 degrees, an ecliptic cut and a meridional cut of the data. Well, you can take those densities that you have from this reconstruction, and you can run the same lines of sight you have for the data and from the densities that you receive from this analysis, and get a pseudo brightness, and use that pseudo brightness to see if you can reconstruct the densities in the same way. And sure enough, this is a remote view. This is the sky map, and this is the ecliptic cut, and a meridional cut from these pseudo brightnesses that you've run through the volumes that you've reconstructed in density and in velocity, by the way. You can also make these brightnesses, these densities into, and then the lines of sight that you have into a pseudo polarization brightness analyses, and you run this through the reconstruction, and you see, yes, indeed, you get a remote view, a sky map, and an ecliptic and a meridional cut that are pretty much the same in just using the pseudo polarization brightness. Haven't yet used the brightness to polarization brightness or PB to B ratios to do this reconstruction, but I'm working on that. Now, this shows in the pseudo B brightness where you are viewing with SME. The caveats I have here are that the images are shown the cuts are shown at a given instance in time, but they were actually obtained over a period of the minutes that were observed from the solar mass ejection imager itself. So, and you use the lines of sight at each time that are available. And that's for both the brightness and for the polarization brightness for the pseudo values of lines of sight. The images that show the volumes were sufficient to make accurate 3D reconstructions, but to provide the pseudo lines of sight, each volume was filled completely, and then that pseudo observation was used. You have to make a filled volume because you don't want parts that are not included, don't have any density in them when you provide the lines of sight. So now here's what I did at higher resolution that would be something very similar to what you see from Punch. You have here using stereo HI cameras 1, A and B, in 2007, the two spacecraft here in the ecliptic cut, you can see they're very close to Earth. And so they can provide a view in the ecliptic plane that would be very much like Punch. And here, the cameras themselves, this is the inner distance. You can look from 4 degrees from the sun in this fairly low resolution plot. And you can also see this is the extent of where the stereo cameras look close to the sun, and from in the ecliptic cut, you see them here. These two locations. This one comes from the behind spacecraft, and this is from the ahead spacecraft. And like I say, in the ecliptic cut, this is pretty good. Here is sort of the closest you can get to stereo over the poles. At higher resolution now, you get a lot more structure, and this is more like you would see in the stereo spacecraft. But again, you only really can directly reconstruct this portion of the interplanetary medium. All of the rest of this is an extrapolation outward. This is about 90-degree across view of the stereo data from this high resolution reconstruction that we provide. And this, of course, a meridian cut. I take a little closer look here. You can see all the structure that's present in the region from the stereo behind spacecraft. And there's a lot of features here that you see in detail at this about 1 degree by 1 degree resolution. And again, this area here is what you can directly reconstruct, and all the rest of this is just extrapolated out from using the modeling that's present and available. Although you can see all the way to Earth here, you must complete the lines of sight that are present along each one of these. And for punch, you're going to have about over a period of a month where you're viewing this, you'll have about 6 million lines of sight in 1 square degree resolution bins, and another 6 million in polarization brightness.
Bernie?
Time. Yeah.
You've got about 1 minute.
Okay. And here's the velocity from that same region that you can see in low resolution from the IPS. What you have to do in the future, some work can already be done using the stereo different angular portions that designate an inner and outer flow locations and reconstruct them. And it would be best to provide this using multi-node processing. The high resolution stuff that I've done takes about a day and a half to do. And so if we can cut that down by a factor of 40 or so with multi-node processing, it'd be great. Better way than IPS currently used to determine the flow in the region would be certainly to have correlation tracking. And hopefully this gives you far greater numbers of lines of sight that you can use and works appropriately to tell not only the flow, but the acceleration that's present. IPS can't do that very well. And both brightness and good PB punch data will certainly refine the 3D positions of structures without as much need for flow impact over large distances. Conclusion, I've given you a brief tutorial about how the UCSD time-dependent 3D reconstruction works. And I've mentioned the analysis modifications currently available to provide high-resolution Thompson scattering, pseudo-brightness, and polarization brightness. Some, and hopefully soon available, changes are needed for future analysis, including correlation tracking, to provide higher resolution velocity resolutions. Working on it. Thank you.
All right, great. So our next talk is Dan Seaton from SWRI, who's going to be talking about the quick punch data for space weather operations. Are you the 5 minutes? All right.
Okay. Just figure out how to make the pointer work. There we go. Okay, great. Yeah, so I'm Dan Seaton. I used to be the SOC lead for Punch, but Marcus has taken over that and is doing a great job. However, I still am the lead for this Quick Punch project. And working on it with people from the SOC, with people from the Space Weather Prediction Center, NOAA's National Centers for Environmental Information, NOAA's Office of Space Weather Observations, among other folks. And then also, some of the stuff I'm going to show today is from a tutorial that I developed when I was at NOAA with a colleague, Rob Redmond, and so I want to give a special shout out to him too. I thought we've heard a lot about sort of really detailed things you can do with punch, and we'll get into some of that, but I thought because this is a talk about how punch data can be used in space weather, it might be worth taking just a few minutes and talking about how space weather forecasting actually happens, so we can see where the data will fit into the sort of different forecast activities. And, you know, maybe to start by just saying, why do we care about this? I don't think I have to sell this to anybody in the room, but there are effects that range from the sun to the earth. It touches aspects of science, it touches aspects of technological society, and it's actually a remarkably old problem. There's this beautiful news infographic here from more than 80 years ago, and they've glossed over some of the key science that happens between the sun and the aurora, but people have been talking about space weather for a really long time. And so I think finally we're at a place where with things like the GOES program, they're going to launch a new satellite next week with Punch. We're in a position we can actually make some progress on some of these things. So this stuff is probably pretty familiar, but let's talk about it anyway. You know, space weather is a really big bucket. It encompasses everything from the sun to the heliosphere, flares, eruptions, the solar wind, to the Earth, the interactions of the interplanetary magnetic field and the solar wind and the embedded magnetic field of coronal mass ejections and all the particles and stuff with the Earth's magnetosphere. And Punch really fits into a special and significant gap in these observations, which I'm going to tell you about. Of course, I probably also don't have to tell you about the different effects that space weather can have, but you might not know about how space weather forecasts are encoded. They have 3 primary scales for describing the severity of space weather impacts that are very much like hurricane categories in category 1 through 5. They have an R scale, an S scale, and a G scale. And I'll tell you a little bit more about those in a second, but let's just talk through sort of what the effects are and which scales people sort of use. You know, space weather can affect global navigation, all 3 scales, radio blackouts, solar energetic particles, and geomagnetic activity affect that stuff. Satellite operations feels effects from S and G scales. Space operations, the same thing. That's, you know, human space flight, astronauts in space, they can be affected by particles and changes in the magnetosphere. Of course, everybody knows about the aurora. We don't have to talk about the aurora. That's the hot topic, thanks to a big G-scale event just a couple of months ago. Aviation is impacted by all of these. Power grids are really impacted by the G-scale. So, you know, we have ways of classifying the impacts and helping people prepare for the effects of space weather. Here are what the scales are. The first one is the radio blackout scale. This really looks at how X-rays and high energy radiation that results directly from solar flares impacts the Earth's upper atmosphere and the ionosphere and causes radio blackouts. And it goes from R1, which is just sort of minor interference for high frequency radio communications, up to R5, where you can completely black out the sunlit side of the Earth for hours at a time. And lots of long range communications can't happen. And these are important communications that are used, for instance, for airplanes that are flying over the poles and have no other way to communicate. And so, you know, airlines have to modify polar routes. Search and rescue can be knocked out. The R5 has a real measurable impact. Then there's the solar radiation storm scale. That's from solar energetic particles. You know, the lowest is sort of just, again, sort of minor impacts to HF communications. But at the extreme side, there's really serious health hazards to astronauts in space from being irradiated by high energy particles. Satellites can be taken down and have died due to just extreme bombardment by energetic particles. And again, you can have additional radio blackouts. And this is categorized by sort of the particle flux measured in situ. And then finally, there's a geomagnetic storm scale. which ranges from G1, which is like, oh, you know, power grids have to flip some circuit breakers and move some power around, up to extreme, which is actually what we experienced. Maybe we were at a G5 minus, but, you know, auroras are seen everywhere. Power grids suffer really potentially catastrophic cascading effects that are really hard to mitigate, major communication problems. And this is the scale, I think, as you'll see, that Punch can help the most with, because Punch, its real strength is going to be helping us to refine forecasts of coronal mass ejection arrival times and impacts. So how do they actually do this, and sort of how do these scales work? Well, when you're a forecaster and you're sort of monitoring the sun all the time, there's a little bit of forecasting, there's a lot of nowcasting. And so every minute, all the time, if you're a forecaster, you're watching for a solar flare, you're watching for a coronal mass ejection to happen, you're watching solar imagery, you know, that's coming down with latencies of a minute or two. So you're really trying to be tuned into things that are happening on the sun in real time. And the first thing you will look at when something happens are the X-ray fluxes, because that's the first effect that's felt at Earth. As soon as we see it, it's affecting the Earth. You're experiencing radio blackouts, and you have to issue an R-scale alert. You notice there's no warnings or watches on the R scale, because by the time we know it's happening, it's too late. The thing's already happening. And so immediately there'll be an alert. They'll say, look, there's been an X5 flare, there's an R4 warning, whatever. And so that's the first step. The next thing is there's no official scale for this, but the actual radio from the sun can cause problems. You know, various radio bursts that are associated with the onset of CMEs. You have to watch for that, and they have some products that describe that as well, just not on one of these scales. Then you have a little bit of time. Just, you could take a really quick breath and deal with the energetic particles, because they take a little longer than X-rays to get to Earth. They travel a little slower than the speed of light. So you might have time to hit the button to say there's a warning, we're expecting an energetic particle event in 30 minutes or something. Then you watch the in situ measurements, particularly from the GOES spacecraft, and you issue your alert that an S-scale event is happening. This has all been in the first 10 minutes to an hour of a space weather event. Finally, there's solar plasma. And this is both the hardest to forecast, but the place where we have the best opportunity to actually issue a forecast. So once you see a CME go off, you look at the coronagraph imagery, you can see it's an Earth-directed event. And you have to quickly assess what's its velocity, what's its travel time. You can issue a watch. You say, well, we think there's an Earth-directed CME coming, and it might have some impacts. Then you wait a long time. If you're lucky, you might be able to run a model, but basically we quickly become blind to what's happening to these CMEs until they arrive at L1, where the Discover spacecraft can measure what's actually happening in the solar wind, and you can issue your warning. And about an hour later, depending on the velocity of the CME, it gets to Earth, and you put out your alert. This is really happening. It's a G5 event, it's a G4 event, or whatever. So there's this big gap. Oops, I hit the wrong button. There's this big gap right here where we don't know what's going on. It's really hard to refine your forecasts. And that's a niche that I think Punch can fill. What do we actually look at? Of course, I'll go quickly through this because I think this stuff is pretty familiar to a lot of people. But the first thing is you might watch imagery in extreme ultraviolet. That's the center image here from GOES SUVI, and coronagraph observations. And this is of the period when we had all that activity back in May. You watch that stuff, you see the CME coming out. Then you can use this CAT tool, which is a way to do 3D reconstructions from multi-perspective viewpoints and actually characterize where the CME is going. And then you can take the parameters that you fit in the CAT tool and you can stick that into a WSA model, and if this thing plays, here it goes, you can actually sort of try to get a sense of how the CME is going to propagate through interplanetary space. And here you can see the CME finally sweeping over Earth and causing all kinds of chaos. And then right before it gets to Earth, if you watch these trends, you can look up at this top line and see the magnetic field measurements, in particular the red line, which measures the BZ. Southward BZ means big G-scale events. You can actually issue an alert that there's a warning and then an alert that this event is happening. So again, you know, we have all this imagery. Oops, wait, it's doing the wrong thing. I'm pressing the wrong button. We have all this imagery over here, and we have data over here, but nothing in here. So, quick punch. And I only have a couple minutes left, so we'll go fast through the quick punch, but you've heard this story before. What is it? it's an enhancement to the nominal punch data streams that support NOAA space weather forecasting. It's going to reduce the latency with which we deliver certain punch products from a couple of days or even weeks down to hours. So these might also be interested for people who want to just see what's going on in the punch data in real time. We're going to do an initial demonstration of service immediately following spacecraft commissioning, and then we'll see what happens after that. All the data are going to go into the SDAC and the VSO, so you can look at them just like regular punch products, but they'll also be delivered directly to NOAA for space weather forecasting. There are 3 planned products. We have sort of low latency cropped Wi-Fi mosaics. These guys, they're going to only go out to 80 solar radii, so people in the space weather community don't have to deal with this rotating trefoil pattern all the time, which makes it really hard. It doesn't play very nice with their tools. We'll have low latency NIFI images, and then F-corona backgrounds, which are needed to subtract the F-corona, which are primarily used if you want to make mass estimates of coronal mass ejections. Most of the time they're going to be working with running difference kind of imaging. And the products are going to be in FITS format, but we'll make, just like all the other products, JPEGs and JPEG 2000, so you can put these things into HelioViewer or whatever. This is what the products look like. Let me see if I can skip ahead and show you the running difference version of this movie, because it's a little bit easier to see. The NIFI images, you can see they look a lot like the real imagery I showed you a little bit ago, and they provide backup for the coronagraphs, including the compact coronagraph that's going to launch on GOES-U, I think on Tuesday. And then they also provide an interesting opportunity to bring a whole bunch of different coronagraphs together and intercalibrate. The C-Core, hopefully LASCO, if it's still working by the time we launch, C-Core to follow on SWIFO L1. And so I think there'll be an interesting product for people who use lots of different imagery in space weather forecasting. And then these are what the mosaics look like. And again, let me see if I can just skip ahead to the running difference. The mosaics go out to 80 solar radii, and what's really important about this is it extends, I don't think it's playing. Here we go. It extends the opportunities to track a CME and refine your measurements of velocity, update your models from just 8 hours for a CME that's going 750 kilometers a second out to 20 hours, because the field of view is so much bigger than existing coronography. And so, you know, if this HALO CME that you see here turns out it wasn't quite going the speed you thought initially, you can go back and you can do another forecast and tighten up your warnings and your watches to better predict the actual impacts of space weather. So we're going to go and we're going to add imagery here that helps us have backup capability and more robust monitoring of the sun. And then we're going to extend this part of the sort of process so that we fill in a big gap where before it was like, oh, you see the hurricane forming off the coast of Africa. Oh, now it's in Florida. To have a little bit of tracking as it moves across the Atlantic. I just want to mention one other aspect of this that we're working on, which is not really part of Quick Punch, but deserves some attention. And this is being led by Matt West, who couldn't be here today. He's in Japan. We're doing some work on research to operations. And people have talked a lot about these, so I'm not going to go into great depth, but just we are working to make products and tools that use polarimetric observations to resolve this ambiguity in, is it a slow, wide CME or a narrow, fast CME? And I won't talk in detail about this because I think you've heard much more authoritatively from other people today and yesterday about how these kinds of polarimetric measurements can work to give you 3D reconstructions. But they do, and we have a tool called Vapor that allows us to sort of operationalize this capability. And Matt's been working to take models like this croissant model and actually reconstruct the positions. So we've done it with models and we've done it with real data. It's really hard to tell the difference between this PB and B image, but you'll have to trust me that it's there. The information needed to make a reconstruction of the position of a CME is there. And in this case, what we find is the CME is not very far from the sun because it's traveling in the plane of the sky. And that's a validation that this works. We've done other ones I don't have time to show you. But this is going to be a tool that will be available in our Punch repository, and hopefully someday we'll have operational products that draw on this. So for instance, if we didn't have stereo, which is, this is scary, almost 20 years old, and we don't, aren't going to get anything like Vigil until 2031. It's not going to be in location until 2034 or something. We might be able to fill in some of this missing information in the CAT tool. All right, so just my key takeaways here. Current CME forecasts lack constraints between remote sensing at like a few tens of solar radii and in situ measurements made at L1. We're going to fix that with QuickPunch. We're going to augment the NOAA data streams by adding both backup capability and extending the region of remote sensing. And through research to operations, I think we can even augment that a little further. So, thanks.
Our next speaker is Hugh Morgan. Are you there? Remote?
Yes.
Okay. I'll show you a sign on the webcam when you have 5 minutes left.
Okay. So I'll just share my slides.
Yeah, we see it.
Get my laser pointer up. There we are. Right, so I'm going to talk about punch and space weather forecasting in the context of SWEEP, which is a UK project which I've been working on for the last 3 years or so. So an underlying theme here is I've had to make quite a drastic change in my way of thinking from research to actual space weather operations. So briefly, SWEEP is the Space Weather Empirical Ensemble package. It was funded under UK government funding. The whole funding was £20 million spread over 12 projects, and SWEEP was one project, led by us here in Aberystwyth with collaboration from 3 other UK universities. We were to develop a new space weather forecasting software package for the UK Met Office, in particular the Space Weather Operations Centre of the Met Office. So the purpose of SWEEP was to take remote observations near the Sun and provide solar wind and CME forecasts at Earth. And in fact, it's perfect timing that I'm following Dan Seaton's presentation there, because it's given a nice background to this. So SWEEP was to merge several existing advanced modeling and research analysis tools to provide a fully automated package, near real-time forecasts of CMEs and the solar wind. We were to develop a full ensemble approach for uncertainties and provide multiple models and data sources running in parallel, and that gives robustness. An important point for SWEEP is that there was no new research. It was a packaging of existing tools, so porting all our messy research codes into a tidy operational package in Python. So I won't spend too much time on this slide, but the central workhorse for SWEEP is the HUX-T solar wind model here in the center. So this is a highly efficient solar wind model, and I'll come back to that in a following slide. Feeding into HUX-T, we've got 4 different inner boundary conditions provided by 4 different models. 2 of these, Dumfrick and PFSS, are based on photospheric measurements, so magnetic models. Then the familiar WSA model, which is an existing tool, and then a brand new coronal tomography, which is not magnetic based, and I'll come back to that in a following slide. So all of those 4 modules provide the conditions for the ambient solar wind. Then we have 2 CME modules at the bottom here. CAT CME, which Dan mentioned in his in the last presentation. So this is a manual tool where you fit the appearance of CMEs in coronagraph images from multiple viewpoints. And this gives you the geometry in 3 dimensions of the CME. Now, another brand new module, I've called it ACT. I also call it ACME for automated CME. And basically that's an automated method of the CAT tool. And I'll come back to that as well. So all of these feed in parallel into multiple cases of HUX-T running in parallel. So we have several initial multiple forecasts. and these are combined into a final forecast. Our very important point for Punch, I've boxed in these in blue. These are all coronagraph based and not photospheric based. And so there's a forecast stream here provided purely from coronagraphs and not from the standard magnetic models. So I've talked previously in Punch meetings on coronal tomography. It's my pet research subject. And Bernie has given a very good introduction to his tomography. So I won't spend too much time here. But basically, we take coronagraph data and invert it to find the three-dimensional structure, density structure of the solar corona. Now, for sweep, we do these reconstructions on a spherical shell at a distance of 8 solar radii from the sun. And this is going to provide the inner boundary condition for our ambient solar wind model. Now, in order to use that density information, we have to convert it to velocity. And the same is true of magnetic models as well. There's some empirical conversion going on. We calculated ours by looking at Parker Solar Probe data. So this is all Parker Solar Probe data up to 2022. And it's showing the distribution of velocities as a function of distance from the sun. And what we did was to fit several curves at different velocities throughout this distribution. So we've got a very slow wind, a medium slow wind, and a fast wind. And we fit those to this lower equation here, described by 3 parameters: the actual base velocity, this alpha parameter, and the scale height. And these are listed here in the bottom of this graph for different speeds of wind. So basically, if we know the base velocity at 8 solar radii, we can interpolate between these parameters and prescribe what the acceleration of the wind, what the velocity profile of the wind is between 8 solar radii and Earth orbit. To calculate the base velocity from the density, we did a large statistical study comparing solar wind speeds measured at Earth over multiple years with the densities we gained from tomography near the sun. So we optimize, using this acceleration profile, we optimize the relationship between density and velocity, and we get this upper equation here. So rho here is the tomographic density. It's normalized between a minimum and maximum. We plug it in. So if we measure a certain density near the sun, we plug it into this equation and we get a velocity distribution as is shown in this bottom map here. So this is Carrington longitude, Carrington latitude at 8 solar radii, and the base velocity for our model. Then subsequent acceleration is described by this lower equation. So using that inner boundary and our model, we can compare our model velocity with a velocity measured by Omni near Earth. And this is showing 3 years of comparison with the model in blue and Omni in black. The short message coming from this is we're doing as good as, if not better than, the magnetic models. And just as an aside, we don't actually use densities currently in sweep, but because we have the densities from the tomography and the velocities, we can do a mass flux constant approach. And when we compare densities from our model, shown here in red, with the Omni densities in black, there is a very satisfying relationship, with the main difference being that the 5 minutes, okay, that the Omni measurements have far larger variation at small timescales. So this is the automated CME detection routine. It fits a cone model. It detects CMEs automatically in near real-time data. So that's stereo beacon data and the LASCO near real-time data. When it detects a CME, it then passes on the front edge of that CME, detects the front edge, passes it on to an automated CAT tool, and it fits the CME. So we get the cone model parameters that can then be fed into our solar wind model. As far as I'm aware, this is the first fully automated near real-time CME characterization tool. So this is HUXT. It's a time-dependent radial solar wind model, incompressible hydrodynamic flow, so far simplified from a full MHD model. It runs in a second or so on a desktop machine, so we can do large ensembles. So we plug in variations at the inner boundary, create hundreds of models, and we get a distribution then at Earth. And this is an example of a forecast, very recent, using the coronal tomography and the automated CME tool. So this top right panel is showing the solar wind near the sun, and these circles are showing detected CMEs. And the green and the orange ones are ones that have a chance of encountering Earth. Because I'm short of time, I'll skip onwards and just show, because we're using an ensemble, this plot is showing as a function of time the arrival probability of the two CMEs in green and orange. So we have a spread, we have a median arrival time and a plus or minus few hours around that. So some thoughts, and I'm stating the obvious here, and Dan has mentioned this, as stereo and SOHO are aging, punch will become central for space weather forecasting, and especially in conjunction with Vigil L5. I see both of them as the future for space weather forecasting over the next decade. Punch will obviously drive different levels of space weather related activity, ranging from blue sky to method, system and development, where we're actually taking our research ideas and proving them statistically and sharing code, and then full-on operations where we use our methods in operational real-world systems. And it's important to realize that requires compromise. The forecasters are not looking for perfection, they're looking for something that's dependable. And punch data will immediately plug into the sweep. I'm using stereo Core 2 and LASCO at the moment. Sweep can easily plug into the sweep system. And some thoughts for discussion. Dan has pointed out the low latency NFI images, and I was very happy to see those. Those will be perfect for sweep. The Wi-Fi will also lead to much greater accuracy, I believe. And what's required, in my opinion, is regularity of observations, repeated observations of the same format at a regular cadence. Can Punch provide higher level space weather products to stakeholders? Yes, I think it can. And again, Dan has said this already. We can do updated tomography type maps, which are valuable. We can provide CME alerts and also CME characterization, but that will require other viewpoints for sweep. Do we want the necessary contact with space weather stakeholders internationally? Yes, I hope we do. And there's an important role here for us as science co-Is. That's it. Thank you.
Thank you, Hugh. You were right on time. So our next speaker is Justin Lelouedec from the Austrian Space Weather Office. We'll talk about enhancing stereo HI data with machine learning for efficient CME forecasting. And change your title. That's okay. That's all right. Go ahead. I'll make you a sign with 5 minutes. Okay.
Thank you very much. Yeah, I'm Justin. I'm from the Austrian Space Weather Office. I'm postdoc there.
I'm sorry, could you move a little closer to the mic?
Yeah, thank you.
Thank you.
Yes, so I'm Justin. I'm postdoc at the Space Weather Office in Graz in Austria, and I'm going to talk about stereo and images, still about forecasting and what we can do with the data and how to improve it with the beacon mode that was talked about before. And also toward the end, I will be a bit more optimistic and hope for stereo to be alive in the next 10 years, hopefully, to see how it can work with other spacecraft. So this whole Beacon to Sense, this enhancing project starts from the paper from Meike from a few years back, which was about comparing science and beacon data from stereo spacecraft, especially the HI instrument, and see if the beacon mode, which is the near real-time mode for this spacecraft, could be used for efficient forecasting and early-on forecasting of CME's arrival on Earth using a drag-based model. So the conclusion of the paper was that to some extent it can, but the quality of the data gaps, and some other problems makes it very difficult to use it in real time and get efficient forecastings. So what are the differences between the beacon data and the SENS data? So the SENS data is quite high resolution, so 1024 by 1024, has a cadence of 40 minutes, which is quite great, but it's available every 4 days, so yeah, quite some latency when you get the data, which makes it not really useful if you want to like forecasting in real time and get warnings for events coming to Earth. On the other hand, the beacon data at the bottom is low resolution, 256 by 256, has a quite lower cadence, so 120 minutes, so basically you miss every 2 frames from the SENS data, but it's near real time, so you can use that for forecasting. So on the images on the right, you have a JPlot with both of the instruments, or both of the data types instead, and the images from this instrument. So our project is separated into 2 bits. The first part called Beacon to Sense on the left, which is what I'm going to talk about today. And there is a CME automatic detection and tracking, which is a poster from Meike. If you didn't see it yet, you can go outside and have a look at it. So the Beacon to Sense part basically is how can we improve this beacon data in real time, makes it higher quality with like more like apparent features in the images, and then how can we augment this cadence to match the SENS one and then get better forecasting from that. So it's composed of 2 neural networks, so machine learning. I know some people are not fan of it, but we use that for now. Which the first one is a GAN-based method, so denoising the images, increasing the resolution, and the second one is more flow-based, so basically doing interpolation between every frame to get 2 more frames, improving the cadence. So the first network is relatively simple. It's more like an autoencoder for denoising, with at the end of it, you have like a small module which is responsible for upsampling. As you can see, it's time 2. So we don't go full resolutions just to save a bit of resources and time while training the model, as we think that 1024 is a bit too much for forecasting. The second one is adapted from a paper from 2022 at ECCV, which is basically using flow between images to do interpolation. We just added an extra layer of interpolation with like this coefficient that allows us to interpolate at any time in between 2 images and be a bit more flexible about which time we would get from that, and also maybe get extrapolation, so future frames from the previous one we have. So in terms of quantitative results, just to go over it quickly, we get quite good results for the upsampling part. So if we just upsample the beacon images to the resolution of the SENS one, we get the results at the bottom part of the table, which are quite alright, but still, all the noise is still there. But once we apply our method, we get way better results, which shows that the images, you get more signal for the noise you had before. So this is the kind of results you can expect from this method and from the pre-trained network we have right now. So on the left, you have the beacon images, in the center, the enhanced version of them, and on the right, the science one. So as you can see, most of the noise is removed. You still get the stars because we didn't remove them from the beacon because it's quite hard mixed with the noise in this kind of data. But the fronts and the features from the CME are way more visible, even though it's not perfect and it's hard to know how much things should be visible as we don't have a science control in real time. Concerning the cadence upsampling, so as you can see on the top, you have the two beacon frames, which are coming at a 120 minutes interval, and we want to get the images in the middle, which exist or will exist once we get them from the science broadcast. So we apply our force network on that. We get the two images on the left and on the right, which are the enhanced beacon one, and then we get the two images in the center, which are then interpolated in between with this flow-based method. So usually it's like a third and two-thirds of the time frame, but because it's not really regular, and sometimes you have like some big mix-up between when the image is captured or not, then we can adapt these 1/3 and 2/3 coefficients for the interpolation. So yeah, let me explain. We get this kind of videos where on the left you have the beacon data, which comes at very long intervals, and on the right, the enhanced beacon one. I'm sorry for the resolution, it got compressed a bit, but yeah, the video is smoother, you get better features, you get a lot of the noise removed, so it's nicer to look at, and then it should be eventually nicer to predict and forecast with that. So for our model, which is a drag-based model, we use J-plots for forecasting, which is basically cutting a slice of the image, stacking them together, and then tracking along these tracks, which some of them corresponds to CME. So I've shown there like the different stages of the improvement, the enhancing of these images, with at the top, on the top line, the beacon data that we get in near real time from the stereo emission. Then next to it, we just upsample the images to the higher resolution with like less noise in the background. So as you can see, like some tracks are more visible and separated. So the CME from CIRs or like other things that comes with it. Then you get like longer tracks which then are more visible for the user to then click on them and track them manually. Then we upsample the cadence, so we fill in the gaps within the images. Not the big gaps, which are just basically missing data and are really hard to extrapolate from the existing data without using core or other viewpoints, which could be useful in the future. But as you can see, like the tracks are thinner, more precise, and easier to track for the user, and then to forecast the CME eventually. And at the bottom, you have the science. J-plots as like a comparison with what we get. So this is just a small animation just to show the improvement for it. Concerning the tracking, for all this kind of forecasting, for now we still have a user behind the screen which has to click on the J-plots and then run that through a model. Eventually we'll get that automatically done with Mike's work or other kind of automatically tracked J-plots, but for now we're doing manually. So the background is the science J-plots, and over it we show the tracks from the different instruments, or different data type, rather. So the beacon one in blue, the science in green, and the enhanced beacon in orange. So for this first example, you can see the orange match is a bit more the science one, which is promising, which is verified for other CMEs. So in that case, we can see that like the beacon is quite short, it's quite unpredictable and like hard to follow and a bit noisy in terms of where the points lie, while the enhanced beacon matches a bit more and is a bit more precise compared to the beacon. And this is true as well for other example, especially at the beginning of the tracks where the beacon data tends to oversaturate and it's really hard to get the kinematics at this point, like the speed and the direction from that. When we enhance the data, we see that the science matches as well a bit more to the enhanced beacon, which makes us think that would be a good thing to use for forecasting. So the conclusion for this first part is that we propose this denoising and upsampling method for the cadence and the images. We get better readability of the images, even just to make cool GIFs for Twitter is already nice. And then we get G-plots, and tracking on these G-plots makes quite a good improvement. For the future work, we want to actually do forecast on them. So we've compiled a small catalog of events, which actually arrived on Earth, and then we started to do tracking on them and forecasting about the arrival time of each CME, which for now is quite looking good, but hopefully we get that out soon so that we can prove that it works. And I talked about the extrapolation problem earlier on, which is basically filling in the gaps of data that never came to Earth and that will never come to Earth. And this is where core 2 might come in. So looking at previous data from like closer to the sun, then we can see if we can predict further on data in the heliosphere. So getting more HI data from that missing bit. And then eventually we want to extend it the full stereo instrument suite. So HI2 on top of that would be next as well. So concerning why this work could be complemented with other missions, especially Punch, thank you. We have Stereo A, which hopefully will still be alive by then, going to L4 in 26, 27, around that time. And it will be around like a nice 90 degrees position compared to Punch, which will be facing on the sun and the CMEs coming in it. So it will be a nice time to have like a double viewpoint for the CMEs coming and doing some forecasting on these events. And on top of that, there will be a nice way to get used to these two type of viewpoints because Stereo B is not there anymore. And then work for Vigil, which comes in 2031, so a long time from now, and maybe combine Vigil and Punch eventually. So that would look something like that, where we just enhance the data from Stereo, so core as well, and HI1 and HI2, and combine it with Punch data, so the coronagraphs from Punch data with the core 2, and the further away from the sun data with the HI data as well. And this ties up with multi-viewpoints kind of work, so moving on from like a single viewpoint, which is basically 2D, with more like 3D or 2.5D, I would say. So looking at the CME from head-on from the Punch viewpoint and combining that with the stereo will be on from the sides, doing tracking of the CMEs, and then looking from the polarized data, what the CME is and what actually do we see from this side view. So it's kind of mixing stereographic view with the two HI points of view, and also polarized, which is some kind of depth viewpoints from the observer, which will be Punch. And yeah, so if we look at, for example, coronagraph data, then projected into 3D, we get, it's very noisy because it's the beacon data, but we can still see a bit of the CME there. And it becomes more like a computer vision problems, but in 3D. So doing 3D segmentation, tracking, and detection adds on top the 2D tracking and detection that we want to work on as well. So in conclusion, most of it has been said during these 2 days, so it's quite nice to see that lots of ideas are shared, and seems to be like a good way forward with Stereo and Punch or other missions. So doing tracking and following the CME and segmenting it, seeing what are its features, etc. So from the Stereo point of view and so Punch. And also like inferring some properties such as the chirality, if we can do it automatically maybe with the Punch data, the polarized data, but also like combining as many spacecrafts as possible. So trying to like build some pipelines with data, so I know it's not everyone is a fan of that, but getting away from ideal, you can make sure that everything works with Python, have like datasets which are ready for people to use, because like people who have worked with stereo and or even stereo beacon know that it's quite hard to get their hand on the processing codes, on the data, make everything work, getting rid of the bad data, etc. So that's something that could be nice for users to just get ready to use datasets. And also combine that for machine learning, because treating data is a bit of a boring part. So if you can just run your exciting machine learning models on that later on, and with like open source code from GitHub, and maybe work with the SOC team as well, because it's always nice to have people to work with. So that's about it for me and the goals with Stereo and Punch for the future. Thank you.
All right, so let's first speakers come up to the. We still have Bernie and Hugh on Zoom. Hard to see if we have any.
Yes.
Okay. All right, we have the Slido talks, the Slido questions up. We can just sort of go through them in order, I guess. First one is from Shaheda.
I'll bring you the mic.
I just had a comment. Where is it? Okay. For the quick punch that Dan was showing, so I think it's not only can be used for forecast, but it can also we used to trigger observations from non-all-day solar radio observations. So there are some telescopes which are not completely dedicated for solar, but we need to give some triggers where sometimes we use SEEDS catalog or CEDAWeb CME catalogs, which are not real-time, and we have to wait like 1 or 2 hours to see if there is any CME happening. But in that case, quick punch can still be used as a trigger method.
So I think it'd be great to find lots of applications for the quick punch data. I think it can be used for many things beyond just, forecasts in the SWPC forecast office. The caveat is that, the data come a lot faster than normal punch data, but it still takes time to get them down from the spacecraft. We don't have a dedicated downlink like an operational mission does. So you're going to have latency that's hours. Maybe faster if the CME happens at the right time and we have a downlink planned. But so there's for some applications that you need to know right away, there's probably still some limitations.
Sounds good.
So next there's a question from Nariaki.
So Dan, so how bad the quick data are, in comparison with science data, in spatial resolution, compression, and temporal resolution. I often use the stereo beacon data. I really hated them because they look so ugly. But now, if you're interested in something real time, that's very useful.
Yeah, I kind of glossed over that in the talk. It's not like beacon data where it comes super compressed and degraded. It's intrinsically the same quality as the science data. We're going to reduce the resolution by about a factor of 2 because it makes it a little more compatible with existing SWPC tools, and it makes everything just work a little bit faster. But it should be really high quality. It should not be like trying to look at the stereo beacon data where your CME is a little tiny blob in a fuzzy, bigger blob.
Okay, Sarah has a question for both Bernie and Hugh. There's a mic right there.
So, question for both of you. Tomography is requiring multiple views on the same material, which may be done like through the rotation, or as what Bernie's doing, which is more of an outward mass conserving flow of the solar wind. But of course, in both situations, you have eruptions and time-varying things, reconnections that are going to affect that. So how do you deal with this, or how can you deal with this?
Do you want me to talk? Bernie.
Sure.
Okay. You see density, and for the reconstructions, you continuously monitor what's happening as the material comes out. So that adds to the 3D reconstruction of the analysis as things occur. So that dealt as material comes out by just redoing the line of sight reconstructions, and that works. It shows you what changes are occurring in the densities that are reflected by the brightness that's present there. Now, you can do that with the observables, and that's both brightness and speeds as things change. So as long as you can have a fairly high temporal resolution, you can watch the changes occur. And that's how at least the 3D reconstructions work. Hugh, you might want to reply to that.
My approach is quite different in that I assume a static corona, so any dynamic changes are a problem, particularly during solar maximum. I do apply quite an effective filtering on coronagraph data that actually separates the CMEs from the background corona. The only problem with that is that the background corona does respond to large CMEs. However, most times during the solar cycle, it works okay. Solar maximum, it doesn't. It's a mess. And that's a big problem for space weather, because solar maximum is the time you want to be most accurate. But the same problems are faced by magnetic models as well.
Thank you.
Okay.
Okay. Sorry, I'm going again.
Sure.
Yeah, so, and actually, Justin, you sort of answered it towards the end of the question. You're saying you want to do punch, but I'm kind of wondering, this relates to what Dan's saying as well, about like what could be done beyond, or how could it be used. And there's a bigger question here, which is also about the international connections between the different operational facilities, which is, how do you take quick punch and then use it in different space weather operational centers in different ways and enhance it and pass it around? Do you see this is something which has a smooth path forward?
I personally, in the UK, I see it as very smooth. Yes, at least for the sweep package, and I think in any space weather operation center, the forecasters are going to have punch data upon their screens alongside whatever other coronagraphs and EUV images are operating, because the more data streams they have, the more robust their forecasts. But certainly there's room for sweep and the sweep team to make things as smooth as possible for the operations center, I think. And it's really nice to see quick punch products, the low latency products. Those are crucial, of course. But whether we want to provide higher level products which people can use, I think that would be great as well.
Maybe to turn it to Justin then, the kind of enhancement you talked about, is that something you think you could perform on the quick punch data as described by Dan?
Yeah, I mean, I don't see any reason for not doing it, because data will be available and like quite quickly available, which is nice. And with the Python suite, definitely would remove some problems we had with IDL and such. And also like about sharing the data and making it available for people to use, etc. Like even if we have the model running on our servers, the data will be available straight away for people to use. And because OpenSense is really nice.
Can I butt in there? The Core 2 beacon data is far reduced in quality because of where stereo is for most of its orbit and telemetry. Punch, of course, doesn't suffer from the same problems, right? Am I right in saying that the punch low latency data will be far better quality than for example, the stereo beacon data?
Yes.
I think someone.
I'll answer your question, Hugh, and then I'll say something to Sarah. Yeah, so the data is going to be about half the resolution of normal punch data, but it's the same quality. It's the full scientific quality. You will not have the problems with compression that there is with stereo beacon data. Of course, at the same time, on I think it's Tuesday, NOAA's launching the first of their compact coronagraph instruments, and there'll be a second one to follow on the SWIFO mission to L1 a little later. So punch will be complementary to those data streams. And I think there's going to be really, really good, robust coronagraph data with backup. We're in an era right now where we're relying on rickety old LASCO, which launched when I shudder to say this, still in high school. That was a long time ago. And we're going to go to a place where we have 3 or maybe even 4 different really high quality coronagraph streams that are ultra low latency, real time, no compression, all that stuff. So I think we're entering a really great age for coronography. As to your question, Sarah, we haven't had these conversations about how to flow the lowest possible latency data to other folks. I don't think there's any technical barriers to doing it, but if people like you and Justin want to talk about it, we should talk about it now so we can set up those data pipelines to get the data to them. I think the data will be available to everybody pretty quickly, but probably not with the same latency we can give it to somebody who specifically asks for it.
What is the latency here? Just a question.
Yeah, so the latency of once we get the data, the latency is really low. It's going to be minutes. The bottleneck is getting the data down from the spacecraft to the ground. And during the initial demonstration of service, we're just going to run at the sort of nominal downlink passes as we're sort of working out the kinks and letting NOAA validate this. But there is a scenario where if NOAA wants to invest in more downlinks, you could have data at much reduced latency.
I'm going to jump in on that because I actually put it in the Slido, but we're not picky about the routing taken by our telemetry. So if Austria or the UK Met Office wants to supply more passes to get lower latency data, we will gladly accept them. I'd be glad to discuss it with you.
Yeah. The 3D reconstructions in theory can take less than an hour to complete and to make analysis. So, and as long as you can continue to do this, you can update as material changes as it moves outward.
Great.
But that's a big bottleneck currently, the latency with the interplanetary scintillation data. It doesn't have to be, it's just programmed that way currently.
Okay, I guess the next question is from Joan.
This kind of follows on to what Sarah asked. So this is, I have for Dan and Hugh, but it could be anybody as well. So of course I can envision punch images up in SWPC and the Met, but I'm wondering about the tools, because I can imagine it's an elaborate process to get to integrate those into the Forecasting Center's toolkit. Have you guys started working on that, or is that going to be post-launch kind of thing? Thanks.
I'll go first, and then Hugh, you can talk about your side of things. Yeah, so we're working on a pretty much daily basis with folks from SWPC to make sure the data meet the requirements, make sure the interfaces get the data where it needs to go. They have very complicated data flow requirements, and it has to move a lot of places. So that's been something we've been working a lot on lately. We've been trying to troubleshoot the data within their real-time, I mean, we're not putting it in their real-time systems yet, but the same tools they use in real time, and make sure that it loads up and looks great in the CAT tool and they can do all their analysis. And so, yeah, from the SWPC side of things, I think once the punch data are ready, they will be ready to work with them that day, pretty much, unless we really fall down in our job, and that's not my plan.
Yeah, for the sweep module in the UK Met Office, I literally think it would be an afternoon's work for me to plug in punch data as an additional data stream in that.
And, we're going to try to give the same high quality data and metadata standards in the quick punch data as are going to be in all the punch data. And so if you have tools that are compatible with standard, with FITS standards compliant products, they ought to just work off the shelf, pretty much.
Yeah.
Okay, I think we got Shaheda's question. Heather has one next.
Heather? Here.
Yeah, I was just saying that there's a plot on my poster that shows that if we can get the density and the speed of the solar wind that passes Earth, we can estimate KP, and which is used for the G5. So, and that works for CMEs or background wind, CIRs.
Well, let's get you the data.
What's the correlation approximately between KP and these other values?
Well, it's pretty high. I have I'll send you some stuff. That's probably the easiest. Okay. Yeah. Okay.
All right, Sam.
To Hugh, you showed this neat thing where you're using empirical acceleration profiles in your pipeline. I was wondering how you meshed that with HUX-T. Like, are you providing a V0 inner boundary, or are you like empirically correcting streams, or how does it work?
So HUX-T does have an acceleration profile imposed on the solar wind, but the official public HUX-T version has a constant acceleration. So if you plug in 100 kilometers a second at the base, it increases by 15%. Okay, but we're having different acceleration according to different speed wind, as you'd expect in the real solar wind. So we have our own version of HUX-T at Aberystwyth where we've implemented that change, but that version is not public yet.
Okay, so it affects the stream
But
interactions.
we do work closely with Matt Owens, who developed HUX-T, and hopefully he can implement that in time.
Thank you.
I was in the middle of typing a reply on Slido, so I'll finish.
I don't know if we can see the replies up here, but Gabriel has a question for Dan.
Where's Gabriel?
I think he's online.
Gabriel, are you there?
We can read it. So, any thoughts on why the G5 storm did not seem to cause the kinds of big disruptions that were mentioned in that matrix under G5?
Yeah, I think that's an area of active research, actually. This is not really the area of my expertise, but I understand that there was a combination of, some areas are more susceptible to geomagnetically induced currents than others because of the content of bedrock and stuff like that. And so partly it was just where the most intense storming happened was not places that are particularly susceptible, but I know that power grids did a lot of advanced mitigation. And so I think part of this is just good forecasting and better awareness and space weather working the way it's supposed to work. So yeah, I don't have a great answer to that. That's we need. I don't know. Maybe there's somebody who is
Well,
a Swipsy
there's
person who
also
wants to
some sort of
comment.
pile up at that high end. There's like G5 minus, G5 plus, right?
Yeah, I think it was not like the utterly catastrophic highest level of G5, but KP did get to 9, and so officially it was a G5 storm.
Okay. Nariaki has another question, or was that the one we got before?
Dan and the Punch team, you often talk about the tracking CMEs up to 80 solar radius. How often do you think you can do it? Because I looked at the HALO CMEs that caused the G5 storms in May. They're not very bright, In order for CMEs to cause geomagnetic storms, they don't have to be bright. The brightness really depends on how the CME moves in the plane of the sky. We're talking about the motion towards us, and is there any reason we can believe that, say, a punch is more sensitive to that kind of motion than LASCO, for example?
Compared to LASCO C3,
C3.
Punch NIFI is a factor of 30 more sensitive.
Factor of 30?
30.
Wow, amazing.
And Punch Wi-Fi is comparable. It's about 10 times more sensitive than High 1.
Okay, thank you.
So I think that there is probably a need for some advanced image processing and stuff. I mean, I think that it's not just going to fall out of the data, but I believe we're going to be able to do this.
Okay, Sarah had a question for Bernie.
A point of clarification, Bernie. There was on a slide, it said something about B and good PB, and you may have said something. I apologize if I missed it. But what did you mean by good PB?
Well, first of all, PB is a bit of a unknown here, and so I'm happy to see what happens in the heliosphere with PB. But you see, at Earth, for instance, there's the difference between at 30 degrees anyway, polarization, brightness, and brightness, because of the fall off. The PB signal is an order of magnitude lower than that present from brightness, and so you have to determine relative to the line of sight if you're going to use PB at Earth and figure out how far away from Earth things are. You have to go down to that lower level of brightness. Now, I know Craig has been aware of this and interested in it, but that's just one of the facts here. So you'll need a lot of throughput to be able to determine that, and to use PB all along the line of sight. Yes?
Okay. Craig had a question for Justin.
All right, Justin. So I saw the great improvements that you made to the J maps. What are you doing, or are you doing more to use the entire image to improve the J map resolution?
Yeah, I mean, this was meant like as a first proof of concept for the idea, seeing how far we can go with it, and then eventually go for the full thing, and then also have it real time running on our server for the full range of image. So yeah, definitely. That was just like a small showcase for it, and then we'll get the full thing running.
Pretty excited to see your results. It's cool.
Thank you.
Okay, Gabriel had a question about coronagraph latency. SEACOR has a requirement for 15 to 30 minutes, and this is because GOES has much more downlink, consistent downlink of data. We might have talked about this. Yeah, are there?
Well, yeah, I mean, I'll just say that, you know, the GOES, for people who are used to waiting for data from L1 or deep space, the GOES data that are going to come from SEACOR are going to be really exciting. The way that they're able to transfer data from GOES, which is in geostationary orbit and has dedicated satellites, I mean, they can get an observation from the spacecraft to the ground where it gets processed, then they bounce it back off the spacecraft. It goes into every forecast office in the country within a couple of minutes. And it's a different scale than people are used to. It's a different scale that we're going to be able to achieve with Punch even. It's very exciting. I mean, the GOES data are so fast that, you know, what they used to trigger the recent rocket flare campaign that ran last month. And, you know, within a minute of the flare starting, they know that it's time to launch the rockets. And so it's a game changer for space weather.
That's the same question than before.
Yep, I think we are done with questions.
Yeah, and I'll just comment that the reason I brought Sam's back, I wanted to let people know that there is ability to reply to these questions, and I put it back up because there was a reply going on actively, and also to let you know that we are archiving, and I'm going to archive this now, but eventually, probably by the end of the day or sometime soon, we're going to have all the archived questions and back. And Kelvin, can you confirm, can people continue to discuss on it? So yeah, so you'll be able to actually continue to respond and reply on these Slido comments.
That's great. Yeah. Well, let's give a hand to our 4 speakers in this session again. All right. So we'll come back at 4 o'clock for the final session.
As we file in, have a look up at the screen. We've thrown up a couple of AGU sessions that are coming up. These are the two major punch relevant sessions to respond to for AGU. So we have the top one is sort of the general punch session on combining coronal and heliospheric imaging data with in situ and modeling to understand the young solar wind, which is our topic. So thanks very much to Rohit, Raphael, Heather, and Anna for organizing that session. And let's all make sure that we get at least something in to it when the abstracts open up. The other is mesoscale structures in the solar wind and coronal mass ejections, which covers a good fraction of both working groups 1 and 2. So please feel free to submit there as well. And thank you to Bernie and to Nikki and to Mario for making that happen. This is going to be our last AGU before launch, and so we want to have a good presence there. If you are considering whether to go to AGU, please do. It's going to be a big splash for us just before we launch, sometime in the undisclosed future, in the months after that. So we're going to start out with, let's see, what's the title here? You get the, pardon me? Marta Casti's invited talk on the Codex Coronal Diagnostic Experiment and its
Relation to punch.
relation to punch. And Marta is right here. Excellent.
Hi everyone, thank you for having me here and talk about Codex. Very excited. So I'm a postdoc at the Catholic University of America, and I'm gonna talk about the coronal diagnostic experiment, which is another coronagraph and its potential synergies with punch. I wanna point out that this is just a chapter of a long story of measurement of temperature and speed that has been done first with during the eclipse, and then with BITSI on an experiment balloon, and now Codex on the ISS. But let's move forward, maybe. All right, so what is Codex? Codex is the coronal diagnostic experiment and is the next generation solar coronagraph. And he will combine for the very first time simultaneous measurements of density, temperature, and the radial speed of the electrons in the solar corona. It will be launched this year in September 2024, and it will observe the corona as an external payload of the International Space Station. The baseline mission of it is for 6 months, but can be extended up to 2 years. And the NASA Goddard Space Flight Center leads the scientific and technical breakthroughs, supplemented by expertise for the Naval Research Laboratory, the Korea Research Laboratory, the Korea Astronomy and Space Science Institute, KASI, and lately also the National Institute for Astrophysics in Turin, Italy, joined the project. So what are the science objectives of Codex? So the scientific goals are to trying to understand the physics of the solar wind in the acceleration region, and also to improve the forecasting methods for the space weather. So these are the questions that Codex would like to address. So there are signatures of hot plasma release into the solar wind from previous closed fields. What are the velocities and temperature of density substructures observed in streamers and corona holes? And we also would like to provide the first observational constraint for empirical solar wind models of electron heating and acceleration in the key region between 3 and 8 solar radii. The method. As I say, Codex is going to measure not only the density of the electrons in corona, the classical solar coronagraph, but also the temperature and the speed. The method is based on the theory formulated by Crum in 1976 and then extended by Reginald in 2001. I'm going to just give a very brief summary about the science and the method, but I would like to encourage you to go and see all the series of papers that Nelson Reginald Regional published since his PhD on this matter. So the polarized brightness is defined as the intensity, the total intensity in the transversal direction minus the one in the radial direction. And this, the formulation of Van der Hulst in 1950 and then taken by Billings in 1966 is show this intensity as a function of the electron density. What Cram did in 1976 is to take in also into account the kinetic temperature of the electrons. And this is what we see. So the profiles is not anymore, the polarized brightness profile is not anymore a single line, but it separates for different temperatures. What Reginald did, I'm sorry, and this is giving you an example. So in red, you can see the polarized brightness as a function of just the electron density, while if you take into account in your equation also the temperature, you will see that there are different profiles for different temperatures, and when the temperature is converging to zero, you can find the same formulation of Van der Hulst and Billings, so just with the electron density. What Nelson Reginald did in 2001 was to also include the speed of the electrons in this equation, and I'll show you how this changed. So let's take, for instance, the profile, the polarized brightness profile at different temperature, of course, with the speed of the solar wind equal to 0 for two different heliocentric altitude. As you can notice from these two plots is that for the two different heliocentric altitude, the profiles look kind of the same. And also, you can see here 3 different places that are circled, like 1, 2, and 3. And those in the Cram paper are called the nodes. And you can also observe that the position of the nodes is the same for different heliocentric distances, in the sense they refer to the same wavelength. So the major takeaway for this slide is that the intensity profile changed with the kinetic temperature of the electrons, and the insensitive nodes are also independent on the line of sign. Let's move forward and let's consider again, here is the same heliocentric altitude, but 2 different speeds. We can still see the same profiles, so the temperature changes the profiles, and we can still see the nodes insensitive to the temperature. But you can notice that the position with respect to to the wavelength has changed. And the major takeaway here is that the temperature insensitive nodes shift with the increasing of the solar wind speed. So we would like to take advantage of this, and what has been introduced, what was suggested first from Cram, by Cram in 1976, and then from Reginald for the speed, is using the filtration technique. So basically acquire measurement of the polarized brightness in those areas where the curve change, to have a measurement and derive the intensity, and derive the temperature and the speed of the electrons in corona, using the ratio of these 2 measurements. How do we interpret the ratio? So interpreted the ratio is explained still in this other paper from Nelson Reginald, and it gives you, so basically when you try to you use this formulation, this equation on top, and you change the temperature and you change the speed, then you obtain these 2 curves when you also consider the temperature ratio and the speed ratio. So a thing that you can notice here is that while for the temperature is easier to find a temperature for a measure ratio between these two measurements of temperature, to acquisition of polarized brightness intensity actually, for the speed is a little bit more trickier. So if you notice, for instance, between 200 and 400 kilometers per second, the difference among these four curves is very is little. So what has been estimated is if we are able to measure to acquire the measurement with a 1% of uncertainty, the uncertainty of the temperature is going to be 0.2 mega Kelvin, while the uncertainty of the speed is going to be 200 kilometers per second. So it's not very, I mean, it is a huge uncertainty. Where Codex is going to do these measurements, so here you can see the previous measurements that has been done of the electron temperatures and the outflow speed in corona. And as you can see, between the previous measurement that has been done in history in the time and the closer Parker Solar Probe approach, there's a gap. And there, in that region is where Codex measurement is going to fill and try to fill that gap. Let's talk a little bit about the payload. Codex is a two-stage externally occulter coronagraph. It has two filter wheels because, as I say, we need at least 4 filters, and then we also have another broadband filters that cover the wavelength, the entire wavelength range that goes from 385 to 440 nanometers. And also we have a calcium additional filter and another filter for temperature. So there's a lot of filters. So that's the reason why we have 2 filter wheels. Also, for the first time from space, Codex is going to acquire images of the K corona with a polarization sensors. And it has been done previously from ground, and this is the first time from space. And as I said before, Codex is going to be an external payload of the ISS. The ISS, of course, is orbiting around her. So Codex also need a pointing system to ensure that the coronagraph is always pointing the sun when the sun is in visibility. Well, the challenge of the payload is that to achieve, so in this plot you can see that there's a lot of noise. So the red and the faint green lines are our signal, while all the other lines are the noises. So the unpolarized F corona is noise for us, the diffracted light is noise, the scatter light is noise, the polarized F corona is noise as well, the vignetting, and so there's a lot of noise. And another thing is, if you remember, the wavelength range goes from 380 to 440. So we are in the lowest part of the visible range. So not a lot of photons there. So for this reason, there has been a couple of strategies that has been implemented in the optical design to try to increase the signal and lower down the noise. So for instance, we have a larger A0, so the aperture is larger with respect to the other coronagraph that work in the entire wavelength, entire white light range. It is almost 170 millimeter. Then we have a focal mask. While the classical coronagraph, they have only they block the sunlight and the diffraction. With the external occulter, the internal occulter, and the Leo stop, Codex has also a focal mask that with a goal of trying to block more the diffracted lights, and so the stray light from the instrument, and so noise, a source of noise for us. Also, as I say, Codex has a polarization camera, so that fact that we are measuring polarized light is to try to avoid the unpolarized F corona. And also, we are going to, while the superpixel of the polarization camera is 2 by 2 pixels, codex superpixel will be 4 by 4 to bin the pixels and try to increase the signal. Of course, well, the spatial resolution is sacrificed in this way, but we're not, our science goal is not to observe the fine structures. So it's a sacrifice that we're willing to make. So now, codex and punch. Now, there are 2 scenarios where codex and punch, we're gonna work at the same time. And and the second scenario is if codex has this mission of 6 months and it doesn't be, and it's not extending. In the case of overlapping in time, we can consider, we can use the 2 instruments. First of all, the synergies are that in the overlapping field of view, we can go and see the relationship between the solar wind density structure and analyze the velocity and temperature with codex and the structure with punch to test the solar wind formation theory. When we use the field of, field of view combination that goes from 3 solar radii to 180 solar radii, we can track the solar wind structure, and we can see in the codex field of view, we can see their development and their evolution in terms of speed and temperature, and we can see in the punch field of view the evolution in the structures, in their structure. What happens if the 2 missions do not overlap? Well, we can still use codex velocity measurement to test punch optical flow algorithm. And we can determine how much solar wind is comprised of a constant flow versus how much flows is intermittent. So I'm gonna leave with the conclusions. That is a recap of what I've said. And that's it. So go codex and go punch. Thank you.
Thank you very much. Remember, we're holding questions till the end. So next we will have an invited talk from Samaya Farid. Samaya is coming up. This is on dynamic flows and jets in the middle corona, a topic that's on everybody's mind, it seems.
Hello, everyone. As Craig said, my name is Samaya Farid. I recently joined the Punch team as an AI associate investigator. My primary research background is in coronal jets, and this talk is going to be a little bit about how observations of coronal jets and the tools that we've developed can be used to connect the solar wind early in the young solar wind to the features that are absorbed in like core 3 and that will be observed in punch. A lot of this this work has been done in collaboration with a bunch of different people and also some of the summer students that I've worked with. So, recap of what coronal jets are. Coronal jets are small eruptions that appear throughout the solar cycle. They're nipping across the disk. They frequently occur about 60 coronal jets in a coronal hole per day. But keep in mind that this is only for X-ray coronal jets, and these are for X-ray jets of a certain size. And so when we talk about whether or not coronal jets can contribute to the solar wind, we have to remember that coronal jets come in a variety of small sizes. A lot of those are much smaller than what we have typically kept record of. The velocities of jets can be anywhere from 100 to 1,000 kilometers per second or more. And they are often observed further away from the coronal, the low in corona. And this last picture here on the slide, let me see if I can. Okay, I don't know how to do the pointer, but okay. Yeah, doesn't work. That's okay. The lower right-hand corner shows that a jet can be traced sometimes from the low corona all the way out to LASCO C3 field of view, and that these are often could be traced back to these jets and often thought to be able to hold the structure continuously from those points. All right, so some of the observation techniques that we've used to understand the acceleration mechanisms of coronal jets include things like line of sight and plane of sky velocity measurements, iris spectroscopic measurements to understand the components of the jet and where maybe reconnection points lie. Also, we derived a new method of using differential emission measure, convolving the differential emission measure to determine how much temperature per AIA channel is being contributed. So it's a new way of developing a temperature per AIA bandpass that we can then use as a diagnostic for coronal jets. So why we can use this is because a lot of the MHD modeling that has been done provide constraints to the types of, can be distinguished using observations. So for instance, in the image on the left shows what happens in a slingshot-only jet when the jet is only accelerated using the magnetic field strength. After reconnection happens, the magnetic field reorganizes and the magnetic field tension accelerates the jet. And we can look at that model and expect to determine what velocities and temperatures and plasma distributions we expect to see. Similarly, in untwisting jet, when there is a filament present, this jet predicts a different type of plasma distribution, and it also accounts for things like torsion alpha waves. So in this case, in the evaporation jet case, we can determine from observations which acceleration mechanisms are responsible for jet acceleration. And I'll just say for the evaporation case, it's mostly due to chromospheric evaporation, which is something that is commonly attributed to happen during flares. And during that time, the reconnection, the jet is accelerated because of the pressure gradient. So that's definitely a distinguishing characteristics of these jets, because then they will have a more like chromospheric-like plasma distribution. So also we developed this technique, the nonlinear force field model, has been commonly used to understand how the topological magnetic field evolves for active regions and for large features like filaments. But we also applied it to coronal jets, so very small filaments, and we found that we can predict, we can understand how these jets evolve and where the energy is being stored and released, so the X point in this jet. This graphic shows how the nonlinear force field model works. We begin with a HMI line of sight magnetic field, although we can also use the vector potential field, the magnetic field. We insert a magnetic filament, we trace the outlines of the magnetic filament depending on the observations, and then we allow the model to relax using magnetofrictional relaxation techniques. And the result of that is an idea of where the reconnection is taking place, and from that we can understand how much energy is stored in the field, how much energy is released, and what does that say about the plasma there. So in combination of both nonlinear force field models and observations, we've been able to determine the acceleration mechanisms for several jets that we've worked on. And when I say the acceleration mechanisms, meaning the dominant acceleration mechanism. Of course, of the three, any of those in combination can be a factor, but these we've determined to be the dominant factors that are causing the acceleration of plasma with jets. So for instance, in the graphic on the right-hand side that shows the movie, you can see, if you can sit as the movie plays, you can see the actual location of the X point. This is where the magnetic field diverges and where we think the most likely place of reconnection is happening. So in the background of that same movie is the emission measure of the jet. So emission measure is diagnostic for the density of that region. And so what we found in this case, for instance, that we found that the density, the emission measure evolves quickly, and the lines that were associated with the strongest emission measure are also the ones associated with, can be traced back to the region of magnetic reconnection. So that shows how distinguishable these acceleration mechanisms can be using a combination of nonlinear force field modeling and observations. So from this, we can understand the acceleration mechanism for these eruptions, jets, including also the filaments, as I mentioned, in active regions, also the topological evolution, like the X point, and the regions where the current density has built up strongly. Also, we can understand how the magnetic field configuration can support additional eruptions. So in the case of reoccurring jets, flares, reoccurring CMEs, streamers that reform, we can understand how much potential energy is remaining in the system and how much energy is released during that eruption. In this case, one of the jets that we see on the upper and the middle region, we found that the potential energy released after during the eruption, but there was enough substantial potential energy to sustain another eruption. And it did actually end up erupting several days later. Okay, so white light jets. So white light jets are observed, like I said earlier, in LASCO C3 and with coronagraphs, but they're not necessarily the same as UV and X-ray jets. There are some correlations. Some EUV jets can be traced to white light jets, but not necessarily the opposite is true. That some ideas about some of the reasons why we can see some jets through LASCO C3 and rather than see them terminate, is that some of these jets are maybe like narrow CMEs where the field is completely organized, and so that the field becomes open, and so the jet material can escape from much further. Also, there's some idea that jets could be a source of the solar wind, and that the perturbations that we see in the young solar wind and in the LASCO C3 could be coming from the smaller eruption of these jetlets. Also, may be possible that these jets could be a source of switchbacks in Parker Solar Probe. Although the jets, like I said earlier, they only occur around 60 per day, and on the scales equally distributed across the disk, while Parker Solar Probe switchbacks tend to be on the scale of the supergranular size. So there's some needed theory to understand how these small jetlets are related to larger jets and how they can be understood as sources of switchbacks. Also, there's some suggestion that these jets could be sources of extended blobs that we see in the young solar wind. So one of the punch goals is to determine where these regions of density fluctuations that we see in the young solar wind, such as puffs and blobs, and where they originate from, and how to connect them back to the source regions in the corona. Also, determine if these perturbations are generated further out from the corona, or if they are generated because of eruptions lower down. So in this case, MLSO fills the gap once again. I'll see Jones' poster to understand the comprehensive way that MLSO data can help with punch analysis and understanding this region, the middle corona region. So specifically for K-core, let me see if this is a movie. Okay, great. The K-core was designed specifically to understand how dynamics and CME eruptions evolve, and how the overall global magnetic field open and closes in these large structures over time scales of seconds to decades. So K-core images the polarized brightness in about 15-second cadence, and it's very useful for this type of study where you want to understand the connection between the solar wind generation and these dynamic structures. So again, MLSO data connects the middle and outer corona, and we want the goal of The goal here is to understand how these structures are connected to the structures that were observed by DeForest and Vial, and how these blobs are generated, if they're generated further away or they're generated close to the field. And I'll get to the point. So we've done some preliminary data analysis of this. So we've tried to first identify where these flows and eruptions, how they behave close to the corona and the lower corona. And we've done this with a few jets to start. You can see on the upper panel, this is AIA data in 304, and on the lower is K-core polarized brightness, tracing these two different jets that appear as jets in EUV data. If you notice, the one on the left is very different from the one on the right. The one on the left actually is does not appear to be a jet in a lot of the AIA channels, but actually it turned out that jet was much hotter and much faster than the jet on the right, which we would normally call a blowout jet because of this broad chromospheric spire. So, and further analysis of the jet, like I said, we can use some of these tools that we've developed to try to understand this acceleration mechanisms, to understand the plasma that is escaping from these open magnetic field regions. The velocities of this jet vary depending on the AIA waveband that you're observing, and also the K-core waveband, polarized brightness. So you can see on the upper region, the velocity is around 500 kilometers per second, but for the lower region, they reach velocities around 700, but on average around 300. When you add in the K-core data, you see that the velocity is actually around 1,200 kilometers per second near the, in the lower corona, and for the jets that were much hotter. So what do we need in order to really address this question of connecting perturbations and flows and jets in K-core data to observations of perturbations in the outer solar wind? Well, we've heard a lot about enhanced feature tracking, and we should we need a more comprehensive way to track these small fluctuations along with non-universal field modeling, because that can tell us how the magnetic field is actually changing in small spatial scales. When we combine that with large magnetic field modeling, for instance, from PFSS model, we can see how that global structure is impacted by these small small fluctuations. Okay, I'll leave a summary here. Basically, we see that there is much study needed to understand how these small perturbations in the lower corona connect to these the extended corona, and that it seems from a small study that these jets are much hotter and much more faster than typical jets. That is all.
Thanks for a really evocative talk. That's very good. We'll come back with questions afterward. Right now, we're going to move on to Ji Zhao, who's going to give us a talk on the ASOS mission and future synergies with Punch. And I'll let you know when there's 5 minutes left. Thank you, Ji.
Hi, everyone. Thanks for the opportunity to introduce ASOS mission here. ASOS stands for the Advanced Space-Based Solar Observatory in China. It was launched October 2022, and it opens the era of comprehensive space solar observations in China. So here I'll talk about the status and some early results from ASOS mission. And this talk is given on behalf of ASOS team. And I'll also talk about the future synergies with Punch and other chronographs. Oh, yeah. Okay, so my talk will include 3 parts. First, I'll introduce the ASOS mission and the 3 pillars. And then I will talk about the browse, download, and analyze of the ASOS data. And at last, I will talk about the coordinate observation with punch and other instruments. So first is the overview of ASOS mission. So the scientific objective of ASOS is the transient event, which is a flare and CME and the source region of these transient events, the magnetic field as a source region. So we have three payloads: the full disk magnetograph, FMG, the hard X-ray image, HXI, and Lambda Alpha Solar Telescope, LST. ASOS has a sun-synchronous orbiter at the altitude of 720 kilometers. And the three payloads, FMG observes the photospheric magnetic field, the LST observes the white light and Lambda Alpha image on the disk, and also the Lambda Alpha and white light image in the chronograph. And HXI observes the hard X-ray spectral and hard X-ray image. So the three payloads work together to give a full picture of the solar eruptions, and to the FMG get the information as the photosphere, the magnetic field, and through the extrapolation, we can get the three-dimensional magnetic field in the source region. And the hard X-ray observes the emissions of the thermal and non-thermal structures, and LST observes the flare and the outward propagating CME structures. First, the HXI. So HXI will observe the thermal and non-thermal structures. The thermal emission is mainly from the plasma, which is heated to a few McKelvin to a few tens of McKelvin. And the non-thermal bromstolone emission is mainly from the energetic electrons at the foot point of the hot loop and also at the loop top. And the main purpose is to observe the solar hard X-ray spectral and images to understand the energy release and plasma heating, as well as the energetic particles generation and propagation, and finally the magnetic reconnection. So this is a parameter of hard X-ray image. It has an energy range from 10 to 300 keV for the spectral and 15 to 284 keV for the imaging. The spatial resolution is around 3.1 arcsecond. And we have 91 sub-collimeter, which makes the image much better. And here is some result from HXI observations. The background is from AIA and the counters are from HXI. We see there are good correspondence between the thermal emission from AIA and also the non-thermal emission from hard X-ray as a foot point and also as a loop top during the flare event. And next is the FMG, the full disk magnetograph. It works at a spectral length of 532.4 nanometer, and the spatial resolution is around 1.5 arcsecond. So here is some result. We compare our observation with HMI, and here shows the curves at the place that as a right vertical line that we sampled, and the long-side magnetic field from FMG is comparable with HMI. And here shows the magnetic field, long-side magnetic field before and after the flare event, and you'll see, oops. So you see there's evolution at this region before and after the eruption, so it looks good. Okay, the last instrument is Lambda Alpha Solar Telescope. It includes 3 instruments. So the solar coronal image, SCI, the solar disk image, SDI, and white light solar telescope, WST. The WST work at 360 nanometer and observe the full disk from 0 to 1.2 solar radius, and the SDI works at 121.6 nanometer, the lemma alpha line from 0 to 1.2 solar radius. SCI UV works at similar line, hydrogen lemma alpha, and have a field of view of 1.21 to 2.5 solar radius. And SCI white light works at 700 nanometer, has the same field of view of SCI UV. And here are some results of our observations. On the left is the result from SDI. So this is a running difference image. We see the lemma alpha flare and also the waves on the solar disk. In the middle is the white light flare. There is here. And on the right is a spectacular prominence eruption in our field of view of SCI. And for the disk image, we have high dynamic range image from the high gain image and low gain image. And by combining them together, so we can get a high dynamic image for the flare event. And here are some other spectacular prominence observations in the SCI lemma alpha. And here's a movie. We observe this prominence eruption in dual wavelengths. Left is in white light and right is in the lemma alpha. But the disk image is both from lemma alpha. And we see prominence very clearly in lemma alpha chronograph. And we also see the core, the cavity, and the front of the CME in the white light image. And here is another event of the prominence eruption from the dual wavelengths. So again, we see the three components of the CME, and we see the prominence in SCI UV. We also do the synoptic map from SDI observation, which can provide the incident low atmosphere lemma alpha emission for investigating the emission in the corona in lemma alpha line. And next, I'll talk the browse, download, and analyze of ASOS data. So the image you can browse from the link here, and you can also download the data here. The data is released since April 1st, 2023, and you can also find the user guide here. And the software used to analyze our data can be obtained through the website or through the Solar software. Here is some example. On the left shows the daily image. The daily image on the left is a lemma alpha disk, and on the right is a white light image. And also the daily movie on the same website. And also you can download the data from our website. You can choose the level of the data. You can choose the burst mode or the routine mode. Okay. And we also provide the cutoff service for our data. And the coordinate observation. At present, we have the coordinate observation between SOS and hard X-ray and the solar orbiter sticks. So if the sticks is in between the Sun-Earth line, which has the same field of view with HXI, we can do the cross calibration between these two instruments. Once the sticks is off Sun-Earth line, we can do the research of the anisotropy of hard X-ray for the flare event, which is undergoing. And we also have the coordinate observation from LST and Solar Malis. On the top left is the SDI movie. We see the prominence eruption here. And this one shows the AIA movie. And this shows the image of a lemma alpha chronograph. On the bottom shows the CME event in Malis observation and also LASCO C2. So this coordinate observation is still under analysis. We look forward to the future coordinate observation between LST and the Mauna Loa Solar Observatory. Here I show some examples that we are investigating. Yeah. On the left corner, there is a very weak prominence eruption in Keiko field of view, and we see some blobs movement. So we do a preliminary analysis of the cloud sky velocity, use LCT tracking method, and we do see some blobs going down and going up into the background of the streamer. So it's very interesting. We also check the observation from AIA and UCOMP. UCOMP provides a Doppler velocity in this region and also the line width in this region, linear polarization. And we put the intensity enhancement on top of the linear polarization, on top of the line width and Doppler velocity. We see the good correspondence between these structures in the mid-corona. And this event is on the day that a few days before the volcano. And this is the first day that we got the observation from ASOS. So we look forward to future observation from Mauna Loa Solar Observatory once it is in operation. And last, I showed the prominence eruption that observed with AIA and then with ICI Lamarfa and then with LASCO C2 and C3. So this one shows a consecutive observation from the solar surface into the mid-corona to the interplanetary space, which is very promising in future to study the physical property of the prominence eruption. And on the right is a simulation, which we found quite similar to this eruption because we see the rotation of the prominence. And we also show the axis of the flux slope rotation in the simulation. And we also look forward to the future coordinate observation with Punch. Yeah. Okay, this is the last slide. This is an advertisement from ASOS. So we have a program which called AGIP. AGIP provides a research program who is encouraged to visit for 2 to 3 months at Nanjing at Purple Mountain Observatory. Yeah, so Nanjing is a really beautiful city, and yeah, this is a Confucius temple, and this is Mingshaoling, which is quite beautiful during fall. So if you have planned to visit China, this could be an opportunity. And last is we have a special issue of SOS mission at Solar Physics. We have the instrument paper and also some first result of our observation. So if you are interested in it, you can find on the special issue. Okay, that's all. Thank you.
Wow. Absolutely great data. Thank you. Next and last but not least, we have Michael Kirk, who will be talking about solving the sun with sunset and punch missions.
Yeah, we're going to solve it all right now. So first of all, thank you for having me at your meeting. I have nothing formally to do with Punch, but I'm very peripherally involved with Punch. Like I just sort of dance around the outside. So I've had a chance to wear a lot of different hats here. I'm going to put on my final hat of the conference and talk about the Sunset mission. Unfortunately, the project scientist couldn't be here. Dan just left instead of, and so I got, low man on the totem pole. I get to talk to you guys. So we spent all our money on these graphics. This is it. It's the whole mission right here. No, the Sunset is the mission, the Sun Coronal Ejection Tracker. It's a bit of a tortured acronym, but it is a CubeSat mission that we are super excited about. We're in the final stages of build and vibe testing right now, and it's a 6U CubeSat. Our target launch date is June or July 2025. A lot of you are on as COIs on this mission. If you didn't hear, we have a targeted ride share, the SpaceX Falcon 9 Transporter 14. So that will put us in an orbit that is at about 550 kilometers at an inclination of 98 degrees, a sun sink, which means we will be have frequent eclipses. If you know of a better ride share, please get in touch with our PI, James Mason. The prime mission is 8 months long. This is just a CubeSat mission, so it's a short duration. We'll extend it as far as possible, as much as we can, but we have 8 months to do all the amazing science. The field of view for this is plus or minus 5.34 solar radiuses by 4 solar radiuses. We'll get into that in a second. It's wide. We'll just say it's a wide screen. Also, our bandpass is also a bit wider. We're focused in the EUV between 170 and 200 angstroms. Our dynamic range, 2 times 10 to the 6. This is a couple orders of magnitude better than what SDO-AIA is doing, with a spatial resolution of about 20 arc seconds. Our exposure times and cadence, there's some nominal numbers up there in the subsequent slides. I'll go into these a little bit more in detail to explain exactly what the heck is going on with this instrument. In general, there's a cartoon that's up there on the screen as well to show a little bit of the schematic, what we have on board on this satellite. So, why did we do this? Okay, let's take a step back. That's sort of the high-level summary. Let's get back into exactly why are we launching this CubeSat and what we're hoping to do with it. In general, this is a synthetic observation of sunset. In general, what we're looking to do is target that acceleration of coronal mass ejections and really track it from the near corona through the mid corona and then into the near far corona, well, through the mid corona at least. So historically, there's been an observation gap between space-based EUV missions that are imaging on disk, and then when you pick it up into space-based coronagraphs, there's a large gap here. Unfortunately, that large gap has a lot of cool things that happen in that gap. A lot of the CMA acceleration, a lot of the any sort of deflection happen in this this gap that's indicated by this dotted circle here. If you'd like to read a little bit more, there's papers down in the corner that I'll be referencing throughout all this. So if you'd like to read a little bit more about the motivation behind it, please check out the references. So in general, the target of this are CMEs. CMEs, of course, are incredibly energetic. We're talking about 10 to the 25 joules. That's in comparison, if you want a quick comparison, to the one that the asteroid that killed the dinosaur was a couple orders of magnitude smaller than that. So these are highly energetic eruptions. But the triggering mechanism for these highly energetic eruptions it's controversial. There are a lot of different models out there for how these energetic processes happen. So there have been incredible amount of work done by the community, over 26 review papers, more than 75 papers doing deep dives into how these eruptions are triggered and how they're accelerated. We have a lot of competing models, torus instability, helical kink, breakout, slip running, but we lack observations to actually distinguish between these two because of this observation gap, this consistent observation gap. And so each of these models can provide a distinct kinematic profile for how the CMEs erupt off the surface and how they actually get transported from the low corona through the mid corona into the outer corona. And using sunset, we hope to distinguish between these. What's interesting is that we have also have a wide distribution of CME speeds, and that's what the plot is showing you on the right there. On the x-axis of that histogram there is the speed of CMEs in kilometers per second, and then there's the number in the histogram form up on the y-axis. And the vast majority of the CMEs have a fairly narrow range of speeds. However, the tail is quite long. So some of these CMEs erupt quite quickly and move through imagers, especially near corona imagers, very fast, too fast to make more than 1 or 2 measurements. So what we are looking to do is expand that discovery area to include more of this space, both physically and temporally, to be able to distinguish between some of these eruption mechanisms. So, for example, the helical kink eruption mechanism for CMEs has a distinct acceleration speed and height profile that is different than, for example, the torus instability and with velocity perturbation, with those two plots reflecting the height, and then the middle plot is speed and the lower plot is acceleration profiles of each of these different models. They have distinct signatures to them, but historically we haven't been able to observe them. The sunset field of view will capture this area, including also what's interesting is CME deflection. There have been a lot of tremendous efforts that have gone into back map where CME deflection may have happened based on structures, based on modeling. Hopefully we will be able to observe this a little bit more directly with sunset. So, how are we doing all this? This sounds all good, but how are we actually putting this together? This is it. We're using a high dynamic range detector. It's a CMOS detector with an algorithm to read it out in an interesting way. So what you have here is a simulated data in that image of the sun with the red areas and the blue areas and the green areas read out at different, or read out and medianed in different ways, okay? The CMOS detector that we're using doesn't read out pixel by pixel wise, we're reading out column by column wise, which is why you have this interesting stripiness to the image. But what we can do is expose the red areas for 15 seconds at a time, while exposing the blue areas for, bless you, for a shorter amount of time, or for a mid amount of time, and then the green areas for a short amount of time. So the inner rows are read in this sort of long, short cadence, as you can see by the blue timeline on the bottom, versus the red ones are read out in much more of a consistent 15-second cadence. So what ends up happening is we get this interesting data product where we have a long duration exposures where the disk itself will be way overexposed, and then we take a series of short exposures to get that exposure just right for the disk every minute. So every minute we go through this run. Of course, then we have to do some compositing on the ground, or which fortunately we can do. We're going to get all of our data down. So we're going to do medians of these different campaigns, these different imaging campaigns, to beat down some noise and to get the final data product. This is the actual bench proof of concept. That was neat in theory. This is actually how it has worked with bench optics. So you can see here there's the electronic suite on the left there with the compact spectral imaging electronics, the detector pinhole, and then we have an ND filter and a laser to simulate what we would see on orbit. And the results of that you can see there on the right. With that green that green blob in the center being the medians of 3.2 second exposures, and then with deeper exposures surrounding that in that stripy readout pattern. You can see in the middle image some specific dots that we picked out to show the intensity and how that falls off with the distance from that light source. And so this, in this bench optics model, seems to work pretty well. So that was really the origin for launching this on a CubeSat. All right, so in to model this even further, Dan Seaton and Matt West and James Mason really have done a lot of instrument simulations, and this has really been a major effort of theirs. And so what they're looking at is, can we actually see dynamics that we're hoping to see using this setup? And these are the simulations that they've come up with using the detector statistics, as well as using the best modeling that we can for CME brightness and acceleration. And so what you can see here is the two cases where we have a faint CME, the worst case that we were expecting to see on orbit, and then a bright CME, and we're able to resolve both. We're able to actually get enough signal to noise to see both of them and to actually track a CME front in both of the extreme cases, both the bright and the dim CMEs. This is what it looks like. Well, this was a few months ago. So we are using a Ricci-Cretin telescope with some significant baffling, as you can see in that cut there on the left. Those baffles actually ended up being really critical to the design. We went through all of this this effort to understand stray light and to be able to really capture what stray light we're expecting in the telescope, and those baffles end up saving us. And so if you are designing an EUV telescope, I'd recommend putting in lots of baffling. That really saved us in the design. So you can see a ray trace diagram on the right, and in the center there's a gloved hand to show the scale size of the telescope. It's a soda can size-ish, so it's a fairly compact design. This design has quite a bit of heritage. It's been flown many times before, so it shouldn't look completely novel to anybody. So, what can we do with punch? Well, this is where it gets really exciting. The wide field imager, of course, you have a tremendous context for the heliosphere. With the near field imager, you get some great data, but there's this nagging black circle in the middle. We can fill that in. We're not, it looks like, based on the numbers I've heard at this meeting and getting clarity from people, I don't think we're going to have much of an overlap. We may have a very little bit of overlap in terms of field of view, but what you can see there on the right is a sunset field of view with simulated data going from the corona, the inner corona, all the way out to 5 solar radii. The absolute extreme is 5.34 solar radii. That's the corners of that. It is a wide field imager, so as I was talking about before, the X direction is a little bit squat, or is a little bit wider than the Y direction. We're a CubeSat, though. If you want to have a different orientation than that lined up on the ecliptic, we can do that. If you want to rotate it by 90 degrees or something like that, we can do that. And so that's the kind of discussions that we'd love to have right now, because we have that flexibility to try out some cool stuff. Just to round this up, the exposure time and cadence are listed here. We're going to have nominal 1-minute cadence for sunset with a 15-second cadence max. So we'll be able to capture some of these fast accelerating CMEs. That lines up nicely with NIFI and WIFI. I think we can make some really nice data products to pair these together. Let's see here. So last of all, we're going to be releasing this data as levels 1, level, and level 3 predominantly to the public, making it available on websites for download as FITS, NetCDF, and ZAR to begin with. We'll look at other formats as well. So what data products would you like to see? In fact, I'd like to announce a new data product that I just came up with here, which is the Sunset Unified Coronal Kinematic Enhancement Repo with punch, or sucker punch. I think we can make it happen. So thank you very much, and happy to answer questions.
Folks would come up to the front. I'm going to hand over to Sarah.
All right, yeah, all of our speakers. Excellent. I think I'm just going to do the questions from down here. So we have some stuff on Slido. Please add, folks. Thank you guys for taking us home with a really excellent session. Okay, the first question on here is from Rahul. Rahul, do you want to? Oh, I guess nobody's running the mic. Oh yeah, I guess we can't. Yeah, just grab one of those maybe.
Okay. Yeah. Hi, Samaya. Nice talk. So, I had two questions blended in one. So, the first one is about the NLFF extrapolations for the jets which are near the limb. So, at the limb, the magnetograms are having projection effects, which can kind of affect how we model the jets and the field lines. So, what do you think about it? How easy or how difficult is it?
For the ones that we've done so far, so there's two possibilities. You're right, near the limb it's more difficult. So what we've done is, especially if they're near the west limb, we can look at the magnetic field a couple of hours or a couple of days before, and a lot of times it's surprisingly steady, and then evolve it going forward. And then most of the jets that we've done so far have been on disk or with enough resolution that we feel confident in the magnetogram.
Okay. And my second question is these switchbacks and the small jet kind of features. So they do originate near the active regions or in the lower solar atmosphere. And the corona, they have to pass through the corona, then to the middle corona, and then come to the interplanetary media. And corona itself is highly inhomogeneous and dynamic. So how do you think these features would survive the inner corona before reaching to middle corona itself?
Yeah, that's a good and reasonable question. The short answer is, I think the theory that Alpha and Sterling and Runmore stick to is interchange reconnection. When the field, the origin of these events are twisted flux ropes, and when these regions experience interchange reconnection or reconnect, they impart the twist onto the field, and that field becomes an open field, and then that the twist moves at an alpha speed, so because the alpha wave along that magnetic field line. Okay. So through that process.
Thank you.
Greg, do you want to do the next two questions?
Sure. So first is for G. First comment that those data are spectacular. Wow, congratulations. The question is, how long do you plan to continue operating?
So the design is for 4 years, but I think as long as it is good, we'll continue the operating.
Thank you. Next question for Marta. This is sort of related. Will Codex data be available basically 24/7, or is it mostly campaigns with gaps?
So basically, it depends when the sun is in visibility. Of course, we are guests in the International Space Station, so we are orbiting around Earth. So sometimes Earth is between Codex and the sun, so it's not in visibility. Sometimes we are on the other side, but the beta angle is not good enough. And so we cannot observe the sun. So there's an interesting diagram that I didn't have enough time to show that, but there's so in one ISS day we might have a range of time of observation that it varies a lot between the orbiting. That said, it also depends not just on that, but also on the activities that are going on the ISS, right? We are a coronagraph. We want to keep especially the external occulter and the tube clean, because we do not want more straight light than we are supposed to have. So sometimes might be necessary even to close the door and do, especially when there are extravehicular activities outside, or other visiting vehicles. So it depends. It varies a lot during the whole mission.
All right, so we have a question online from Gabriel. So I'll ask it. It's from Marta. Is the main idea behind Codex to measure changes in the shape of the polarized K coronal spectrum in the 380-440 spectral range?
In theory, yes. So basically, the concept of operation would be to acquire images, let's say for the temperature, acquire images with the first filter, then acquire images with the second filter, then do the ratio between the two and compare the results with the theoretical curve that we have. So what will be the final product will be an image of the temperature of the solar corona between 3 solar radii and 10 solar radii.
All right. Craig, I think you have the next one.
Wait, Samaya, it seems that KCOR and LASCO and Punch, or KCOR and Codex and Punch, are going to be very important for tracking the jets outward. Do you have a sense of how unusual those white light jet detections in KCOR are? Do you expect them all the time, or are they rare events?
They occur pretty frequently. We've been going back through the KCOR data and looking at a lot of the 5-minute cadence difference images, and at least a couple a day, and those are the big ones. But again, with some image enhancement and probably a careful look at the smaller ones, definitely at least some a day. So very frequently.
All right, I will follow up with a question. I think it also resonates back with an earlier question from Rahul. But first of all, do all jet models by definition result in mass escaping in the solar wind, or can there be some that shoot up and fall back down? And then also, kind of related, are there difference in the predictions of the models in terms of the behavior, like how far out and how collimated a jet might be? Because, of course, with Punch's sensitive detectors, you might be able to observe them quite a ways out.
Yeah, that's true. For the first part, jets experience failed eruptions just like CMEs are when you see other eruptions that do not overcome the overlying field. So they have to also make whatever eruption mechanism that's happening with the jet, it has to be able to overcome the overlying field or be able to open up the overlying field so that it can escape. So there are a lot of cases in which they don't. So in order for the jets to be contributing to the solar wind, most estimates try to look at jets in open field regions, so in polar coronal holes, on the boundary of those coronal holes, and quiet sun, because those are the most likely contributors to mass to the solar wind. The other was probably not as much. And then the second question was about models and how easily detectable.
How far out would you see them? Yeah.
Yeah. Definitely models do predict different widths and heights and paths for how far they will be able to go out, depending on how much energy is released in that process. So it definitely could. In order for Punch to be able to observe them, there would have to be additional circumstances, because most of the models, I think, are designed with the idea that these are typical jets, not ones that we see in extended white light jets. I'm not sure how the models of the extended white light jets differ in that way. So I could look at that. I'm not sure.
Sounds like we're going to trigger some more modeling. All right, let's go on to Rafael.
Hi, Marta. You, in an early slide, you mentioned some uncertainty on the measurements for the velocity, the radial velocity. Can you elaborate on the uncertainty we would get from the measurement on the superpixel of the Cameron Codex after we've scanned over the spectral bands?
So it's not a scan in the spectral band. So we are just acquiring image number 1, let's say, with the first filter, and image number 2 with the second filter.
That's what I meant. Once you covered after all the filters have been imaged.
Okay. So from the previous studies from Nelson Reginald, he showed that if we can measure the polarized brightness intensity with an uncertainty of 1%, then we would be able to estimate, to measure the speed with an uncertainty of 200 kilometers per second, which is high, right? So what we are trying to achieve with the data processing is that 1% of uncertainties. This means that once we remove all the noise given by this stray light that has been calibrated in the lab, and given the detector noise and so on, we would add different images all together to increase the signal. So the final, as I say, the final uncertainty is going to be those 200 kilometers per second. And this means that we're going to be able to say it's slow speed, or is low solar wind, or is fast solar wind, because this is in the method. Unfortunately, we're working on the lower part of the visible light range, and there are not so many photons, so we need to do a lot of co-adding. About the how many velocity measurements, well, as I was saying before, it depends on the ISS, how much, and also the operation is going to be for each day on the ISS. We're going to see how many minutes of observation we have available that day, and we're going to split between temperature and speed in order to be able to characterize the same solar wind in the two aspects, so temperature and speed together. So it really depends on the day of the ISS.
Okay, thank you.
All right, let's go to Craig's question for Michael.
All right, Michael, I'm poking at you. EUV imagers in general tend to have grid-mounted foil filters in the front, and you get diffraction off that. That's sort of a bane of dynamic range. So how are you overcoming that?
Yeah, that's a really good question. So I can say that about 90% of the stray light coming off of the mesh-mounted filter is blocked by the baffles that I mentioned. But then, of course, the point spread function is absolutely critical. However, we did prove that we can meet our minimum science requirements without a point spread deconvolution, and so that's that I said we were going to release levels 1 and 3 data products. The level 2 data product is the point spread function deconvolution, which should improve dramatically. So we have high hopes for being able to improve that. If for some reason it doesn't do as good as our simulations have shown, we're still going to be able to get our minimum science for CME tracking. But yes, that is going to be a critical piece of dealing with stray light.
With Dan on the team, I imagine you're going to get something.
Oh, we'll get something, yeah.
All right, here's a question for G. How far out do those beautiful Lyman alpha prominence eruptions go?
Yeah, for our event catalog, we do have some prominence eruption observed in the field of view of Metis, which is quite far away from the sun. I think maybe because the prominence eruption is really slow, so the Doppler dimming effect is not so severe for such event.
All right, let's have Bernie's. Bernie, yeah, you can talk. So do you want to make your comment?
Okay. Yes. The comments that is that large jets have been tracked from the solar surface in both the solar mass ejection imager that looked 20 degrees to the sun and stereo HI fields of view, and especially in perspective views, so you could get more or less total masses of these structures for the big ones. And so Punch will certainly see these, and we compared the bigger ones and determined how much material there was there relative to the ones that were where we had 800 and some X-ray jets that were measured in Hinode, and you could follow the energies there and determine how much the big jets that you could see in X-rays anyway populated the solar wind and what energy was available. And it was about 10% of the total solar wind in the range that, well, you could project this all the way back to zero energies. So because of that, you could say that the solar wind for the big jetting anyway only comprised about 10% of the total energy that's needed for the solar wind. So that's all been done. Be very interesting to redo this analysis with Punch and with other jetting that you see. So that's a comment here.
All right, let's have Joan's question for Samaya.
Yeah, hi, Samaya. Nice talk. This might be observationally impossible, but for some of those jets near the limb where they are field lines twisting or untwisting, if you look in line of sight Doppler, you think it's possible you might catch a blue-red signature in that twist? I don't know if you've done that or thought about that.
I've tried to determine that for a couple of the ones in comp and UComp, but I haven't been able to distinctly say that I see that signal. But I do have iris and ice observations of jets, and they definitely showed a blue-red signature.
Oh, that's great. Thank you.
And if I can follow on, there's a Chinese satellite, right, G, that might be able to help with that kind of velocity signature.
Yeah, there's another Chinese explorer called Chase, and it observes the spectral of HR5 and also includes the prominence. So you can get the Doppler velocity of prominence to compare with UComp.
All right, so now Ever, who I believe is online, has a question for Samaya. One of the figures you had, a label type 2 source region, but I missed any discussion you might have given on that. Do you mean the source for a type 2 solar radio burst, believed to be associated with a shock driven by a CME, or to a type 3 burst, usually coming from a reconnection region?
Yeah, that's right. That was a typo, sorry. It's a type 3 burst that came from a jet flaring region. And in fact, that jet was what we think was a type of, was accelerated through a two-step process, two-step acceleration. So some reconnection happened and then a different acceleration process, a different reconnection point. So yes, you're right. That was a typo in there. So
keeping you on your toes there. All right, is Kevin in the room?
Yeah. Marty, yeah, there's not a lot of photons in the blue. And what is the integration time that you need typically to get that 1%?
So there's a paper from Reginald, but if I remember correctly, for the temperature, it's something about 100 seconds of integration, and it's going to be coding images for sure. And the speed requires a little bit more of integration time.
One other question, if I can hop on. The models there for the shape of the spectrum and the velocity determination, are those just, single points in the corona? I mean, or are those taking into account a line of sight integration along the...
So as I shown, for the temperature, those nodes and also the differences in the anti-nodes regions, they do not change with the line of sight. So it's gonna change. Of course, the polarized brightness intensity is gonna change. So you're gonna see the curve translate up and down depending on the intensity and in which line of sight you are. But the nodes will be the same. So it's not gonna change that. For the speed, I believe is as well. Yeah, that's it.
Thank you.
Sure.
All right, the next one is Nariaki.
I think you already discussed this, but the big jets extending to tensor radius may be well correlated with type 3 bursts observed in DH, decometric hexametric wavelength range. The rule of thumb is the highest frequency of those instruments, like 14 megahertz, is 2 solar radius. And if we go down below 1 megahertz, it will be probably above 10 solar radius. So please check that.
Yeah, and I haven't looked specifically at this, but people like Ben Chin have been looking at these bursts in radio data, so it's been other people.
Has anybody looked in the white light that's there to see if there's any signature?
Connecting the white light just to those type 3?
Well, I mean, I'm thinking of like LASCO or something like that, or is it just not possible?
Not sure. I think most of these associates were made with AIA and X-ray data, so I'm not sure if they also connected it to the LASCO data.
Okay, let's go to Joan. Yeah.
Gee, I'll second what Craig said. Beautiful data. I probably missed it, but what was the cadence of the white light images?
I didn't see that in the presentation, but I just check it. It's around 1 minute. 1 minute in my movie. But I think it could be here. I'll check in the detail.
Okay, and that's online at that cadence too?
Yeah.
Okay, great.
All right, David is next.
Yes. Michael, what's the, you probably said this, but what's the inner limit of the field of view of Sun, CET, and the field of view looks like a natural match with K-core, and also maybe Proba. I'm not sure what their inner field of view is, but just wanted your comments on that.
Yeah, we've been using Proba data significantly with a lot of our data simulation and modeling. So absolutely, we overlap quite nicely with Proba. In terms of K-core overlap, we should have some really nice overlap too, because we're going from the inner corona all the way out to 4 or 5 our sun, depending on which direction you're looking in. So we'll be looking to validate and to work with those instruments to make sure that we have a good handle on what our data looks like.
All right, and the next two questions are related. I know my question, they're both for Marta, was kind of about like, these are different ways of getting velocity, so how do you connect them? But maybe, Joan, you can finish us with your comment. Oh, you don't. Oh, you answered it to Raphael? Okay, then my question then.
All right. What I envision would be, so Codex is gonna give you an image where every pixel has a value, which is a value of speed. So for the structures in the image, you will see an area of different speed with respect to the background. I do not know how many images we will be able to capture the same thing, but we will see an area of pixel with higher speed moving in some direction in the punch field of view. At that point, I think if we're lucky enough, there will be an overlap of these two. The two way of observing the same thing with the two different instruments. If we are not, I think we will need to use the flow tracking algorithm and then continue to track what we think it is, the same structure.
Okay, great, thank you. Do we have any other questions in the room? If not, let's give our speakers a round of applause. Okay, so I'll just say that I want to thank everybody who's come. This has been a wonderful meeting. I know that Craig's going to do some thank yous, but I especially want to thank the working group chairs who helped with the organization and the planning for this meeting and the choosing of the kind of topics we were doing. You'll probably mention who those people are. And also just want to thank the speakers in the audience. You guys have been great. It's a lively crowd. We've had great energy all week, so thank you.
All right, I'll try and take us home. So we have had another phenomenal meeting. I have an announcement to make at the beginning of all this, which is Ronnie Killo, our PM, hasn't been here since yesterday morning. He is now a grandfather. So he has a new granddaughter as of this morning. I don't know the name yet. So highlights, am I here? Right. So highlights from the meeting. We've had some great updates from our and thank you to Mary for coming in remotely when she felt sick. Let's see, status on the mission, outreach, STEAM, the ground systems, tremendous progress on all fronts. We heard a lot of great science this week, and that's been typical of these meetings. In-situ punch connections, shock and SCP events, really exciting stuff on connecting those with punch. Some great talks on tomography, how to identify prominence material in the punch field of view and track it. New insights on the kind of quantitative expectations we might have for punch data and what we can get out of it, and potential gotchas for the unwary, which was pretty exciting to me. We heard talks from Barbara Thompson on open science, which is near and dear to my heart, and which I hope we will all go forth and evangelize, because trying to keep our tools accessible and our data accessible to everybody makes the science better, as well as just is good. We heard talk from Joe Westlake summarizing what's going on in heliophysics. You could tell there's a lot going on in heliophysics right now. We all need to be ready to go out and evangelize getting more RNA funding into the division, more funding overall, but RNA as well, because there is a crunch coming, so be ready for that. I saw a ton of really exciting posters, flow models, turbulence studies, insights from in situ comparisons, and of course the space weather stuff. Really great contributions from everyone. I heard plenty of exciting conversations in the hall. I hope you all had as invigorating a time as I did. So we've already thanked the speakers and the poster presenters, but I do want to especially thank the folks who prepared posters for today, because they were phenomenal. And of course, we have a representative from NASA Management and Science Support. We have David Cheney here, Majulika Guhatakirta, who may still be in the room, but may have stepped out, and Nikki Vile. So thank you guys for making the trip out. As we wrap up here, I want to acknowledge the AV team, because it works best when it's invisible and it turns invisible. It's easy to not remember what a great job they're doing to make everything invisible. So thank you to Kelvin and to Joey in the back of the room there. Let's see, meeting logistics and organization, everything else went smoothly, largely because of the efforts of Carrie Dawn Solner, who has been fighting some personal illness to work on this and has done a bang-up job. So thank you to Carrie. And finally, thanks for organizing Sarah, for making yet another science agenda come out exactly right. Thank you. So as we move forward, this is the run-up to launch. I can't announce the date, but I will tell you that we will have another science meeting the week of February 23rd. We're organizing the logistics of that now. As we move into meeting schedules, this is the first year in a while that Shine and SPD haven't been in near conflict, so we'll enjoy that. AGU is going to be a large piece of splash for the community. Please wave your punch flag at meetings you attend this summer and at AGU. And we'll see you in February in California. So thanks, everybody.